조금만 다시 시작. 아. Okay, good morning. I think, okay, so we are ready, right? Okay, good morning, everyone. So today we resume the workshop, and the first talk will be by Rob Spekkens from Perimeter Institute. So Rob Spekkens is a professor in Perimeter Institute and working in Quantum Foundation. And today we'll talk about quantum interference. So, okay, thanks, Rob. The floor is yours.
Okay, well, thanks very much to John Wu. And as I was saying earlier, thanks for giving me the chance to participate in the conference virtually. I'm sorry I can't be there in person. So I want to talk today about, what is the essence of quantum theory? And what I mean by that is I want to talk about what are the precise conceptual innovations that distinguish quantum theory from the classical theories that preceded it. So an important question is, why should you do this? And I would say it has both practical and foundational applications. So on the foundational side, there's a sort of difficult question of how to generalize quantum theory into domains where we don't know how to apply it yet. So for example, we don't know how to apply quantum theory to gravitational phenomena. And so what you think is the essence of quantum theory will dictate sort of how you engage with that project. But also there's a lot of other classical frameworks where it's, again, not obvious what the quantum generalization ought to look like, and it depends on what you think is the real conceptual innovation of quantum theory. So things like if you're trying to generalize, say, the model of computation based on cellular automata, or if you're trying to generalize the framework of causal inference, or various concepts in machine learning, or algorithmic information theory. I think in all those cases, your views on what the essence of quantum theory will dictate how you pursue that project. And then finally, if you get the essence of quantum theory wrong, then I think you're less likely to be able to identify the true quantum over classical advantages in information processing. So I think it has practical applications in quantum technologies as well. So I'm going to be studying the question in the context of quantum interference phenomena today. And so the project I'm going to tell you about is actually an old project that Matt Leifer and I worked on back in about 2005, and we never wrote it up at the time. But in recent years, my former PhD student David Schmidt and Matt's former postdoc Lorenzo Catani persuaded us that we really ought to write it up. And in the process, we actually, as often happens, you learn a lot more about the topic than you had originally understood. So there's a lot more insight that came out of this new version of the project. Okay, so let me jump in, and I want to talk about the aspects of the phenomena of quantum interference that we're sort of generally told are puzzling or problematic for the classical worldview. So I'm going to call the phenomenology, the operational phenomenology, the trap phenomenology of quantum interference, and that's an acronym for typically regarded as problematic. So it's sort of the thing that you usually hear. But I also want to argue that actually you can explain this stuff classically, and so it's a trap to think that this is the essence of quantum theory. So that's the purpose of this acronym. And so the story is the one that I'm sure you're all familiar with, which is that if you take a double slit experiment, and so you have a source of photons or electrons here, and you don't observe which slit they went through, then you'll see an interference pattern on the screen. Whereas if you put a detector in front of one of the slits, for example, here, then that'll destroy the interference pattern. And so the puzzling aspect is that if you thought that you could explain this entirely in terms of waves, like something like water waves, then that has no trouble explaining what we see here. But you would have expected that, for instance, if I put detectors on both slits, that I would have both detectors be slightly excited. But of course, that's not what we see. What we see is only one detector at a time ever fires. So that's sort of what's puzzling about imagining that it's a wave ontology underlying it all. But on the other hand, if you imagine it really is particles, then the question is, well, why do you have this interference pattern? You can explain this side easily, but why do you have this interference pattern? And furthermore, even if you think that there's some way that a particle ontology could explain this interference pattern, there's the following kind of challenge based on locality, which is that if this is the setup over here on the right, and you happen to not detect the particle, so you know that it must have gone through the left slit. So if over here in this experiment, the particle also, sometimes goes through the left slit, then how does the particle know whether it's allowed to appear at one of the dark fringes or not? So that whether it's allowed to appear at a certain spot on the screen depends on whether the other slit has a detector on it or not. But this particle has never been in the vicinity of the right slit. It hasn't probed that region, so it doesn't know whether the detector's there or not. So how can it decide whether it's allowed to show up at these troughs of the interference pattern? So that's the standard story, which you can read about in for example, the Feynman lectures of physics. And in Feynman's treatment, he calls this impossible, absolutely impossible to explain in any classical way, and that this phenomenology has in it the heart of quantum mechanics. It's the only mystery, the basic peculiarity, and basically the essence of quantum theory. And so what I want to try to persuade you of today in this talk is that this is not correct, that this phenomenology I just described to you can in fact be explained in a totally classical theory. And the essence of quantum theory lies elsewhere. So first off, I'm going to not use the double slit setup per se, but I'm going to use a kind of a discretized version of it, which is based on the Mach-Zehnder interferometer. But it's the same story about what's puzzling. So here you have a single photon source on one of the input ports, vacuum on the other, and then you recombine them on this is a 50-50 beam splitter. You recombine them at another 50-50 beam splitter, and then you look for detections, and you can see interference here in the sense that I can choose these path lengths so that when I toggle the phase shift here between, say, 0 and pi phase shift, I can make sure that all the excitations come out either the left port or the right port. And so the fact that one of these ports is dark is kind of the analog of having those fringes in the interference pattern. Whereas I can also do the experiment in a way where I put a detector on one of the arms of the Mach-Zehnder, and now the interference goes away. I see equal probability of detection at the two ends. So it's the same sort of phenomena, but just in a simpler setting. And I'm going to now sort of just remind you of the sort of the treatment of this in quantum theory, but I'm going to do it specifically in a kind of second quantized approach. So I'm going to have a left mode and a right mode. I only care about a two-dimensional subspace of the Fock space for that mode. So the vacuum state and the single excitation state. So you can think of this as like a qubit for that two-dimensional subspace of the Fock space. And these are like the eigenstates of a poly Z observable in that two-dimensional space. But of course, I can also write down the complementary basis where the relative phase between the vacuum and the singly excited state is 0 or pi. So that's like the poly X eigenstates here. Now, if I ask about two modes, a pair of modes, I get a Fock space that has these 4 elements in it, where each mode can be vacuum or occupied. But if I'm only interested in the cases where this Mach-Zehnder interferometer has a single excitation in it, then I really just care about this two-dimensional subspace where the excitation is either always on the right or always on the left, and it's never one of these other two states. And so in that two-dimensional subspace of the full Fock space, I can also write down complementary bases where I have entanglement between the two modes. And so if I ask, what does a 50-50 beam splitter look like in this formalism? Well, if I start out with the excitation on the left and vacuum on the right, I put it through the beam splitter, it takes it to one of these entangled states. And basically, it's just doing a Hadamard transformation inside this two-dimensional subspace of the full Fock space. So that's the kind of beam splitter I'm assuming for simplicity. So here's how I recover those operational predictions I was telling you about. So originally, I have the excited tensor vacuum state here. I put it through this beam splitter, and the Hadamard transformation takes me to this entangled state. And now if the phase shifter is set to apply a phase shift of 0, well, that's just the identity, so I stay in that entangled state. And then I apply the beam splitter transformation again, but the Hadamard is its own inverse, so I'm back to the 1 tensor 0, and so I will always detect the excitation over here on the left board. Whereas if I go to the case where the phase shifter applies a pi phase shift, and that changes the relative phase of these two terms, because it's sort of a poly Z on the right here. So now I get to this entangled state, I apply the beam splitter transformation, and now I'm down to the vacuum on the left, excited on the right state, so I expect to see everything coming out this port. Finally, if I'm in the case where there's a detector on the right arm instead of a phase shifter, and for concreteness, imagine the case where you don't detect the excitation on this side. So that gets represented by the projection postulate in quantum theory, where I project onto the vacuum state on the right, because I haven't found the excitation here. And the only term in this entangled state that has vacuum on the right is this one. So I'm projecting, I normalize, I project to that 1 tensor 0 state. And now it goes through the beam splitter, gets taken to this entangled state, and I expect 50-50 statistics, because it's equally likely to be excited on the right or excited on the left. So that's the reproduction of the phenomenology I was telling you about. And as I said, I mean, this is same story as in Feynman. And actually in the Mach-Zehnder, there's this really nice dramatization of what Feynman described as surprising in terms of what's called the Elitzur-Weidmann bomb testing procedure. And so the story here is that you imagine there's a factory that produces bombs that have a trigger that is sensitive to even a single photon. But the manufacturing process is such that sometimes these bombs get created without any trigger at all. And the question is, can you figure out which are the good bombs without exploding them? Because if you sort of look at them to see if they have a trigger or not, you're shining light on them, and then it's going to explode. So here's the scheme that Elitzur and Weidmann devised for figuring out whether you have a dud or a good bomb, which is you place it in such a way that if it does have a trigger, it's in the right arm of the interferometer. So if it's a dud, like this one here, then this interferometer is just like the one I described, which has no phase shift here and no detection. And so everything should come out the left port. And over here, it's like the case where I have a detector on the right arm. And so what happens is that half the time, this detector sort of finds the excitation here and it blows up the bomb, but half the time it finds that the excitation is not here and the bomb doesn't explode. And you learn that the excitation must have gone left. But if the excitation went left, then it means that at this second beam splitter, it's equally likely to go left or right. And so half the time I find it on the left and half the time I find it on the right. And so that's the key thing, that when I find this right detector firing, I know it couldn't have been a dud, because everything comes out the left port when it's a dud. And so if the right detector fires and the bomb doesn't explode, I know it was a good bomb. So that's the solution. And the puzzle is just that, if you didn't find the excitation here and it went this way, how did the particle know whether the bomb was a dud or a good bomb? How does it know whether it's allowed to come out the right port or not? Because it never spent any time in the vicinity of this bomb. So it's the same puzzle as the Feynman double slit setup. Okay, so now I want to talk about how to explain all of that within a classical framework. And so we call the classical model of all this qualitative phenomena a toy field theory. And the idea is that there's a toy theory that I wrote about many years ago in this paper, which is a way of explaining the phenomenology of, collections of qubits, which are essentially, prepared in stabilizer states and subjected to stabilizer measurements and Clifford operations. So it's a theory that sort of reproduces that type of phenomenology qualitatively. And all I'm going to do here is sort of apply that same theory, but where my qubits become these Fock-based qubits, this vacuum excitation type of subspace. So that's all that's going on with the toy field theory. So here's the idea that for every mode that you're considering, there is a classical state space, which is actually a phase space. So lambda is just the notation I'm going to use for the classical state of this mode. And it has basically two properties, an occupation number and a phase. So these are just classical variables that take well-defined values. And the theory is very simple because the occupation number is just a binary variable. The occupation number is either 0 or 1. And the phase is going to be either 0 or pi, which I'm just going to denote by this binary variable. So it's going to be 0 or 1 as well. And so every mode has, is a point in this 4-state space, that has a binary number and a binary phase. Now, if I look at, if I ask, well, what could I know about that thing? One of the key parts of the theory is that every agent can only know the value of some Poisson commuting set of variables. So this is a phase space, so there's sort of a Poisson bracket on it, and I can talk about which variables Poisson commute with which other variables. And so you can only know values of variables that Poisson commute with one another. And besides that, you're going to be maximally ignorant. So to give you an example, if I just have a single mode, I could know the value of the occupation number of that mode, but then I don't know the value of the phase. So the occupation number could be known to have value 0, and then the phase is unknown. And in this theory, that's the analog of this a vacuum quantum state. Or I could know that the occupation number is 1, and then the phase is unknown, and that's the analog of this singly excited state in the quantum formalism. Of course, another variable that forms a Poisson commuting set, because it commutes with itself, is just the phase variable. So I could know that the phase is 0 or know that the phase is 1, and then the occupation number is unknown. And in this theory, those are the analogs of having the quantum state plus or minus in this complementary basis. Now, what about for a pair of modes? So now, again, each of these modes has a well-defined physical state, a number and a phase. They're all binary. So now we have a 4-dimensional phase space. And I can have some more interesting sets of Poisson commuting variables. So for example, the number on the left and the number on the right Poisson commute with one another. So I can know both of them. So I could know that the number on the left is 0, in which case the phase on the left is unknown, or I could know And I can know that the number on the right is 1, in which case the phase on the right is unknown. And that's the analog of this product state in quantum theory, where it's vacuum on the left, occupied on the right. But I could also have the reverse, where the occupation number on the left is known to be 1, occupation number on the right is known to be 0. Again, phases have to be unknown. And that's the analog of this 1 tensor 0 state in the quantum formalism. Now, when you get to the 2 modes, you have something more interesting, which is that you can find Poisson commuting sets not just in terms of local variables, but in terms of some global variables. So you can actually write down a coordinate system for the whole 4-dimensional phase space that's not just in terms of local number and local phase, but involves some global property. So this delta phi is the sum mod 2 of the local binary phases, and this delta n is the sum mod 2 of the local binary occupation numbers. And it turns out that these form a perfectly good set of coordinates. The number on the left is conjugate to this relative phase. This, I'll call this the relative number is conjugate to the phase on the right. And these guys Poisson commute with these guys. And so I can describe everything in terms of this coordinate system if I like. And in particular, this relative phase and relative number are a Poisson commuting pair. And so I could know both of them simultaneously in this theory. So in that case, this number on the left is unknown, the phase on the right is unknown, and I could, for example, know that the relative phase is 1 and the relative number is 1. And that's the analog of this sort of entangled state, where you kind of only, like here, you only know that one of the modes is unoccupied and the other mode is occupied, but you don't know which. And here you know that the relative phase is definitely a pi phase shift between the two. Okay, so that I've told you all about the sort of kinematics of the theory, and now the question is, well, what about the dynamics? And all I need to tell you is how the different non-trivial elements in this Mach-Zehnder interferometer are represented. And so for that, if I take the beam splitter, all I need to tell you is for every possible physical state, classical physical state at its inputs, what's the output state that results? So, I have a particular value of the occupation number and phase of the left mode and the occupation number and phase of the right mode coming in. And the question is, what values do I get out? And the answer in this theory is just given by this deterministic function. So for every one of the output variables, there's a specific function of the input variables that defines it. Turns out this is actually a symplectic transformation, so it preserves the Poisson bracket. So I can sort of think of it as a valid kind of classical dynamics. It's a bit hard to see what's going on here, but it turns out that if you write it in this other choice of coordinates with the relative phase and the relative number, it becomes very simple. So it says that the the relative number doesn't change at all, which is sort of what you expect, that the beam splitter transformation sort of preserves the total number. So if I have just one excitation shared among the two modes, it keeps it that way. So if delta n is 1, it stays 1 at the output. The phase of the right mode evolves trivially just by identity. And the only thing that happens to the other two variables is that their values get swapped. So in this theory, a beam splitter is very simple. If you say, well, what port is the excitation going to come out of at the output? The answer is it just tracks what the relative phase was. So if the relative phase at the inputs was 0, it comes out the left port. It comes out the right port. And if the relative phase was 1, it comes out the left port. Meanwhile, if you ask what the relative phase at the outputs is, it just tracks the number on the left. So if the number on the left was 0, the relative phase at the outputs will be 0. If the number at the left is 1, the relative phase will be 1. So it's extremely simple. That's the rule for how beam splitters work in this model. The rule for how the phase shifter works is also extremely simple, right? So we're going to imagine phase shifts just on the right mode. So the left mode is always just doing an identity transformation. So the output for the number and the phase is just the same as the input for both cases here. When the phase is 0, well, that's also identity, so nothing interesting happens. And when the phase is pi, well, all that happens in this model is that this variable that describes the property of phase just gets flipped, right? It's just a binary phase, so it just gets flipped. That's it. Okay, so how do you reproduce the phenomenology using this model? Well, let's go through it. I drew it here on the far right. So initially, we would have described it quantumly this way, but we describe it in this model as knowing that the left mode is occupied and that the right mode is unoccupied. But if I know that the left mode is occupied, of course, the left phase is unknown, the right phase is unknown, so the relative phase is also unknown. So that's sort of your state of knowledge about the initial condition. The beam splitter just implements this swap rule, which says that the value of the relative phase at the outputs of this beam splitter is just the value of the occupation number of the left mode at the input. So the relative phase becomes known to be 1. And now the number on the left becomes unknown because it's tracking the relative phase at the inputs. So this is the new state of knowledge after the first beam splitter. If the phase is 0, you just do identity, so you stick with that state of knowledge. And then the second beam splitter applies the swap rule again. And so the number and the relative phase just get swapped. And you're back to knowing that the number on the left is definitely 1. And so you predict that you'll definitely find an excitation on the left, and you definitely won't find anything on the right. So it reproduces that prediction. And now if you consider the case where the phase shift is pi, things proceed as before, except at this stage, I'm doing a phase flip on the right mode. And as the phase of the right mode changes, well, the relative phase is going to flip as well, because the phase of the left mode hasn't changed. So the relative phase gets flipped by virtue of that, becomes 0. Now I apply that swap rule, and the number on the left comes out 0, so that means it's the right mode that's occupied and the left mode that's unoccupied, so I predict that everything's going to come out this right port, which is the correct prediction. And then finally, we have to talk about what happens when there's a detector on this right mode, and it doesn't fire. So now there's sort of two things that have to happen. There's a Bayesian updating of your knowledge, so you learn that the number on the right is 0, and therefore you assign 0 probability to all the physical states in the theory that are inconsistent with this. So all the ones that assign, number on the right to be 1, set those guys equal to probability 0. So update your knowledge. Then the theory also says you need to randomize the phase of the right mode. So that means that with probability half, you leave the phase as is, and with probability half, you flip it. And the reason for that's part of the original toy theory. And that's just because this restriction on how much you can know, if there weren't this randomization of phase, then I could just measure number and then measure phase and come to know both of them. And so to prevent that, you have to imagine that the measurement of number randomizes the phase. So we're just borrowing this from the other toy theory, and it means that everything proceeds as before up to after this first beam splitter, and then if the detector does not fire, you learn that the number on the right is 0. So even though you didn't know what the number on the left was prior to your measurement, you now are certain that the number on the left is 1, because it definitely wasn't on the right, it had to be on the left, the excitation had to be on the left. And although you knew the relative phase prior to the measurement, you've randomized the phase of the right mode, and the phase of the left mode hasn't changed because you didn't do anything to the left mode. But so that randomization of the right mode phase has randomized the relative phase. So now the relative phase is unknown because it's become randomized. And so you do the final swap rule, and now the relative phase at the very far output is 1, and the number on the left is equally distributed. So you expect to find 50-50 statistics and no interference. So that's the basic reproduction of the phenomenology. So if you ask, well, okay, how does it answer the puzzle of the Elitzur-Weidmann bomb tester? Remember that the idea was, how does the particle know whether the bomb was a dud or a good bomb given that it went left? And the answer that this model provides is there is no particle in the ontology of this theory. What we have here are two modes, and they have internal degrees of freedom corresponding to occupation number and phase. And so even if on the right mode here the occupation number is 0, which would correspond to the quantum vacuum state, there's still a degree of freedom there, which is this binary phase. And that degree of freedom can encode information. And so when the bomb is a good bomb, what happens is that even though this mode is found to be occupation number 0, there's a randomization of the phase. And so that degree of freedom, the phase degree of freedom, can carry information forward about the fact that this was a good bomb. Over here, when it's a dud, the phase doesn't get randomized. So when it's a dud, you come up to the final beam splitter, the relative phase is necessarily 1, and so it definitely goes out the left. Whereas here, it's 1, or if this happens to be randomized and flipped, it comes out 0, and now it's allowed to go to the right. So there was something on the right path. It was this mode, and even though it's unoccupied, it can carry information. So to some extent, the lesson here is that we should think that a mode that's unoccupied can still carry information via its phase degree of freedom. And this really appears puzzling and non-local if you think that the fundamental description of what's going on has to involve particles rather than these modes and their internal degrees of freedom. And in particular, if you think that the vacuum quantum state is kind of a state of reality, then the only thing it seems to be possible to make it would be like nothingness. There's, nothing. If there's quantum vacuum over here, then that means there's nothing there. There's no possibility of carrying information. But in the sort of model I described, every pure quantum state really represents an ensemble of possibilities, a probability distribution over a set of physical states. And the vacuum quantum state is no exception. It's an ensemble of possibilities where the occupation number is 0, but the phase could be 0 or 1. And so even though this is, quantumly described as a quantum vacuum, there's still this extra degree of freedom of the phase that's sort of underneath that distribution that can be manipulated, that can be randomized based on whether the bomb is a dud or a good bomb. Okay, so I want to use this same model to explain a little bit more of the phenomenology that's usually thought to be puzzling. So there's this thing called the quantum eraser experiment. So the way it works is it's very much like the Mach-Zehnder interferometer experiment we just talked about, except instead of putting phase shifters or detectors on the right mode, I coherently couple that mode to another qubit, which is my auxiliary system A. And so I imagine that A is prepared in some state A naught, and there's a control naught applied to it, such that if this right mode is occupied, then A naught gets swapped over to the orthogonal state A1. And I then measure it either in this A naught A1 basis or in the complementary basis of A naught plus or minus A1, which I'll just denote this way. So that's the standard setup of the quantum eraser. And I'll sort of show you what these two measurements do. So if I think about what the C naught does to the right mode and this auxiliary system, it basically just says that the auxiliary system is going to be flipped only if the right mode was occupied, as I said. And so if I start out with some arbitrary state of the right mode, like alpha 0 plus beta 1, I do the C naught, and then I measure in this A naught A1 basis, I just collapse the right mode down to the 0, 1 basis. So effectively, I'm just learning whether the right mode's occupation number was 0 or 1. So this is just a coherent way of effectively doing a measurement of the number bases, right? So if I do this measurement, get the A naught outcome, that's just like having a detector here and not seeing the particle. Whereas if I get the A1 outcome, that's like having the detector here and finding the particle. It's the same effect. But if I instead measure the A naught plus A1 versus A naught minus A1 basis over here on A, well, then I'm going to collapse the R mode into, if I get the A plus outcome, I collapse it back to alpha 0 plus beta 1. And if I get the A minus outcome, I collapse it to alpha naught minus beta 1. And so that is like applying either identity to this guy or a pi phase shift. So yeah, if I get the plus outcome of this measurement, that's just like the experiment where the phase shifter was in place and the phase was 0. If I get the minus outcome, its effect on the right mode is just the same as if I'd had a phase shifter here with phase pi. Okay, so the thing that's usually thought to be surprising about this phenomenology is that many of the stories about the Mach-Zehnder sort of say that what you measure kind of determines the reality of the system inside the interferometer. That if you're measuring which way information, then it's that you're basically inducing it to be a particle, and if you're doing the phase shift, then it's allowed to kind of be a wave and have wave-like properties. But if your choice of what to measure, this basis or this other basis here, is on the auxiliary system, well, that system could be brought far away. I could postpone doing this measurement into the far future. And so it would seem, therefore, that my choice of what to do, far away in the far future, is kind of determining the reality inside the Mach-Zehnder interferometer. So that's usually what people say is puzzling, that this way of doing things makes it seem like there must be sort of causation backwards in time, for example. Okay, so now I want to show you, what all this looks like in this toy field theory. So I have to say a little bit about the kinematics for this auxiliary system. So it's going to be the same. It's going to be given a phase space. So it too just gets some classical underlying state space. And there's a coordinate q and a canonically conjugate coordinate that I'll call p. And they're both binary. And I'll just label the different values in a way that's sort of suggestive of the quantum states I wrote earlier. So the q can be A naught or A1, the p can be A plus or A minus. And so this C naught operation is just taking one of these modes, like the right mode here, which has a number and a phase, coupling it to this A system, which has a coordinate and a canonically conjugate coordinate, all of which are binary, and generates the same pair of systems at the output. And this is the function that it's just a deterministic function that stipulates the values of all the outputs in terms of the values of all the inputs. And of course, even though I've given these things the A naught, A1, and A plus, A minus labels, I can also think of them as 0, 1 valued so that these sum mod 2 make sense. So that's exactly what the C naught does. And if I then say, all right, well, what happens if I measure in the A naught, A1 basis over here? Well, that in this toy field theory corresponds to measuring this Q variable. So what happens if I measure this Q variable at the output? Well, remember that the input down here in the quantum case was prepared in this A naught ket, which in this theory is I know that this Q variable takes value A naught, and then this P variable is unknown. But then I learn what the Q variable is at the output. That's what sort of measuring the QA up here means. And so by virtue of the fact that I knew the input value of Q and I learned the output value, I can infer what the input value of the occupation number of the right mode was from this equation. And of course, that occupation number is the same as the occupation number of the output by this. And so basically, I've just learned what the occupation number of the right mode is via that measurement. So it's just like in the quantum case where you ultimately are just learning the occupation number here. But now you're learning the property that this system has. Meanwhile, if I measure the P variable on this output A, which is the analog of doing this A plus A minus basis measurement, the P of the output by this equation is the same as the P of the input. And that tells me what the difference between the input and output phases of the right mode are because of this equation, right? So knowing that, measuring that P tells me effectively whether the phase of the R mode has been left the same or whether it's been flipped. So just knowing whether this is 0 or 1 tells me whether it's identity or flip. Okay, so all that's happening here is that I'm learning different things about the properties of this right mode. So what people claimed was puzzling was that somehow the reality of things inside the Mach-Zehnder interferometer could depend on what you've measured here or here. But in this picture, all that happens, the reality of the right mode is the same no matter what you measure up here. It's always got a number and a phase. And all that changes based on your choice of whether to measure Q or P is whether you've managed to learn something about the number or learn something about how the phase has changed. And that's it. So all that's changing is what you learn. And so there's no influence of your choice on the reality. It's just your choice determines how you get to resolve your uncertainty. So there's no backward in time causation here. It's just as innocuous as, you know, I find some fossils today and I make inferences about dinosaurs living in the past. I don't cause dinosaurs in the past to exist. I'm just learning about them. And so that's exactly what's happening in this model of the quantum eraser experiment. Okay, so I should mention that you know, there's a lot that's said about what this trap phenomenology, you know, might force on us in terms of, you know, interpretations of interference phenomena. So I just want to mention that this model I just described shows that these interpretational claims are not forced on us. So one of those claims is wave-particle complementarity. So there's this idea that it's impossible to describe what's going on assuming that the system has, you know, both wave-like and particle-like properties. It's either got to be purely wave-like or purely particle-like, but there's no possible description of the two notions together. So that's not the case because the model I just gave you explicitly had the modes having both wave-like and particle-like properties. They have a phase and they have an occupation number. The second kind of claim is this observer dependence of reality. So you know, like in the quantum eraser, people said, oh, what I choose to measure actually influences the reality. But in this model I just gave you, all that your choice of what to measure has influenced is what you learn about the reality, but not, you know, what the reality is itself. And then finally, I mentioned that in the Elitzur-Weidmann bomb testing problem case, for example, people thought, well, maybe the only way to explain it is by having these non-local causal influences from, say, the bomb to the particle on the other wing. But in the model I just gave you, there were no non-local influences. You know, the modes have local properties, and every time I do a phase shifter or put a detector on one of those modes, it only influences the properties of that mode. The only place where the degrees of freedom of the two modes can influence one another is at the beam splitters or at the C0 gate, and nowhere else. So it's a completely local explanation of everything. Okay, so the first lesson of this toy field theory, I would say, is kind of very similar to the lesson of the older work I described, which is that it really is best if you want to see if you can get a classical explanation of some quantum phenomenology, you're much better assuming an analogy between quantum states and probability distributions over classical physical states. In other words, if you assume that the quantum states are understood as epistemic, you'll be able to explain a lot more of the quantum phenomenology just using a kind of fundamental classical ontology and dynamics. But there's, as I said at the beginning, there's kind of a second lesson that came out of all this, which is about the meaning of the distinction between the first quantized and the second quantized formalism for quantum theory. So I want to tell you a little bit about that. So first, let me remind you what sort of is the conventional view on how to think about these two formalisms. Certainly this is sort of the way I was taught to think about these two formalisms. And it's really a distinction between, you know, what are the entities and you know, what are the properties of those entities. So in the first quantized formalism, we tend to think that the entities are particles, and the kinds of properties they have you could call motional degrees of freedom. So things like, where is the particle located in space? That's its position. How is it moving through space? That's something about its momentum. That's the first quantized picture. Whereas in the second quantized picture, the idea is that no, we don't have particles at all. We have these modes, and their degrees of freedom are like internal degrees of freedom, which you might call excitational. So a mode can be occupied or unoccupied. It might have a phase. But in the second quantized picture, position is no longer a degree of freedom of some system. It's a label. Different modes are at different positions. So position becomes sort of a parameter that describes different systems, not a dynamical degree of freedom of a single system that can change. So that's the conventional view, and I want to challenge it. So let's remind ourselves, what would the account of the Mach-Zehnder interferometer look like if we had done it in first quantized description? So now instead of having two modes and the Fock spaces for each, I just assign sometimes people call it a dual rail qubit. I just say there's a particle in the interferometer, and it has these two quantum states of going left or going right. So there's just a two-dimensional Hilbert space. And of course, there's a complementary basis where I have the superpositions of those two possibilities. And that's it. And of course, there's a standard story about how you could recover the first quantized description from the second quantized description. So that the first quantized description applies only if you've got a sort of a single excitation there, single particle. So you're really, if I look at the second quantized description, I'm in this two-dimensional subspace where there's a single excitation. And the case where the right mode is occupied and the left mode is unoccupied is what maps to this R ket. In the case where the left mode is occupied and the right mode is unoccupied, maps over to this left ket. And any superposition with this in this 2D subspace gets mapped over to the corresponding superposition for this dual rail qubit. Okay, so let's ask ourselves, well, what does this all look like now from the perspective of this toy theory? And so I want to now present to you kind of a different version of the toy theory, which is kind of the analog of the first quantized description of the quantum experiment. So it's sort of like a first quantized toy theory. So you can imagine we just said, okay, look, there's a particle in this interferometer, and it has some definite property, a motional degree of freedom, which is just which way it is. So is it on the left or is it on the right? I could have imagined that. And then I could have imagined that I complete the phase space by saying it also has this binary phase, which I'll call theta. And that's all that's going on. And just like in the quantum case, I can imagine those variables as arising from the variables of this. Whoa. Sorry about that. I can imagine these variables arising from the second quantized toy theory. So this is the toy field theory I told you about, just by a kind of coarse graining. So this number on the left variable is what maps to the W which way variable. So if the number on the left is 0, that means the which way variable is R, right? And if it's 1, then it's this guy's left. And now this theta is just tracking what I call the relative phase in this second quantized picture. So meanwhile, this relative number is basically fixed to be 1, because the first quantized picture only makes sense when you have this single excitation. So you know that one of these two is 0 and the other is 1. And this phase of the right mode, we're just coarse graining over it. We're just forgetting that information as we make the transition from the second quantized to the first quantized toy theory. So the point is that I can think of this first quantized toy theory as just a coarse graining of the degrees of freedom in the second quantized toy theory, so that the entities are still modes that have these excitational degrees of freedom. And this stuff here is just sort of a coarse grained description of those, including some variables that are really about global properties of the pair of modes. And after I've done this, I can still recover the whole phenomenology, the trap phenomenology that I described earlier. Because if you remember that those accounts I gave only really talked about the number on the left and the relative phase. Those were the relevant variables. The other two didn't really appear because this one was fixed and this one wasn't relevant. So I could have given you an explanation at the beginning of the talk just in terms of this first quantized kind of toy theory where I have a W and a theta, and basically I just, everywhere where I had this NL and delta phi, I just write W and theta, and it would have been exactly the same story. I could have reproduced the phenomenology. But here's the key point. If I had said, consider this toy model that involves a particle with a definite property of location and a definite property of phase, I would have not been able to resolve the following puzzle. Remember that a measurement that doesn't detect the particle randomizes the theta variable. So you learn the W variable, you have to randomize the theta variable. Now, if you thought that what was going on is that you have a particle, and you asked yourself, well, where does this theta variable live? The only place it really could live is sort of on the particle. It has to be localized with the particle. So if a measurement over here was randomizing theta, that would have to be a non-local influence, because the particles, you just learned that you didn't detect it here, so it must have gone this way. You would have had to assume a non-local influence. So the point is that if you forget that this theta variable is actually a global property of a pair of modes, it's actually the relative phase of two modes. If you think it's an intrinsic property of the particle, then it looks non-local. But if you remember that it's just this global property of a pair of modes, then you know that I can flip the value of theta either by acting on the left mode or by acting on the right mode alone. And so, the fact that I have a detector that's randomizing the phase of the right mode is enough to randomize theta, and there's no non-locality required. Okay, so the second lesson of the toy field theory is that this second quantized description ought to be considered the fundamental one, and it's really a description of the excitational properties of modes, not a description of particles. And the first quantized description should be thought of as really just a coarse-grained description of an ontology of modes and their excitational degrees of freedom, and not a description of an ontology of particles. That's the lesson. And so I think this is this is one of the interesting things we learned when we came back to this project. Okay, so finally, in the last couple of minutes, I want to just say, what can we infer about what really is a challenge to the classical worldview in interference phenomenology? So, I argue that this trap phenomenology can be explained classically, but is there something that can't be explained classically? And so let me just say a little bit more about what I mean, what's my preferred notion of classicality. So in this talk, I've been basically using this notion that, that the kinematics of your theory is basically a set of possibilities, like a phase space. That dynamics is just a function over that set, like maybe a Poisson bracket preserving function. And then all your inferences are just done by classical probability theory. So that's all sort of part of what it is for a theory to be classical. But then there's also some principles that we want to adopt. This is a bit too weak. Like too much could be explained classically if this is all you assumed. Typically, we have some other principles, like the principle of locality, that we want to preserve. And so we demand that our classical explanations preserve these principles. And for me, there's something called the Leibnizian methodological principle, which is that things that are indistinguishable operationally should be represented physically as indistinguishable as well. And it boils down to something called the principle of generalized non-contextuality, which is an operational generalization of the Cauchy-Specker notion. And it includes local causality as a special case. If you don't know what generalized non-contextuality is, it doesn't really matter for the purposes of this talk. You can think of it as a kind of generalization of locality. And I mean, all this stuff is described in this paper. All you really need to know is that this toy field theory I told you about, I persuaded you that it was local, hopefully, but it turns out it's also non-contextual. So it satisfies that principle as well. So if you ask, well, okay, what aspects of interference do challenge the classical worldview? First of all, let me say that there's a way of answering this question that I don't think teaches us very much, which is that you can just take any operational setup that you know can prove contextuality in quantum theory. So we have a lot of proofs of the failure of generalized non-contextuality in quantum theory, and some of those proofs involve just a single qubit. And so I can take any one of those proofs, and I can just sort of make the qubit one of these dual rail qubits in an interferometer, and now I have a description of something that could happen in an interferometer that I can't explain non-contextually. But of course, I haven't learned anything. I've just translated something I knew into this, interferometric language. So the more difficult but more informative answer is to try to find some aspect of the phenomenology of interference, which was of prior interest to researchers, that people already sort of thought was maybe part of, what's the quantum behavior of interference phenomena, and show that that aspect of the phenomenology witnesses this failure of generalized non-contextuality. So we have done that. We've shown that actually the functional form of something called wave-particle duality relations can witness contextuality. So it can be sort of true non-classicality. So here's the idea that you imagine splitting this Mach-Zehnder interferometer into sort of a first half, which is like a preparation of this dual rail qubit, and then a second half, which is a measurement. And so maybe I've got, the beam splitter, the 50-50 beam splitter in place. That's one kind of measurement. It ends up just measuring the basis corresponding to, left plus right or left minus right for this dual rail qubit. Or maybe I just put detectors on these two guys, and now I'm just measuring the basis of left versus right. And the sort of bias for the outcomes of these measurements are described fringe visibility over here and what's called path distinguishability in this case. So basically the fringe visibility for a given preparation is just how well can I predict the outcome of this kind of measurement, and the path distinguishability is how well can I predict the outcome of this kind of measurement. And it's well known that these things trade off against one another. So as I vary overall preparations, I find that v squared plus d squared is less or equal to 1. So I can saturate it, and then I get this curve here. And the extreme cases where the visibility is 1 and the path distinguishability is 0, well, that's the case that we've talked about already, where I have a 50-50 beam splitter here. So then I can have all of the excitations come out one port and perfect fringe visibility. But in that case, I can't predict the which way information at all, right? Because it was 50-50 beam splitter. And the other extreme is where I maybe make this beam splitter perfectly reflective or perfectly transmittive. And now I can predict the outcome of this measurement, but I can't predict the outcome of this measurement. So I'm down at this point. Those are the only two cases that appeared in this trap phenomenology. Those were the cases that we were told ought to be surprising. And the question, and I've shown that you can have classical models of them, but what about the cases in between? Can we have classical models of those? And it turns out what we were able to show is that the principle of non-contextuality actually involves a trade-off, but it's a linear trade-off. It's this trade-off relation, not the square. So there's a gap. So when you see that at a particular value of the path distinguishability, the fringe visibility can be made, this high, that's a truly non-classical effect. That gap is something I can't explain in one of these non-contextual classical models. So this should appear on the archive probably next week. Okay, so the answer to the question, what's non-classical about interference, according to us, is just, well, there's this faux non-classicality, which is the trap phenomenology, but there's genuine non-classicality, which is this precise functional form of the wave-particle duality relation. That's what really witnesses quantumness. And you can start asking the same question for lots of other phenomena. So if you ask about uncertainty relations, well, we're sometimes told that the fact that you can't jointly predict say, poly Z measurement and poly X measurement, that's kind of non-classical. But actually, you can explain that in classical models where you can't know everything. There's an epistemic restriction can get you here. But the actual functional form of the uncertainty relation is what can't be explained non-contextually. This quadratic trade-off can be shown to violate a non-contextual bound. So that's what we did in this paper here. So it's that gap, that very small quantitative gap between what the trade-off looks like, the uncertainty relation in quantum mechanics and the uncertainty relation you would see in a non-contextual model. Okay, so it's the same story for all these other stuff. If I look at bipartite correlation experiments, then EPR Bohm, that can be explained with a local hidden variable model. It's not really non-classical, but Bell inequality violations, that's truly non-classical. So this is the caricature people usually use. It's a thin gap, quantitative gap. We have a paper about state discrimination, same idea. The genuine non-classicality is in the functional form of the trade-off between the probability of discriminating two non-orthogonal states and how non-orthogonal they are. Again, you see a gap, which is the real quantumness. And if you see these papers, if you go looking at these papers, it's the same thing for cloning, unambiguous state discrimination, weak values. You can do this for really any phenomena you like and try to find the true gap there. So just what I want to say at the end is that all of what I've told you just now is sort of part of a broader research program where you're trying to identify the kind of thin film of true quantum effects. Most of what we're told is the essence of quantum theory for various phenomena. I think can be explained in classical models, as long as you're careful to make sure that the quantum states get represented by probability distributions over classical states. That's important. And as long as you let your classical ontology be a field ontology, not a particle ontology, that's also important for capturing a lot of these phenomena. So the transition from a particle to a field ontology is not a transition from classical to quantum, because of course, there are classical theories of fields. You can have classical theories of fields with a restriction on how much you know, and you can reproduce a lot of the wave-like phenomenology of quantum theory in those classical theories. But you can still find this sort of thin film of truly quantum effects, and that's what really we should be looking for to kind of understand the information processing advantages of quantum theory. So with that, let me stop, and thanks for your attention.
Thanks a lot, Rob. Yeah, it's very nice and inspiring talk. So maybe we can start the question from Hyun-Suk Zhong, I think.
Hi, thank you for your very nice talk. I much appreciate it. I think it's a very interesting quest to explore this quantum and classical border, while people have different understanding and notions of classicality and non-classicality, pushing the classical limit as much as possible. Listening to your talk, I've got two questions. The first one is, can your theory be applied or extended to a continuous variable system with an infinite dimension, including Gaussian and non-Gaussian states, measurements and operations? That is my first question. And the second one is about the epistemic restriction. It seems to play a crucial role as the basis of your whole theory. But other than to reproduce the predictions of quantum mechanics, can you suggest some other reason that we must have this kind of restriction in a classical world? I think if there is some kind of reason like this, your theory should be very attractive. Yeah. So,
okay.
Yeah.
Yeah, thanks for your questions. So the answer to your first question is yes. We have done a certain amount of work on writing down classical theories of continuous variable systems and seeing what part of the phenomenology of like quantum mechanics for particles can be reproduced. And so we have a set of axioms which sort of define an epistemic restriction. And what you can prove that you can reproduce in a non-contextual local model is all of Gaussian quantum mechanics. So if I look at the quantum mechanics of collections of particles, then as long as the Wigner representation of the state preparations and the transformations and the measurements in your experiment, they're all positive, then I can think of all of that as just, it's a classical theory where I have probability distributions, and the Wigner representations are describing those probability distributions. So it all has a classical interpretation. And what you can show is that as soon as you get out of that Gaussian subtheory, then you have the opportunity for proving contextuality and non-locality. So there's a kind of tight connection between Gaussianity and the possibility of this sort of classical explanation. So that you can read a bit about that in this fourth reference here, but there's an earlier paper with Steve Bartlett and Terry Rudolph that this one's building on that also deals with that case. As for your second question about the epistemic restriction, I mean, for the purposes of what I'm saying in this talk, it's not so important that the restriction is fundamental, that if I can give you a model of the phenomenology of, the Mach-Zehnder interferometer in terms of a subset of all the probability distributions you could imagine, it just means that, like, okay, the theory that describes this phenomenology only uses these probability distributions, but it's conceivable that maybe the theory is wrong and I could access other distributions that have less uncertainty. So you could, in principle, sort of avoid the epistemic restriction if that's really what was going on in the world, if these classical theories were really describing what we see. So in a way, it's not really key. You can think of it just as like, oh, this is a classical theory where I only make use of some of the probability distributions that the theory has available. And that's already enough to show that there's a classical explanation of the quantum phenomenology.
Okay, just one more question then. Can you formulate your theory in terms of hidden variables?
Well, it is, I mean, what I'm talking about really are hidden variable theories I mean, I call them ontological models just because the term hidden variable has a certain amount of baggage where people think that that the case where, for example, just the quantum state is real is not a hidden variable theory, but I want to call that an ontological model. But yeah, these theories that I've been describing are hidden variable theories, but the main difference from other more traditional types of hidden variable theories like Bohmian mechanics and others is that in those prior hidden variable theories, the quantum state was taken to be one of the variables, one of the things that was real. Whereas in these approaches, the way you get back to the quantum state is that different probability distributions over the physical states and the hidden variables correspond to different pure quantum states. But yeah, it is a kind of hidden variable theory. And you know, the reason we study them is not because we think hidden variable theories are the right theory of the world. It's because only when we figure out what local non-contextual hidden variable theories can explain can we find that thin film of things that really are hard to explain, which is where the interesting stuff is, which is what quantum computation and cryptography are kind of built on top of. So we study the hidden variable theories just to know what's uninteresting.
Okay, I think I got your motivation. Thank you.
Okay, thanks for your questions.
Okay, thanks, Dan. Kieran, so Kieran is around. Yeah.
Hello. Hello, Rob. Thanks for the nice talk this morning. I've got a question. It's kind of related to the previous question in the sense that I'm interested in trying to understand this epistemic restriction. So I try to think about in which sense the epistemic restriction is interpreted classically. And if I do this, I think, how could I implement it in some classical system? Then it seems to me that what it comes down to is a kind of finite memory requirement, that you can only have one bit of information about a given system with some constraint. But when I think in this way, it seems to me now it's become an ontic restriction instead of an epistemic restriction. So I wondered if you could convince me that we have to interpret this thing as a restriction on the epistemology of the model.
I don't think I would want to persuade you of that. Yeah, ultimately, I feel like it ought to be possible to understand an epistemic restriction as being a result of the kind of dynamics and kinematics that's allowed in the theory. So, you know, roughly speaking, you know, every system in the universe that could said to be to know something about the systems around it can only do that by virtue of like physically with them and you know, having some like memory storage system. And so, you know, the possibilities for what anything can know ought to arise as a result of kind of your fundamental physics. So that's how I see it ultimately, you know, being justified. But because all of these epistemically restricted classical theories are not empirically adequate, they, you know, they can't explain Bell inequality violations or non-contextuality inequality violations. You know, there's a sense in which, you know, trying to justify them in terms of the fundamental, you know, ontological dynamics is not such a worthwhile project. Whereas I feel like if we could understand sort of the quantum analog of it, it would be more interesting to ask how this restriction on observers emerges from the fundamental physics of the observers.
Okay, thank you. Thank you for the answer.
Thanks for the question.
So maybe we have a quick question from the audience. Okay, Taiko.
Hi Rob, it's Taiko here. Do you hear me?
Yes. Hey, Taiko.
I need to first express my sadness that you are not here. But you had this slide about classicality. What you mean by classical? Well, and then you had a first sentence was there something like kinematics and dynamics is described by sets and functions. Do you admit that you had this sentence?
Yes. Yes.
Yes, but this means, for me, this means almost nothing. I mean, Hilbert space is also a set. It's just a specific type of set. Hilbert space operator is a function. So, I mean, what you mean by this? Because almost everything what we do are sets and functions, just with some specific structure.
True. And that's really why I said ultimately that if you just said, you know, classicality is the kinematics and dynamics of sets and functions, and your inference is done by classical probability theory, you can explain almost any theory in that way. You have to add principles like non-contextuality and locality to let those have teeth. But to some extent, there is an ambiguity in the quantum formalism. That the way I put it in a title of a recent paper, that's this paper at the bottom of that slide, is that we need to kind of unscramble the omelet of causation and inference. That the quantum formalism is given to us, and it tells us, okay, there's going to be some correlations, but it doesn't tell us, for example, did those correlations arise because of a common cause or because of a cause-effect relation? It just says, here's what the correlations are going to be. So there's a sense in which the formalism doesn't tell us whether the set of, say, pure states should be thought of as a set of physical states, so the kinematics of the deeper theory, or should I think of the set of pure states as a set of probability distributions over some other manifold, which is really the thing that describes the set of possibilities. So just to say that I think, interpreting quantum theory where the pure states is the kinematics is a very specific kind of, what I call a psiontic model. It is radically non-local and contextual, so that's kind of why I don't like it. Mm-hmm. But it's not the only way to interpret the formalism.
Would you agree that it's more about principles that are valid? It's not about mathematical representation, because this we can always change. I mean, we can have many different kind of mathematical representations for classical or quantum, and it's more about, contextuality.
Yeah, I agree that the way I like to usually say it is that the kinematics and dynamics is more about the kind of the fundamental causal structure of the theory. And I think that you can say some things about the causal structures that are sort of independent of what sort of formalism you're using. Like, are you doing it with path integrals or in the Schrodinger picture or with Wigner representations? Like, there's a whole bunch of choices you have to make, but I think there are some facts that might be common to all of those, which correspond to the causal structure. But I totally agree that it's really this sort of principles that are doing most of the work in kind of constraining the possibilities for explanations.
Mm-hmm. Okay, thanks for your talk.
Oh, thanks for the question.
Okay, so let's thanks a lot. Okay, yeah, let's thank the speaker again. Okay, so now we move to the next talk. Then I will pass the microphone to my colleague.
Hello, Paula. Are you online?
Yes, I am here.
Hi, nice to see you online. And thank you for accepting our invitation. So let me start. First, let me introduce Professor Paula Capellaro. Paula Capellaro she's a professor, the fourth professor of nuclear science and engineering at MIT, currently leading quantum engineering group. Her major contributions has been in developing control techniques for nuclear and electron spin qubits, including diamond MV centers. And these works are inspired by NMR techniques and quantum information ideas. And the goal of these works is the realization of practical quantum nanodevices such as sensors and simulators, and more powerful than classical counterparts. And meanwhile, the acquisition of a deeper knowledge of quantum systems and the environment is also the goal. And I'd like to also briefly introduce our two panelists. One is from Dr. Oh from Korea Research Institute of Standard and Science, and there's another panelist, Jung-hyun Lee from Korea Institute of Science and Technology. Panelist, Dr. Oh and Dr. Lee, can you briefly introduce yourself? Are you online?
Yes.
Yes.
Dr. Oh, you can go first.
Oh, okay. Thanks. This is Sangono. I'm at Chris. Mostly I'm working on diamond MV-based diamond sensors.
Thank you for inviting me for the panel. I'm working at KIST. We're trying to utilize the diamond MV centers or silicon vacancies for building quantum processors that can be useful for quantum computing system.
Okay, thank you, Dr. Oh and Dr. Lee. So now I think we're ready for the talk. Please welcome Professor Capellaro. Paula, the stage is yours.
Thank you so much. Hopefully you can hear me well.
We can hear you very well.
Perfect. Okay, so I want, of course, to start by thanking everybody in putting up this very nice program, and I hope that I will be able to stay online a bit and listen to a few more talks. And thank you so much for the invitation to present some of my work and sort of kick off this discussion about quantum sensing. So I listened a little bit at the previous talk, and this is going to be quite a different type of subject. So I'm interested in my work in performing quantum sensing because I really like to bring together both the beauty of quantum mechanics, but also some practical advantages, some practical application that they might bring. So before I really start and present some of my work, I just want to motivate why we are interested in quantum sensing. And the idea, in some sense, is very, very simple. We know very well that quantum systems are fragile, and so it's difficult to preserve a quantum system in its own quantum state, in its coherent superposition, and so on and so forth. And this is because we are very, very sensitive to any external perturbation, so to the environment. At the same time, this sensitivity, of course, makes them very good sensors, because it means that they connect very strongly, very precisely with the external world. However, of course, what makes them great sensor also, again, make them fragile. So what we would like to do is to find the best compromise between these two things. So in order to have the best sensitivity, or if you want the best signal-to-noise ratio, what we want is to preserve the signal that we want to measure, but at the same time canceling out the noise. And this is not so easy, because the signal that you are trying to measure, let's say a given magnetic field or an electric field, or maybe change in temperature, it's something which is unknown to us. That's why we're trying to measure it. And so because it's unknown, it looks very much like any other source of noise. It has often very, very similar properties. And so it's become difficult to preserve the signal while canceling out the noise. If we cancel out the noise, it means that we will have a low decoherence and we will have the longest possible interrogation time. So we can let the system evolve for a long time under the effect of the signal. It will acquire, it will arrive to a state which is quite different from the initial one, and so it becomes easy to detect the external parameter. And so what we would like is indeed the possible longest t, and so the possible longest, let's say, coherence time here at T2. At the same time, we would like that the signal produces the possible largest change of the sensor state. And so what we would like to have is a strong coupling. However, these two things are sort of in contradiction. If I have a very low decoherence, it means that my system is not connected very strongly to the external world, so most probably also this gamma is small. Or if this gamma is large, then most probably the system is also very sensitive to any other source of noise, and so T2 is short. So the product gamma and T2 is somehow constrained. So it's not like a precise relationship, of course, but it's somehow constrained in many, many different systems. So what we would like to do is to act on the system so that we can somehow protect it. For example, applying some quantum error correction scheme, some dynamical decoupling. But at the same time, these protections should somehow magically let the signal pass through so that we can detect it. So how can we distinguish noise from signal? So there are various strategies that indeed we are trying to sort of both devise and implement experimentally. And some of the ideas come from trying to exploit correlation, temporal and spatial correlation in the noise and the signal so that we can indeed sort of distinguish between the two. And we can also, again, apply control and potentially some entanglement between our system in the qubit sensor in order to improve this task. So, of course, all of this will give us some practical advantage in sensing, which might happen even before, for example, we achieve the true quantum advantage, which is the Heisenberg scaling with respect to the standard quantum limit scaling. But I think that indeed just achieving some practical advantage for quantum sensor is something which is a bit more near term and definitely worthwhile exploring. So if I had to plot on a chart some of the achievement that magnetic field sensing, in particular with NV centers in diamond, have achieved, you would see that these sort of put quite a bit of previous work in several different parameter regimes. In particular, we also recently achieved some pretty good magnetic field sensitivity for detection of fields around 3 gigahertz, which is the resonance frequency of the NV themselves. And indeed, what we can see is that there are a few techniques that one can exploit in order to achieve magnetic field sensing. These go from Ramsey interferometry, which is the basic technique in which you just exploit a superposition in order to see the presence of an external magnetic field. Then there is a Rabi experiment in which indeed you will see frequency shift at the frequency of the MV themselves, so the presence of some fields which oscillate at the resonance frequency of the MV. And then there is another regime which is on the kilohertz to low megahertz, in which you can apply dynamical decoupling to indeed be able to detect fields. However, as you can see, there is a large sort of range of frequency which is very difficult to tackle, and also all frequencies which are above the resonance frequency of the MV center. The other things which is missing is to extract the vectorial information out of the sensor. So there has been, of course, a few work in all this direction, for example, simply increasing the magnetic field strength, which is applied externally to bias, and exploiting NV in various directions in ensemble. But typically, these approaches are not as robust as we would like in many different directions. So these sort of illustrate that despite the fact that we have a lot of success even with the MV center, which is the most well-developed spin defect sensor, we still have some work to do in order to extend the range of applicability of this type of system. And so what I want to do today is indeed to show a few directions, if you want tricks that you can use in order to expand the potential of this magnetic field sensor. And in the process, hopefully, convince you that indeed we still need to find a lot of control techniques in innovative ways of doing sensing in order to really be able to achieve all the potential of NV centers. So the first thing is to try to detect DC field by exploiting the fact that the NV center is actually not a single defect, but it has also a nuclear spin which can help in the task. So it's the nuclear spin which will help the task of the MV center. So before I present this work, I just want to do a brief recap in what I mean by dynamical decoupling for quantum sensor. So if we assume that the main source of noise is the phasing, so some random magnetic field in the z direction with respect to the MV axis, then we can apply spin echo and some longer pi pulse sequences like CPMG, XY, etc., to refocus this type of noise. And of course, the idea that what we want to do is to sort of invert the phase spreading with pi pulses faster than the noise can act. So if I have some random phase accumulating for some time, I do a pi pulse, this random phase will sort of refocus back, and so I recover the coherence. Of course, this will also cancel out any static magnetic field, but we can then sense fields which oscillate in step with the pulse sequence. And so these allow to do this relatively low frequency, kilohertz to a few megahertz detection of magnetic field. However, it refocuses the quasi-static noise, and also fields which are themselves static. So again, if I want to detect a static field and cancel out the noise, I don't really have a good protocol because, of course, they look very much the same. So the typical solution for classical sensor is to use a lock-in amplifier. But however, we cannot do it very often with quantum sensor because this will sort of imply to add some sort of bulky apparatus, and we want to exploit typically the nanoscale properties of the sensor. So how can we do? Well, in order to understand that, we want to sort of have a better picture of how the noise acts. So if I have a pulse sequence now with many pi pulses, this modulates the phase which is acquired, giving a plus and minus sign every time that I apply a pulse. In the frequency domain, this looks like a filter for a particular frequency which corresponds to this pulse space in tau. Indeed, this is what is allowing this cancellation of the noise. So if my noise spectrum is shifted with respect to the filter of the pulse sequence, typically the noise spectrum is around 0, but okay, it could be also at a higher frequency. If the two don't have a large overlap, the exponential decay becomes much, much smaller. And so we will have an improved qubit coherence. I can also use the same technique and sort of sweep the frequency of the filter by changing the pulse spacing and trying to reconstruct the whole noise spectrum. So once the noise spectrum is known, then I can go ahead and do optimize sense. However, again, this works well for low frequency signals, but it doesn't work for DC signals. However, we can exploit the nuclear spin in order to frequency upconvert even DC signals. So again, if I have a DC signal, what I would do is to mix it with a reference field, some local oscillator at some higher frequency, and then send the signal through some bandpass filter before I do some detection. We already have a bandpass filter. This is given by the dynamical decoupling sequence which I introduced, but we are still missing the mixer. So what we can do to achieve this mixer? Well, we can exploit the fact that actually we have a local oscillator, which is given by the nitrogen-14 spin, which has a quadrupolar interaction, which is around 5 megahertz. So this is high enough frequency, which is typically separate and distinct from all the other noise which is in the system. The mixing happen through second-order processes involving the electronic spin and the nuclear spin. And in particular, what gets mixed in and up-converted are transverse fields, which indeed mix the energy level of these two spins. And then we can simply apply these band pass filter given by the dynamical decoupling sequences in order to detect the DC field, which transverse DC field, which has now become an oscillating Z field, so a longitudinal field for the MV center to detect. So in this way, we can really use a single defect in order to detect this static transverse field. In addition, we can, of course, still combine with simple Ramsey, which will measure the longitudinal field, static field, and so achieve a vector magnetometry using a single spin, instead of needing to use an ensemble of spin. And so we sort of like preserve the spatial resolution of NV centers. And indeed, this could be as small as a few nanometer resolution, while still achieving the reconstruction of the full vector magnetometry. So we demonstrated that in our setup with engineered field, and we were indeed able to observe variation in the signal as a function of the field, external field strength for both transverse and the longitudinal field using the two detection method, so the sort of nuclear spin mixer for the transverse field and the Ramsey for the Z field. Although they had slightly different amplitude here because of the timing that we chose, we actually had the same, if you want, overall slope of the signal. And so indeed, we achieve a similar sensitivity for detection of both a component of the field. And with the addition of some phasing of the pulses, one can reconstruct indeed not only the X direction, but also the angle in the transverse plane. So this is one example in which like the nice idea, the trick that we use is to realize that actually we don't have a single qubit sensor, but we have 2 qubits that indeed can be exploited, and in particular exploit their correlation, even if the nuclear spin doesn't even need to be polarized, so there is no real entanglement if you want, but just the correlation between each spin can achieve a task that a single spin qubit cannot achieve. And so I think that like this type of idea of using a small quantum system to achieve tasks that a single one cannot do, sort of put itself in between having quantum advantage with larger spin system and just having single qubit sensors. For the moment, this project was detecting DC field and achieving vector magnetometry of DC field, but we also wanted to detect the vector components of a C field. And so how can we do that? So in this case, what we exploit is just simply the control of a single spin itself. So if you have an AC field, which is in an arbitrary direction, you can always decompose it into its longitudinal and transverse component. In particular, if you look at the same field in the rotating frame, which is rotating at the applied microwave frequency, what it will look like is something like this. The longitudinal field will be unchanged. Its frequency is still omega s because indeed the rotating frame rotates around the z, and so it will not really change. However, the transverse field now gets downshifted by the frequency at which the rotating frame rotates, so this omega s. Sorry, this omega frequency here. And so now the 2 components, the longitudinal transverse component, they have different frequency and can now be distinguished just by the frequency. Indeed, we can now tune the driving field, this Rabi driving field, to match either the omega s of this shifted frequency and detect the 2 fields separately. This is what we demonstrate here. Okay, so we detect that we have both a z component and the transverse component of our field by sweeping the amplitude of the driving field between 22 and about 28 megahertz to sense the presence of both these 2 fields. And we can indeed use this technique to map out all the vectorial component of the source of our magnetic field, which is actually a single simple wire. So indeed, this is much longer than our diamond, and so it looks like an infinite wire, which has the typical sort of a fill line represented here by this thin blue line. And by looking at different MV centers, we can indeed, for each MV center, reconstruct the direction of the magnitude of the field, and indeed the reconstructed magnetic field does matches with the prediction from the classical model for the infinite wire. One of the advantages of these techniques, which only relies indeed on control, is the fact that we are using the same experimental tools to detect both the transverse and the longitudinal field. And so we expect to have the same amount of errors for the 2 type of detection. And so we expect that bias error and other technical error will be the same, and so this becomes a very robust technique to do vector magnetometry. However, in this case, we are sort of stuck with measuring fields which are not too far away from the range in which we can tune this Rabi frequency, and so we wanted to sort of move away from this restriction and really fill up the gap that I show you in my plot of sensitivity versus frequency. And so really try to do broadband sensing, being able to detect any possible frequency. So how can we achieve this? We can do that by implementing a quantum frequency mixer. So again, in this vector sensing with this frequency shift, what I told you is that in the rotating frame, the longitudinal field is unchanged, but the transverse field is shifted in frequency by the frequency of the drive field itself. We can sort of generalize that by adding an additional bias field. So if we have our signal field and we add an additional bias field at a different frequency, we can create an effective signal which is at the mixed frequency. So this is sort of similar to what you have in classical mixer, but indeed what we need to do is to engineer the same type of nonlinearity which make a classical filter work. So how can we indeed engineer this nonlinearity? These are achieved by the NV center itself. So your quantum sensor is going to work as both a sensor and the quantum mixer. We can demonstrate that, and indeed in this case, we don't really need to be set or to be restricted by the amplitude of the field that we use to probe this effective signal. We can always select a target frequency omega t, which matches our experimental capability. So for example, we were detecting a signal at about 150 megahertz, even if we were only able to generate about 3 megahertz of rapid driving. So we can really now sort of sweep any frequency and be able to detect signal of really any frequency using this method. So again, as I said, what we need to do is, however, to be able to achieve this mixing. And to do that, we need to engineer some sort of nonlinearity. This can be understood by using a flow-case theory, and actually multimode flow-case theory. So I have now both a signal field and a bias field. For example, and like you can have many combinations of transverse, longitudinal, etc. But just to be concrete, now my signal is in the transverse direction, and I can apply a longitudinal bias field. I can now use a flow-case theory to expand the two-level system that I have into many bands, which correspond to the Fourier component of the two fields that I'm applying. Because I have two fields, I have now a two-dimensional system with an infinite number of bands here, which are similar to the quantized electromagnetic field, if you want, but this is just sort of classical field. So now what I have is that I have two possible transitions, which appear to the fourth order perturbation theory. One transition happens that the spin will sort of flip, but then flip back and come back to the same state. In this way, through this process, I only acquire a frequency shift, which is indeed the very well-known SC Stark shift, but I'm not flipping the spin. Another transition, which is indeed enabled by the fact that I also have this additional bias field. So I have both a bias and the signal. Now what happens is that the spin is sort of like excited to one larger manifold, and then it can flip and go to the other band. So in this way, what I have is that I have indeed a spin flip, which can be then measured accurately. So it's these second order processes which are in they of course include commutators of intrinsically quantum, which give rise to this nonlinearity which achieve the quantum mix. In the end, what you have, as I said, is just an effective field. So I have my signal, a bias field, and in the rotating frame, I just have indeed both a longitudinal and the transverse field coming out from the two components. And they're now effective field at the target frequency. So now I can use any of the well-known protocols for sensing, such as spin locking, CPMG, and so on and so forth, to detect this field. So indeed, the protocol is not more complicated than what people have used until now. You just need to be able to add this bias field, and then you will convert any signal to the target frequency that you can detect with well-known control sequences. So we demonstrated indeed our ability to detect this field around 100 of megahertz and also around like gigahertz, but far away from the NV resonance frequency, with using both, as I say, spin locking or Rabi, if you want, and CPMG techniques. And with both of them, we were indeed able to detect both the transverse components and the longitudinal component, achieve very similar sensitivity as illustrated by the evolution of the system as a function of time. So this sort of explain how we can indeed use some slightly more advanced form of control. It's actually not too complicated, but what is sort of like more subtle is analysis that we do through the flow K theory in order to really be able to predict precisely what are these second order transitions that allow us to measure these fields. The last things that I want to talk about is how we can improve our quantum sensor by performing better material characterization. And in this case, what actually we were trying to do was to sort of improve a quantum sensor based on the nuclear spin of the nitrogen 14 associated with the NV center. And we actually use the NV center electronic spin as a controller which enables to improve the coherence time of the nitrogen nuclear spin. So this problem actually was inspired because we were trying to build a nuclear gyroscope following theoretical work that we proposed by now almost 10 years ago, and also some more recent experiments in other groups. And indeed, what we wanted to do was to demonstrate a very stable and robust nuclear spin coherence. However, we saw that some sort of like weird behavior, at least initially to us. Indeed, if we were measuring the Ramsey decay, so T2 star for the nuclear spin, when the NV is in 0, we had pretty long coherence time, although not as good as we wanted. While if we were moving the NV centers to the -1 state, the coherence time was much, much smaller. So this was in large ensembles. I should make it clear. And so what we were starting to think is like, well, okay, the NV center as an hyperfine interaction, maybe what we are observing are some inhomogeneities in the hyperfine interaction. Indeed, when the NV is in the ±1 state, we have this hyperfine interaction, and the strength of the hyperfine is on the order of 2 megahertz. This is almost like 1 Tesla if you were to convert it into a magnetic field as sensed by the nitrogen 14. So the decay that we were observing could be given by just something like 0.03% inhomogeneities in the hyperfine itself. This is very, very small, so that if you look at the NV Ramsey of large ensemble, you don't expect to see this effect because for the electronic spin, these 2 megahertz correspond to a small magnetic field. And so other inhomogeneities, indeed, in the magnetic field and the spin but noise typically overwhelm this decay. But for the nuclear spin, this hyperfine is very large, and it becomes indeed one of the main sources of decay. So we decided to sort of explore this effect, and we sort of started looking at a new experiment to probe this effect. This is indeed just a sort of like a slightly different way of performing spin echo, which has been used typically to map out like the spin echo peak itself. However, what we observed was something indeed weird. So if the hyperfine inhomogeneity was the only issue, and if I were to do a so-called single quantum echo, so sort of flip the electronic spin state from the 0 to, let's say, the +1 or the -1 state, what I would expect is that this would not really help, because during some time I have 0 hyperfine, and so 0 inhomogeneities in the hyperfine, and then in the rest of the time I do have some hyperfine, and so also some inhomogeneity. However, what we saw was that actually the echo was indeed helping, and it was helping in such a way that we had an optimal time of the pulse, pi pulse location. And this was at about 20% of the total time. And so we had to somehow revisit our model. And so we went back and wrote down the full Hamiltonian for the system, for the electronic spin, the nuclear spin, and their coupling. In particular, because the nuclear spin is a spin 1, we also have a quadrupolar interaction. Because we're doing a Ramsey on the N14, if we also have inhomogeneities in the quadrupolar, we expect that also these inhomogeneities will induce decay in a similar way that inhomogeneities in the hyperfine will induce decay. If the NV is in the 0 state, the dephasing is only due to the quadrupolar interaction, while if the NV is in the ±1, the dephasing is due to both the quadrupolar and the hyperfine interaction. So the idea that we had was to combine evolution in the 0 and plus and minus 1 state in such a way that the two contributions from 0 and plus and minus 1 cancel out. If this is 0, we can select a time, which indeed set this to 0, and this is indeed the optimal pi poles position that we have. So now we can understand in this way. What we are doing is to matching how much inhomogeneities we have in the quadrupolar with how much inhomogeneities we have in the quadrupolar and the hyperfine. When the two match, then we have this recovery. And indeed, this recovery can be obtained for almost no matter what is the total time, all the curve overlap, as long as we sort of rescale the total time so that they are all on top of each other. So what we are able now is really to have very good coherence, even for quite a long time. And indeed, if we compare the decay that we have without this unbalanced echo and the coherence that we can have by just pulsing on the MV center at the optimal time, we can achieve an almost 20 times improvement in the nuclear spin coherence time. And what I want to to somehow highlight is that a priori this is unexpected, because the inhomogeneities in the quadrupole and the hyperfine come from different sources. The hyperfine is mostly given by the NV, if you want, density cloud, while the quadrupolar is just given by the electric field gradient. And so they're not a priori indeed connected one to the other. However, experimentally, we find that they are, and we can indeed sort of develop a model which explains why the two are connected. In particular, one of the causes of inhomogeneities, which give rise to these inhomogeneities, are temperature shift. What we can see is that both the hyperfine and the quadrupolar vary quite similarly with the temperature. So what we did was to increase the amount of time that we illuminate our diamond with the laser, and this, of course, increases the temperature. And as a function of the measured temperature, we can plot out what is the average shift in the hyperfine and in the quadrupolar. So these are now shifts and not inhomogeneity. I guess I use the same symbol. And what we see is that there is a precise slope, a precise ratio between the two slopes. We can indeed also formulate a theoretical model which connects the shift, both of them, even if indeed they're like quadrupole and hyperfine have different origin, they're both connected to a second order foreign effect. And in principle, then, we can use the same type of model for other spin defects and trying to optimize our sensor, either become very good temperature sensor, or maybe very good magnetometers when this cancellation becomes pretty good. Because it's a second order effect, it's not linear, like this dependence on temperature over all temperature ranges, but you have pretty large ranges where indeed you have a constant ratio between the shift in hyperfine and Q that you can indeed achieve a pretty good cancellation of the effect. And the interesting thing is that the cancellation is actually obtained by sort of controlling only the electronic spin, while the nuclear spin is left alone. You're just doing a Ramsey experiment. And so now you can really use the nuclear spin in principle to detect static magnetic field. Unfortunately, nuclear spin are relatively lousy magnetometers because they couple very weakly to the magnetic field. However, we are very good at detecting rotations because indeed the coupling of spins to rotation does not depend on the type of spin itself. This is why NMR, so nuclear magnetic resonance gyroscope, have been proposed for a long time, but they have many drawbacks. In particular, they're relatively bulky, and so that does not make them particularly good as a gyroscope, because typically you want to miniaturize your gyroscope. Instead, these need to be used as vapor cells. So using instead MV centers could be beneficial because you can have a very compact device based on the solid state diamond. In particular, what could be quite interesting is to create a MEMS gyroscope out of of the diamond itself, and then collocate a nuclear spin gyroscope by adding the relevant control so that you can use the nuclear spin to stabilize the MEMS gyroscope, which typically lose its calibration over just the arc of a few minutes. So this type of hybrid sensor could be, I think, particularly powerful. And indeed, being able to apply good control on the system would improve the robustness of the nuclear spin itself, in addition to, for example, using the electronic spin to detect other variation in magnetic fields and electric field. Okay, so what I presented to you today was a various way in which we can improve quantum sensor. Overall, quantum sensors, I think that they were already quite developed, and they're already providing also practical advantages, and they are a near-term technology. Some of the practical advantages, for example, that they can work at the nanoscale and in many different regimes. But of course, at some point, we might want also to explore achieving the Heisenberg limit, which is the type of quantum advantage similar to the exponential speed up for quantum computer. But even if we are not there yet, in the same way that we have NIST devices for quantum computing, even for quantum sensors, some small amount of entanglement or some small correlation between a small quantum register can make indeed some tasks possible which are not possible otherwise. And this I sort of illustrated with the frequency up conversion project, and also with the coherence protection, in which we're using the electronic spin to protect the nuclear spin. Central to this task is, of course, achieving good control on the system, because this can protect the sensor from decoherence and sort of distinguish noise from the signal that we want to measure in order to indeed be able to achieve good signal-to-noise ratio. But also quantum control can also deliver new regime of applicability. So we can be able to detect vectorial information of the field to be sensed. We can improve the breadth of the range of frequency that we can sense. And all of this is indeed possible by developing novel control techniques. So before concluding, I want to sort of acknowledge the people that have worked on a lot of this project. So Scott was the student who really pushed the sensitivity for a relatively simple rabbit protocol, but he really made possible to achieve picotless sensitivity, which is the current record for this gigahertz frequency. Guoxin has been instrumental in many of the work that I presented. In particular, he's the master of everything which is Floquet control. And Yishang instead worked on the nuclear spin and SIL work. In particular, we are now also collaborating with Professor Julie, still at MIT, who is providing a lot of good ideas on how to model the ambient center system and how to model its physical properties. Of course, this picture was taken during COVID, but we are now back to be able to indeed meet in person. And so you can see some of the faces, but in the meanwhile, some people also graduated. And so we don't have a picture with all the authors. Okay, so I'll leave up my conclusion, and I will be happy to take any questions.
Thank you, Paula, sharing the great work with us. Now we have some time for question and answer session. Maybe I think we can start with the two panelists. Dr. O and Lee, if you have any question, you can ask Professor Capellaro.
Oh, can I ask a question? Yes, thanks for the nice talk. This is really amazing. I have two questions. One is one kind of a general question is about magnetic field sensitivity of the MV. So far, you have shown the best sensitivity is about like picotesla level, but there are a lot of people trying to reach like a femtotesla for the image application. So can you comment how can people realize that kind of sensitivity or something like that? That is one question. And another question is like, regarding your unbalanced echo experiment, so you showed like me 20 times of the T2 or T2 star enhancement of your nuclear. Then can you comment me how much T2 or T2 star of MV when you use those kinds of nuclears as a kind of quantum memory, something like that?
Okay. So this was like the plot that I showed, which is one way of plotting recent result in terms of magnetic field sensitivity versus magnetic field frequency. And indeed, we're sort of like going down to this level of sensitivity. And these are typically obtained through ensembles. So I think that to sort of push it even further, first of all, well, both this work and this work, which was in Rabi, this one was indeed done just by DC measurements, and this one is with Rabi, which are not the most sensitive and robust method for sensing. They're slightly easier to implement in an ensemble because you don't need too much like control robustness. But I think that one way to sort of improve would be to sort of, if what you want to measure is indeed in the AC sensing, then you might be able to push it even further by using these dynamical decoupling sequences. What sort of, just to tell you, I mean, you can see that this result is much, much lower. That's why I'm highlighting, because it's so much lower than all the previous results. So what went into doing this, and totally not my work, I was just advising the student, but this was, the work was actually performed at Lincoln Lab at MIT, where we're working very hard in really optimizing all the technical detail of the magnetometer. So light excitation, light collection, microwave delivery, the diamond itself, and so on and so forth. I think that probably could do even better. So like it's already amazing, but you need, and the ingredients are sort of always the same. You need even better diamonds, so with more homogeneity is probably slightly denser than they had here, but while preserving the coherence time. You need even better illumination. So we will use the side, the notch illumination, which is like a way of really using a lot of the MV center in your diamond chip. But you can probably still achieve a larger number of excited MV. But we're using the, again, a light pipe, light collection, so again, which somehow optimize how much light is extracted, but maybe there are other ways of even improving that, cavities and so on and so forth. So I think that all the technical detail should be improved. The largest improvement here was just the fact that they had many more MVs used in the experiment, because they were using this way of illuminating the spin and the diamond, and they were using low magnetic field so that all the four orientation could be used. So that's sort of like the lowest hanging fruit, is to really have as many MV as you can. That gives you, for ensemble detection, the shortcut to getting a good result. And then to push even forward, I think is, again, control in order to improve the coherence time. For the second question, I think that it was about, okay, let me just skip to that one, if I can find it. It was about the coherence time of the unbalanced echo. So that one was indeed like for the nuclear spin that we achieved this result. As I said, for the electronic spin, you would not really have much. So you could think of doing the opposite. So measure the T2 star of the electronic spin while doing an unbalanced echo on the nuclear spin, and that would cancel out potentially the hyperfine, and you should maybe match it with the inhomogeneities in the zero field splitting. But the hyperfine is much, much smaller than the zero field splitting, so I don't think that in practice it would really work. So you can improve the nuclear spin coherence with this method, but not really the electronic spin. So that's of course a limitation of these schemes. but at the same time, we were trying to indeed improve the nuclear spin, so that was our goal.
Yeah, thank you.
Thank you, Paola, for very broad range of interesting ideas and very nice results. I also have two kind of technical questions. So my first question is that my intuition tells me that if you do the magnetometry using the Rabi method, then I feel like you're trying to do like a spin lock onto the MV, and that kind of would hinder hinder your MV to actually actively sense the external field. So like if you actually drive it too hard, then you're actually locking even harder, so that I feel like your MV will not sense the external field enough. So in terms of the sensitivity wise, I guess I am quite surprised to see that result, that the sensitivity by Rabi is actually...
I think, yeah, so, okay, maybe you will consider this cheating. So we are trying to sense, like we are performing a Rabi experiment, and we are trying to sense, again, a transverse field rotating at the resonance frequency of the MV.
I see, so you're matching the frequency.
Yeah. Yeah, so basically, yeah, so you have like your main Rabi, and then you're saying, okay, now I have an additional field at the same frequency. You can have some a nearby frequency, so that basically still somehow driving.
Then what if you don't have information about the frequency of the external AC field that you want to sense?
Then what you have to do is start to fill up this void here by using this addition. But of course, like for this frequency mixing, you pay a penalty because it's a second order effect. So you can go beyond rotating wave approximation, etc., by having very large bias field, but you will still pay a little bit. So then what you're saying is totally correct. I mean, like you will pay some penalty in sensitivity, and then it's a matter, okay, if you can fill up points here, but you can in no other way, then it's worthwhile, I think, even if you pay a little bit sensitivity. But yeah, the best sensitivity you will find just for the, let's say, 2.87 gigahertz of your MV or nearby and or other places. Yeah.
I see. And my next question is that so you show that you can extend the nitrogen-14 nuclear spin coherence time by realizing that there's an inhomogeneity in a quadrature. The quadratic effect, but alongside that hypothesis, could you also confirm that using the nitrogen-15 to see that the enhancement is less than the nitrogen-14 case, because nitrogen-15 doesn't have a quadratic cube?
So yeah, so so for the nitrogen-15. It should not work at all because you don't have like the quadrupolar. So basically you will have a period during which you don't have any shift, and then you will have a period during which you have some shift. Indeed, these schemes work for quadrupolar nuclei. But there are actually quite a few nuclei with quadrupolar. So if you are thinking of having some other defect, that will also work. Like for nuclear like for N15, you could try to just use the simple echo on the nuclear spin itself. But of course, that's problematic for compatibility with other sensing schemes, and you would like to avoid a lot of pulses on the nuclear spin itself because they're slow and so on and so forth. So this works quite nice for this type of quadrupolar spin.
Amazing. Thank you.
I think we have about 2 minutes. Is there any question from the audience? We can take one. Okay, there's no question. So let me ask a simple question from the outsider perspective of the field. So Paula, in your chart, right, there was a empty space around 10 megahertz to 100 megahertz. So can you comment on the reason why there is completely empty? Is it because there's no, like the protocols, right, dynamic decoupling and Ramsey, these things, Rabi, they're not gonna work at all. There's no like protocol working in that frequency regime. Is that why?
Yeah, so like, as I say, Ramsey basically can detect a static of very low frequency field. Rabi, like to be sensitive, you need to make it a field which is at the resonance frequency on DNB. Now, of course, you could use a relatively large magnetic field, and so that the Rabi frequency gets shifted down, for example, and use Rabi. But especially if you want to achieve this good sensitivity, you want ensembles, and then having very homogeneous magnetic field with ensemble becomes difficult. So it's probably not impossible, but it becomes quite hard to, for example, push the Rabi down here. Okay, and dynamical decoupling, the limitation is that you're doing these pi pulses and you want to match the interspacing between the pulses with the period, if you want, so the inverse frequency of the field that you want to sense. And again, yes, maybe if you have a super good amplifier, you can reach a gigahertz driving, which will make like a few nanosecond pi pulses. Then you can put the pi pulses very, very close to each other. But again, with ensemble, it becomes difficult to have so much power. And so like typically the pulse spacing is on the order of microseconds. And that limits what is the largest field that you can sense here. With spin locking is the same. It's how strong you can drive your system. And so like it's not, I mean, you should not take this window as this is physically impossible. It's just like, again, what is practically possible with at the same time preserving the good performance that we would like to achieve. And so in order to do that, I think that indeed trying some more different protocol as this frequency mixing might be like a viable option.
Thank you for your answer. Now I think time is up, so we can move on to the next session. Let's thank speaker Professor Paola Capellaro again. Thank you, Paola.
Thank you.
들어와 계시나요?
Yeah, we're waiting for the next speaker a little bit. It's gonna be just a few minutes of delay. So meanwhile, I can have some advertisement of today's afternoon event. So in afternoon event, it's starting from 2 p.m. Korean Standard Time. And we have 4 speakers. And this time, all these 4 speakers are working on experiments. And as you have seen just now, Professor Capellaro was also one of the experimentalists we invited this time. So there were 5 experimentalists. And we, in fact, tried to make some balance between different areas of the quantum information science. So even within the experiment, of course, we made a good balance between theory and implementation. So, right. So within the experiment, we try to make some balance. Of course, we have only limited 5 seats. So we assigned, so there are like basically 3 subfields in the experiment, right? A lot of you already know that quantum computing is, of course, big thing. Everyone knows about quantum computing. And there's a quantum communication, right? Quantum communication, there's a communication, you have a, like sending quantum information over a long distance, and then actually that allows you to do things that classical communication is not possible. That's what we're, heading to. And the last one was a quantum sensing, using a quantum object and getting sensitivity that wasn't available with the classical systems. And Paola Capellaro, professor, just showed that such a system, how it can be implemented. And I think that sensor community is moving to the regime where you actually take advantage of entanglement and get better sensitivity, which is very difficult and challenging, but the community is moving forward. So for the afternoon, we have prepared one speaker working on the rare earth ions, which is one of the really promising quantum memory platforms out there. And also, since it has a great interface with photon, so this, all of these, quantum memories used for quantum repeater, they have this, it's supposed to have an interface with the photon. So the way it works is that it has a spin qubit, so it can work as a local quantum memory, but it can be entangled with the photon emitted from these emitters. And these rare earth ions, is one of the very promising platforms, and we invited the speaker who made a major contribution to this field. And we'll see how this rare earth ion field is moving forward with integration with another technology called integrated photonics, or nanophotonics. So it can enhance its existing functionality. That's our first talk of the afternoon. And the second talk will be about, in fact, it's the same system, diamond and V centers, but with different direction. So our speaker will speak about, he had made a major contribution in controlling the diamond and V center to an extreme, in a way that, in diamond, right, when we say diamond and V center, we are usually talking about, first thing, the simplest thing we talk about is electron spin. Diamond and V center is something like an artificial atom, so of course it has an electron has a spin. But in fact, diamonds can be engineered to have a lot of nuclear spins nearby, right? So these nuclear spins, in fact, is working as a really good quantum memory. So if you listen to the previous talk, there was a comment that these nuclear spins are not very good sensors in a sense that not very sensitive to magnetic field, right? Because its magnetic dipole moment is small, but the exact same fact, right? It makes it a really good quantum memory. So it's a quantum information science experiment research. It's all about finding these, advantage of the system and taking it, using it. So our speaker will talk about how NV center can be combined with the nearby nuclear spins, and then how it can be used for building a small-scale quantum computer. And then also, NV center is also a good platform for building a quantum communication system, the quantum repeater, because NV center also has an interface between electron spin and the flying photon. So it was one of the very promising platforms for quantum communication as well. So it's the NV center it's kind of its usage is most wide among known platforms, because as you just heard, right, it has its usage for sensors, right? We just saw the talk, and it has its usage for a small-scale quantum computer, but also it's one of the most promising platforms for making quantum repeaters. And the third one, we invited the speaker who's working on ion-trapped quantum computer. As many of people in the field would know, ion trap is probably one of the it's probably almost as popular as a superconducting qubit quantum computing system. It has a lot of investments going in, and there is a famous startups. There is a startup which already did IPO, right? The IonQ. So ion trap has a lot of advantages. So it's really hard to compare with superconducting qubits like apples and oranges. And even within ion trap community, there are different studies, right? Of course, there are some people use this ion, some people use another ion. And our speaker we invited today, actually, he pioneered the unique field that these traditional ion traps. People use these Paul traps and there are existing traps, right? But however, our speaker, he really pioneered the new types of trap by taking advantage of integrated photonics. So having this photonic circuit on your chip, and you can design a lot of photonic components, and you can manipulate the light, not with the traditional free space components. You can actually start manipulating these lights with printed photonic circuit. So that's kind of emerging trends for the ion traps, and we will have a chance to see the talk directly from the person who pioneered this field. And the last speaker is from the company called PaiQuantum. In fact, I used to work in PaiQuantum, so I had a chance to invite the speaker. So PaiQuantum is likely at the moment, it's the largest photonic quantum computing company out there, located in Palo Alto, the heart of the Silicon Valley. And these people are working on photonic quantum computers. So the qubit is actually a very unique approach. So if you're used to these matter qubits, right, something like superconducting qubit, ion traps, Rydberg atoms, and V centers, was it silicon quantum dot? All these things are matter qubits, and they are kind of more compatible with circuit-based quantum computing in general. So it's used for that or adiabatic quantum computing. However, the photonic quantum computing, in fact, is historically had a big difficulty in implementing a simple gate, because it's linearity. Yeah, it doesn't have non-linearity. So people, theoretical physicists have been trying to overcome this issue for a very, very long time. And then, after all, in a series of innovations, really it's a series of innovations over the last two decades. And then people found a way to build a practical photonic quantum computer. So we'll have a chance to, listen to the essence of the PaiQuantum's work. So we had so it turned out we had an issue with the order of the speakers, because who was originally scheduled had a little trouble, so we need to switch. So we decided that the first afternoon speaker, who is a Professor Tian Zhong from the University of Chicago, will talk about rare earth ion work. So let's wait a little bit while we prepare for the presentation. Okay, hello everyone. So as I mentioned, we have swapped the talk. What was originally scheduled with the first talk of the afternoon. So let me introduce Professor Tian Zhong. Professor Tian Zhong is an assistant professor of molecular engineering at the University of Chicago. He got PhD from MIT in 2013, and afterwards he worked as a postdoc at Caltech. So while he was working at Caltech, Professor Zhong has pioneered this field of the one I mentioned, the rare earth quantum nanophotonics. And this is one of the most promising platforms for quantum communications because it has exceptional coherence properties. Also, in addition to that, he has expertise in a broad range of quantum optics, such as nonlinear quantum optics and quantum key distribution, in addition to rare earth ions. Please welcome Professor Zhong with a warm applause. Welcome.
Thank you very much. I hope the mic works. So, first of all, I'd like to give sincere thanks for the organizer and Dr. Song and Dr. Bu for the kind invitation for this wonderful events. And it has been a distinct honor to be here and give the presentation on this very exciting workshop, a colloquium. So the goal of my talk today is to give you an overview of in this nascent but rapidly developing field of rare earth quantum technologies, which has been already introduced by Professor Song. And meanwhile, I would also like to give sharing some of the recent development in this field, as well as in my own group towards the next generation rare earth quantum technologies. So let me begin by saying that in this wonderful events, as just advertised by the Professor Song, that today, in the field of quantum information science and engineering, there's a multitude of physical platforms, and most of them are represented in this workshop. So, for example, the ion traps, solid-state spin systems, which I'm working on, and another speaker team also working on, and of course, photons remains one of the most important degrees of freedom. Actually, the photons is essential for interconnecting the different physical platforms together. So we believe that one of the next frontiers in quantum information science and engineering lies in the quantum interconnections. So we believe that quantum interconnections means at least two aspects. One aspect is the interconnections between physical qubits of the different or disparate physical realizations. For example, can we convert a quantum signal from the microwave domain in superconducting microwave circuits to optical photons? And this essentially realizes the quantum transductions, and we can establish transductions between every pairs of these physical platforms. The second aspect of quantum interconnect is really interconnect qubits that separate by large geographic distances. And this underlines the quantum internet or quantum networks. So most of these domains are of tremendous interest to our research. And since I'm from Chicago, I would like to share some of, out of a lot of interesting activities. One of the domains that we're heavily invested in is in quantum interconnect. And to highlight one of the activities that happening in Chicagoland, actually over the years we've been building a fiber-based optical quantum network testbeds over the Chicago metropolitan areas. So as of early this year, and this quantum network has expanded to 120 kilometers of fiber distance. And this fiber links has been operational fully and running quantum key distributions and sending secure keys almost continuously 24/7. And this network covers 4 quantum repeater nodes. And of course, it's hubbed at University of Chicago and our School of Molecular Engineering, and then includes, which links to other major national labs in the United States. These are Fermi labs and Argonne National Labs. And also, we sent out a fiber towards Chicago downtown. So this altogether forms a 4-node quantum network. And the guiding vision for this kind of network is actually you're going to allow different physical platforms, such as spin qubits, superconducting qubits, trap ions, or photonic qubits to be plug and play into these networks seamlessly. Of course, in my own work, we focus on spin qubit, degrees of freedom. And in particular, we're working on rare earth ions as one of the very promising, relatively new type of optically active spin qubits. So rare earth ions refers to the lanthanide series, and the lanthanide atoms runs from atoms lanthanum to the lutetium, and all of this lanthanide series shares a very exciting, very interesting common orbital configurations, which has a xenon core at the center and which is surrounded by partially filled 4f electron shells, indicated by this red ring. And this 4f shells is further enclosed by 5s, 5p, sometimes 6s outer shells. These outer shells are completely filled, and they are responsible for chemical bonding with the external ligands in the materials. However, this outer shells also effectively behaves as a Faraday cage, and that shows the 4f electrons from interacting with the noisy environments. As a result, the intra-shell 4f transitions has exhibited very long coherence times, both in optical degrees of freedom and the spin degrees of freedom. As compared to other leading optically active spin qubits systems, such as NV centers, we just heard from the previous talk, and other the newly developed silicon carbides and other systems, we can see that the rare earth ions really thrive in terms of very long coherence times or very narrow optical linewidths due to these protections of the 4f states. So given this excellent, outstanding coherence properties, one of the natural applications, of course, is towards the long-distance quantum network. There has been a lot of tantalizing theoretical proposals to build a quantum repeater network based on the single rare earth emitters. And essentially, this is following the footsteps of the pioneering experiments done in Delft using NV centers in diamonds. In this case, we would like to realize the teleconversions of that experiment, so enable long-distance quantum network. So the basic requirements of this new proposal comes down to the four things. First of all, we would like to have a optical active spins with telecom transitions, and this is rather quickly fulfilled by one of these rare earth ions, erbium, the famous erbium transition, which is in telecom C-band. Now, this qubit should have a spin coherence times that is at least millisecond, and such that it can sustain or can store the quantum states over the photon transit times during the between the neighboring repeater nodes. For a typical quantum network, and which spans a inter-repeater distance over a metropolitan distance, which is 50 or 100 kilometers, this type of coherence time amounts to about milliseconds. So that's why millisecond coherence time is kind of the lower bound that we have to fulfill in order to enable this kind of repeater schemes. The next requirement is the indistinguishable photons. Of course, this means the quantum emitters needs to have a radiatively limited coherence times, optical lifetimes. And for rare earth ions, unfortunately, both of these long millisecond coherence and the indistinguishable photon emissions hasn't been really demonstrated, and there has been roadblocks, which we'll discuss later on in this talk. And we're making a very concerted efforts towards overcoming these two shortcomings in order to realize the full potential of rare earth qubits. And the last of our list, the other condition is to have at least a multi-qubits in each quantum repeater nodes, so we can perform entanglement distillation, so on and so forth. And this, we think, can be readily realized by having multiple rare earth emitters that couple to a single optical cavities. Or, alternatively, we can explore the hyperfine transitions, hyperfine interactions between the electron spins in the rare earth ions with paired with the nuclear spins. So that forms a multi-qubit as well. Now, I assume that the audience is not completely familiar with this relatively new color center system. So I would like to start with a very basic spectroscopy of rare earth ions. I start with the spin Hamiltonian. Term by term, we begin with a spin-orbit couplings, and in rare earth ions, because it's heavy elements, there's a tremendously large spin-orbit couplings, and the speedings can be on the order of the optical frequencies. Essentially, the lowest ground levels of erbium is of the spin-orbit levels give rise to this 1.5 telecom transitions. The next one, when you embed these ions in your solid-state host, there's a crystal field interactions, and that cause further speedings of the spin-orbit levels. And the typical speedings of the crystal field levels is on the order of terahertz. So equivalently, that's the temperature about 30 to 50 kelvins. That means that's why rare earth ions typically we have to operate at cryogenic temperatures. Otherwise, in order to unpopulate some of this that high-lying crystal field levels. And then the remaining degeneracies in the lowest crystal field levels can be lifted by applying an external magnetic field. So this makes the ground state essentially behave like an electron spin half. And there's a Zeeman speedings with a very large magnetic moment. So G factor can be as large as 20 in these rare earth systems. And next one, if you choose a particular isotopes of rare earth ions, there could be also nuclear spins, and therefore there's multitudes of hyperfine interactions that give rise to many, many levels, typically. So this kind of combination of electron spin and nuclear spins is really powerful. It provides a rich selection of energy levels for qubit encoding. And that combined with the narrow optical line width makes all these qubit levels optically addressable. So that's the very distinct features of the rare earth systems. Now, having said all these all great things about rare earth, let me tell you also the caveat of working with the rare earth ions. One of the biggest challenge working with rare earth ions is that all of these rare earths have actually extremely low oscillator strengths associated with their optical transitions. Again, this is due to the enclosure of the 4F states, which makes it almost not interacting with light. And this is reflected in the second column by the extremely small oscillator strengths of the rare earth ions. And this is typically few orders of magnitude lower than the atomic system, such as rubidium, even comparatively very low to MV centers, color centers in diamond. So this requires us to essentially couple the rare earth ions to optical cavities of a very small volumes in order to enhance these light matter interactions. So typically for cavity QED systems where we operate in the so-called bad cavity region, where the coupling strength is much, much stronger than the atomic dissipation rates, but lower than the cavity decay rates. In this region, the key figure of merit is the cooperativity, which is scaled as the Q, the quality factor of the cavity versus the mole volume of the cavities. So for rare earth ions, in order to achieve reasonably good coopetitivities, we require a Q over V of the cavity to be on the order of a few thousands. As compared to state-of-art silicon photonics technologies, we can make photonic crystal cavities with very small mode volumes and very high Qs. So we think these kind of requirements can be easily fulfilled. So that's the genesis of rare earth and nanophotonics, why we think it is actually possible to do this. Then over the past few years, there has been very exciting pioneering experiments that basically demonstrate this is actually working. So in the next couple of slides, I'd like to show you some of the milestones that has been achieved over the past few years. So first of all, this group from the group that I've been working with from Caltech, led by Andre Ferrand, is arguably the first who successfully coupled a ensemble of rare earth ions to a nanophotonic crystal cavities. In these devices, we essentially use a focused ion beam to sculpt a structure that looks like a Toblerone chocolate bar on the surface of a rare earth doped crystals. And using these photonic crystals, we strongly enhance the absorptions of ensemble for neodymium ions in this case, and make a miniaturized and nanoscale quantum memories based on atomic frequency comb protocols. So the figure is showing essentially it looks like a frequency comb structure, but in the atomic domain. So these are not optical combs, but atomic combs in this nano device. And also because of the strongly enhanced light-beam interactions, we can use the very high AC Stark effects by optically controlling the optical line-widths of each individual emitters. By doing that, we can shape, dynamically shape the structure of these combs by using external lasers. Doing so leading to the first demonstration of so-called optically controlled on-demand quantum memories. We can control when to retrieve a single photon that is stored in this device. Subsequently, and the same technology has been applied to address down to the single rare earth ions. And this is really the exciting part, where we actually are building a rare earth qubits. The first work is done by the same group and who are at Caltech, who addresses the single ytterbium ions 177s. So the reason that ytterbium 177 is interesting because the ground states has an electron spin 1/2 and a nucleus spin 1/2. So it forms a singlet triplet states in the ground state for the qubit encoding. And the spin transitions between these singlet triplet states is essentially a clock transition, which on first order is immune to all the electromagnetic noise in the materials. So this leads to a demonstration of a rather good coherence time, the spin coherence time T2 of 44 microseconds, and then after applying dynamic coupling, they were able to extend that to 30 milliseconds. The optical line width on a similar story is rather narrow, in this case barely about 1 megahertz. Another line of work, and this is a separate platform developed by Jeff Thompson from Princeton University. What they are doing is fabricating silicon photonic crystal cavities on top of rare earth doped crystals, in this case, the erbium doped YSO crystals. In this case, they were able to observe, they were able to use the evanescence fields in the silicon waveguide to couple to those ions that are near the surface of their crystals. In that case, they were able to achieve a very long spin lifetimes, nearly 1 minute. However, for some reason, the spin coherence times hasn't been very good, and it's typically on order of microseconds. Correspondingly, the optical line width appears to be a little bit broader than the other work, so which is on the order of 10 megahertz. So these three sort of pioneering experiments really highlights the viability of rare earth quantum technologies and opens up very exciting prospect for these technologies for a variety of quantum interconnect applications. At the same time, it also identifies several areas that we do need do more work on. One of the issues, one of the pressing challenges, as I see it, is there's really this gap. So what I see the next pressing challenge is really this gap between the coherence times, that the coherence properties observed out of a single rare earth qubits, then the ensemble averaged coherence times that usually measured out of a pristine bulk crystals. And this opens up some important theoretical questions, fundamental science questions, and why, what is the causing the decoherence of the rare earth qubits? And more importantly, this could lead to the discovery of new materials, new techniques, and new technologies in order to close this coherence gap between the single rare earth qubits and their ensemble-based memory performance. And if we can do that, then I think we'll really truly realize the full potential of the rare earth quantum technologies. So in the remainder of this talk, I'd like to share with you three interesting developments in this field. And actually, all of this our group also have a contribution to. First, let me start with a material platform, a technology platform for the next generation rare earth quantum technologies. As you might have seen, almost up to now, almost all the the leading platforms of rare earth technology has been exclusively based on these macroscopic bulk crystals. Right, so this is a very old technology, dated back to six or 7 decades ago, starting with the laser optics industry. Now, while it has a very good, these bulk crystals are nearly perfect. They have a very high purities and the crystalline qualities. They lack the essential prospects for scalability for future quantum technologies, in our opinion. And we believe that the really enabling or really scalable platforms of rare earths will be the one that has based on submicron thick membranes or thin films that we can actually synthesize over the wafer scales. So one of my the thrust of my research group is to build a new foundation for the next generation quantum technologies by synthesizing the rare doped thin film crystals over the wafer scales. So the example shown here is our first effort, which is to demonstrate a rare earth doped yttrium oxide single crystal epitaxially grown thin films over a standard industry standard 3-inch silicon wafers. And by doing so, we hope to achieve a scalable fabrication of rare earth quantum devices, as well as monolithic integration of the rare earth materials with other technologies such as the superconducting qubits, superconducting circuits, as well as nanophotonic devices. And as a first attempt, we were able to show a bulk-like luminescent properties of erbium ions out of these entirely new, different thin film platforms. Now, the first model material we choose to push this field forward is yttrium oxide. So yttrium oxide is a lattice, has a qubit crystal structures, and in this lattice there are 2 sites of different point group symmetries, C2 and the C3I group point group symmetries. In those 2 point groups, the yttrium atoms can be substituted by a rare earth atoms. When we put erbium in this yttrium oxide, we actually reported extremely narrow optical line width down to 100 Hertz and extremely long electron spin coherence times up to 10 milliseconds. Now, the good part about this material is it has been very popular, very common, and it can be synthesized using a variety of different techniques into different topologies, such as nanocrystals, polycrystal ceramics, and epitaxial thin films. Of course, we're interested in the epitaxial thin films, and that's our focus. So we do that with molecular beam epitaxies. So due to a fortunate lattice match between these yttrium oxide crystals and the silicon substrate, we're able to grow yttrium oxide thin films on silicon with a thin film thickness anywhere from a few nanometers to up to microns. And the rare earth ions are incorporated in this thin film as we grow it from the bottom up. And with a very high precision in controlling their doping concentration down to parts per billion level. And also, we're able to control the position of these ions due to the delta doping techniques. So by doing so, we control the proximity of these rare earth ions to the defective material interface in order to preserve its coherence times. By combining of these different techniques, we're able to, on first order, demonstrate a erbium dopants ensembles which has a narrow inhomogeneous line width, as narrow as their bulk counterpart. So this is very promising. The next, then we have these wafer materials. What we do is we try to design a wafer scale qubit device, and we dice up these wafers into smaller chips. Those are qubit chips. And on top of these chips, we fabricate superconducting microwave circuits on top of the thin films in order to coherently drive the spins, as well as performing electron spin resonance spectrometries on the spin ensembles. And then we optically address these rare earth ions by bringing a vertical cavity. This cavity is formed by 2 high reflective DBR mirrors, one below the thin film, and the other one is coated on the tip of the fiber, which is hovering above these thin films, and then in order to collect photoluminescence emissions back into the fiber. So we operate these qubits in the ground state. The speeding is about 5 GHz, so it's completely compatible with the superconducting microwave technologies. And optically, of course, we're addressing it while erbium's the telecom transitions. So more about the microwave part. We fabricate niobium superconducting circuits on top of the thin film, and actually we can make arrays of these devices over the wafer scales. And we optimize the impedance of these microwave circuits such that it enhances the single spin couplings. In this case, we can typically achieve up to about kilohertz single spin couplings. And this wafer then dice up into multiple chiplets, and each one represents a erbium qubit source. So the coherent coupling between the microwave circuits and erbium spin ensembles, and that leads to dispersive shift signals in the cavity, the microwave cavity. And in this figure, we're measuring this dispersive signal as we change or sweep the magnetic field orientations in the device plane. So as we do so, we observe the various patterns, and these dispersive patterns represents different orientations of the erbium spins within the single crystal lattice. And the clear observation of these patterns actually provides the first direct proof this is a single crystal. It's not amorphous or polycrystalline materials, which is really important. And secondly, in order to operate or address our erbium qubits, we choose the direction of the magnetic field and magnetic strength such that these qubits have a lowest G factors. So the lower G factor means it's a less sensitivity to magnetic noise. In both of the cases, we park our field at about 45 degrees, with respect to some arbitrary reference angles. And in this case, we are addressing the C2 site erbium with a G factor of 3.4. And similarly for C3I site, the G factor is also about 3.2. So with such a magnetic configuration, then we measure the spin coherence time and spin lifetime. For both these qubits, the spin lifetime is on the order of seconds, and the spin coherence times, which very excitingly, we achieved both millisecond coherence of these platforms. So this is already fulfilling one of the checklists, our quantum repeater requirements. And this millisecond coherence time is achieved after dynamic decouplings. And most importantly, we think that the remaining 1 millisecond spin coherence time is actually limited by this residual erbium dipolar interactions, because these samples still contains relatively high concentrations of erbiums. So if we were able to lower this concentration by 1,000-folds, for example, to to 10 ppb instead of ppm, then we'll extrapolate a spin coherence time up to seconds, which will be really exciting. I think that's something that currently is a work in progress. Well, you may say that we're measuring this very good coherence out of one dice of the chip of the wafer. So what about the rest of the wafers? Well, actually, we performed the spin coherence times over many dies on the same wafer, and we find that these long spin coherence times are consistently observed throughout these wafers. So almost for all the dies we measured, it's a coherence times of more than milliseconds. And more importantly, we can extract the noise, magnetic noise background levels from the T2 measurement. And this gives rise to about 10 nanoteslas of magnetic noise, which is also consistent throughout our wafers. And this 10 nanotesla is actually the limit of the Each nuclear spin bath. So, which in other words, we prove that this material is extremely pure, and the noise, the dominating noise in these materials is really from the nuclear spins of the host crystals. Now, this is about the spin coherence. And next, we'll look at optical transitions. Again, this is more details about these optical cavities. which is a fiber-based Fabry-Perot cavities, it allows a rather efficient extraction or collection of the photoluminescence emission back into the fiber, with the efficiency can be up to 80%. Now, the volume of this cavity is not as small as the photonic crystal cavities. However, we're able to achieve a very small cavity length down to nearly 1 wavelength of light, 1 lambdas. Meanwhile, preserving a very high quality factor up to hundreds of thousands. And this kind of cavities offers then a Q over V ratio actually is fairly large, on the order of 100,000, which is essentially comparable to a state-of-the-art silicon nanophotonics. And with this high Q, we actually can measure extremely low loss of these thin films down to something like 1.8 dB per meter. So compared to silicon, this is a really, really good number. And this whole setup can be operating in a very stable fashion in the dilution refrigerator, and the cavity resonance actually can be in situ tuned by mounting the bottom mirror onto a piezo stage. So with these cavities, we're able to optically address a single erbions in the C2 site via very strong Purcell enhancement. And in a single cavity, you typically can address hundreds, sometimes it's about thousands of these individual erbion ions. Then next, we measure the optical line width of these emitters. This is done by a technique called transient spectrum hole burning. Well, I will not go into details about this technique, but essentially what we do is by tuning the cavity resonance in and out of these the emitters, we're able to change the optical lifetimes by tuning its Purcell enhancement. Then we build a evolution of the optical line width, emitter line width versus time, and to extract the optical spectrum diffusions. So without applying a magnetic field, so this is really operating these ions as a single emitters, then we do see a rather significant spectrum diffusions of these emitters up to a few megahertz. But now, as soon as we turn on some modest magnetic field in order to generate the spin degrees of freedom, we actually can completely quench this optical spectrum diffusions. We think that's because we're able to quench the paramagnetic spin impurities within these materials. However, the remaining line width of this emitter is still good on the order of just slightly below 2 megahertz, which is pretty good. However, it's still far away from the radiatively limited line width that are required by a quantum repeater architectures. So we think that is because for the C2I site erbion species, they lack the central inversion symmetry. In other words, the optical transitions of erbion in the C2 sites acquire a forced electric dipole moment. So that makes these ions susceptible to electric noise via the DC Stark effects. So in order to further cancel out or further mitigate this electric noise-induced broadenings on the optical transitions, then we turn our attention to the other symmetry site, which is the C3I site. Now, C3I site is the structure that is slightly distorted from the so-called S6 point group symmetries. In this point group, there's a central inversion symmetry. It means the erbion sits at the inversion center between every pair of oxygen atoms, which completely cancels out this electric dipole moment, which makes these ions immune to electric noise, and the only magnetic moment-induced transitions are allowed. Furthermore, for the C3I site erbion qubits, the excited state G factor is 0, which means now we have a spin and optical transitions are exposed to the same magnetic noise. The G factor, effective G factor, or G transduction coefficients is the same. Now we measure the spin line width, spin spectrum diffusions on the ground states, and that is upper limited by 3 kilohertz. So this implies that the optical transitions can, in principle, also as narrow as a kilohertz. So that pairs with the millisecond coherence. I think we really find the recipe to engineer a rare qubits with a simultaneous long optical coherence times and a long spin coherence times in the ground states. Now, the future prospect of these qubits is that we can consider now coupling these erbium C3I site qubits into a nanophotonic devices. And in this case, we're designing a so-called heterogeneous photonic crystal cavities where in sandwich this low index yttrium oxide material, thin films, between a high index silicon materials. So this effectively forms the so-called slot waveguides, which further confines the electromagnetic wave into those nanometer thick thin films. By doing so, we're able to, I mean, this is a simulation, at least by simulation, we're able to confirm that these photonic crystal cavities has a further reduction in the mode volume, which has reaching a astounding value of 4% of a cubic wavelengths. And that will give rise to another order magnitude enhancement in the coupling strengths, which we think it could be as high as the 10 megahertz. If we can do that, then we really can reach a very exciting uncharted territory in cavity QED, which is a single erbiums having cavity coupling cooperativity on the order of 100. If we can do that, of course, this work is still ongoing, and that really opens up a very exciting avenues for advanced quantum technologies. For example, with a cooperative of hundreds, we can think about single photon, single atom gates. We can think about non-demolition detection of single telecom photons, which is essential, as we heard from yesterday, Anthony's talk. It is essential for DI-QKDs, it's essential for quantum memories, because you will know when you are loading a photons into the memories device. And this will also lead to potential application of the two qubit gates between rare earth ions that coupled through exchanged virtual photons in the cavity, as well as, you know, in the long term, you can start dreaming of single photon nonlinearities, so on and so forth. Okay, so that wraps up my first story about erbium qubits. The next development is also about single rare earth qubits, but with a slight twist. So the intuition that we gained from study all these rare earth ions, individual rare earth ions in a oxide lattice holes is that the spectroscopy properties or coherence properties of these rare earth qubits is almost entirely determined by these local crystal field interactions. In other words, it's determined by how a single rare earth ions are correlated or coordinated with its nearest neighbor oxygen atoms. So in both C2 and the C3I side of yttrium oxide, and each erbium is coordinated with 6 oxygen atoms. And the only difference between these two qubits is the slightly different orientations and arrangements of the 6 oxygen atoms surrounding this these erbium ions. So this intuition then motivates us or inspires us to look at these so-called erbium oxygen complex systems, which consists of merely 7 atoms. And in principle, these 7 atoms, if you can arrange it properly, it should spectroscopically behave identical to the single erbium ions in a oxide lattice. But now we can take these complex systems and put it into arbitrary alternative host materials. One of the natural choice of this alternative host materials, of course, is silicon. Right? So everyone loves silicon. So we did a very simple experiments. We tried to co-implant erbium ions and oxygen ions into silicon, and with a ratio of 6:1 to mimic this erbium oxygen cage structures. And by annealing it at optimum temperatures and the timings, we hope to optically activate the appropriate arrangements of these complex structures. So here shows the off-resonance above bandgap excitation photoluminescence of this erbium in silicon, and here we can see the multitudes of transitions in the telecom C-band And actually, most of these transitions are well identified with a known symmetry site of erbium in silicon. Especially interesting are the two. One is at 1535, one near 1539. Both of these transitions are identified with a low site symmetries, which corresponds to very similar to the erbium oxide lattice structures. So with silicon, of course, we can make nanophotonic devices, and this way we make long photonic waveguides. And in this case, even after implantation and annealing, we achieve a very low propagation loss, or relatively low propagation loss. And this means we can fabricate high Q photonic crystal devices, which indeed we measured Q up to 70,000 after all these implantations and annealings. Then with this waveguide, we performed on-resonance photoluminescence. Okay, so here shows the emission, photoluminescence emission spectrum as we vary the excitation laser wavelengths. Here clearly we can identify these two sites, symmetry sites I just talked about. Both of these sites shows a very strong zero phonon line emissions, one in near 1535, the other one near 1539. Actually, both of these transitions can be identified with a low symmetry. This is a monochronic symmetry. That is essentially identical to the symmetry groups of erbium oxide. And this is further corroborated by the very similar magnetic anisotropy of these spins. So you can see that their G tensors are essentially parallel to each other. One is erbium oxygen in silicon, the other one is erbium in yttrium oxide. So now, of course, we can also couple this into silicon photonic cavities. And in this case, because the strong confinement in the silicon waveguide and the fact that we'll position these ions fairly close to the center of the waveguide, we can achieve a very high Purcell enhancement with a Purcell factor up to 800. And also, the benefit of having silicon, which is a high index materials, enhances the luminescence rates, and that gives rise to a much stronger optical transition dipole moments compared to rare earths in other host, oxide host lattice. In this case, we're able to demonstrate a single erbium coupling strength over the 10 megahertz just by implanting into a silicon material. So, of course, this opens up a very interesting platforms. And now we have a alternative qubits, which is the erbium oxygen complex. And spectroscopically, this is behaving very much similar to a single erbium in the oxide lattice. But now, instead of oxide, we have these qubits inside the silicon. Okay, so that wraps up my second story. And both of these first two stories is about engineering single rare earth qubits. And in the last part, I think I have a couple more minutes, I will talk about a ensemble-based rare earth quantum memories. And we are rethinking some of ways that making these memories to work better in the quantum repeater context. So first, let me begin with a review of one of the long-established quantum repeater protocols, which is initially proposed by Christoph Simons back in 2007. In this repeater architecture, they consider a photon pair source, for example, realized by spontaneous parametric downward conversion, that generates a frequency non-degenerate photon pairs. One is coupled to optical fibers for long-distance transmission, and the other photon is sent immediately to optical quantum memories. And after some storage, these photons can be retrieved from memory to perform further BSM or entanglement swap operations. Now the large bandwidth of the photon pair source, typically SPDC, has a very large bandwidth. That paired with the multimode capability of the quantum memories, and in this case, in the initial proposal, they're already thinking about rare earth quantum memories, which offers this multimodal storage capability. This pairing really enables a significant speed up of the entanglement generation rates compared to the original DLCZ protocols for the quantum repeaters. However, the challenge of this architecture is that there is an inevitable interface, which tends to be very lossy. This lossy interface between the photon pair source and the memories. And in fact, after nearly 15 years, a full, relatively complete experimental demonstrations of this protocol has only been realized very recently. Last year, there's the 2 papers in Nature published back-to-back. In my opinion, they represent the first really a full implementation of these protocols. However, due to this light matter interface loss, which significantly limits the entanglement generation rates, and even without long fibers and the demonstrated E bits or entanglement bits rates is on the order of a kilohertz. So in these projects, what we're thinking is, can we rethink a different protocols that can eliminate this light matter interface? And I think one way to do so is to consider a new process that combines the photon creations and the storage as one process and in one optical cavities. So here shows the basic schematic of our idea. And now we consider a optical cavity that's strongly parametrically driven or parametrically pumped, which generates a 2 entangled, non-degenerate entangled photonic modes. One is the signal modes, one is the idle modes. Now we also consider the resonant frequency of the signal mode is on resonance with optical transitions of quantum memories. So this quantum memory consists of inhomogeneously broadened ensemble of atoms. Naturally, we're thinking about rare earth atoms. And the inhomogeneous line widths of these memories are, we let it comparable. It's not necessary to be exactly identical, but comparable to the cavity line width. So this kind of system can be modeled using equivalent circuits with the 3 inputs. 2 of these are vacuum modes in the optical degrees of freedom. The other one is the memory modes, which is in the ground states. Now, these 2 vacuum modes and then undergo a 2-mode squeezing interactions, which entangles them, then followed by a beam splitter interactions between one of the signal modes and the memory modes. The output of this 3-mode system is a tripartite entangled states between the 2 photonic degrees of freedom and 1 memory degrees of freedom. What is surprising and interesting is that even we discard one of the modes, for example, the signal mode, the remaining entanglement between the idle photons and the memory degrees of freedom is nearly intact. So this is really useful as a bipartite entanglement, which is the key ingredient for a quantum repeaters. Also, because all of the 3 modes are interacting they're created and interacting all within 1 cavities, and there's no interface. And because of that, this impedance matching condition is not relevant in this case. And in fact, the impedance matching conditions is not even optimum, as we see from the entanglement as a function of the drive and the optical line width and the coupling. There's a range of the system parameters that actually give rise to maximize the entanglement rates. Now, as an experimentalist, I think the most exciting part is I actually think that we can do experiment with all the existing technologies in the lab today. So here we consider a integrated device. It's an integrated device consists of silicon microring resonators that's on top of a erbium doped rare earth crystals as a substrate. And we use a spontaneous forward mixings in the silicon to generate non-degenerate photon pairs and signal and idle photons in the telecom band. And now we tune the resonance such that idle photons is now coupled to erbium optical transitions, and this is realized by the evanescent field coupling of the silicon waveguide to the substrates. And for erbium memories, we're considering, again, the atomic frequency cone protocols, which allows a storage time at least a microsecond. So during that 1 microsecond storage, the idle photon is already propagated outside the cavities into the fibers. In this case, there's an entanglement that generated between the idle photons and the memory degrees of freedom. Now, if you plug in all the numbers, actually, this system projects a e-bit rate up to 50 megabits per second. As provided, if we can engineer a quality factor of the silicon ring resonators up to 1 million. I think there are lots of experts in this audience and in the following talks. For silicon photonics, 1 million Q for ring resonator is really no problem. So another advantage of working with this system is actually quite robust. There's a reasonably large parameters range that we can tune different parameters in order to achieve the high rates. So without requiring strong couplings, without requiring extremely heroically high Qs, without requiring extremely narrow langways as well. So there's a quite relaxed set of conditions in order to achieve a entanglement generation rates that we think can be as large as tens of megahertz. All right, so I think I'm almost at the end. Just very, very quickly, we have some other projects that are happening, and I think in terms of the materials, I'll really spend a lot of time and thinking about how to create a scalable platform for build a really strong foundation for the next generation rare earth quantum devices. And we explored MBE, grown thin films, but beyond that, we also think about a hybrid growth approach where we start with MBE to define a template, which is highly single crystal, and then we overgrow with the CVD techniques. So this is in collaboration with Professor Philip Goldner from University of Paris. On the other aspects, we're also trying to engineer a quantum transducers based on magneto-optical nonlinearities of the spin ensembles of rare earth ions. Because actually, already seen that we're able to couple these rare earth ions simultaneously to the superconducting microwave circuits as well as optical cavities. By combining those will give rise to a bidirectional conversions between the microwave signals and the optical signals. And very lastly, this is I really can't help by mentioning this interesting collaboration with my colleague Professor Bernier at Chicago. So in this case, we're thinking about a hybrid quantum network architecture where we try to connect a single rubidium, this optically tweezer trapped atoms at the near photonic crystal cavities, and coupled to a single erbions. While these are very different species of atoms, almost like completely random, magically we find a matching optical transitions. So one of these high-lying rubidium transitions actually in the telecom C-band, and that matches almost exactly to the transition of erbium, which is really mind-boggling. You can take completely random two atoms in the periodic table and find a perfectly matched optical transitions. And we're going to capitalize on that and making a quantum network demonstrations between these two platforms. Okay, I think this is really my last slide. I would like to thank my group members who really make all this work possible, especially the thin film work is led by a senior graduate student, Shobi Gupta, and Dr. Zhong Huang, and assisted by Zhong and Chao Fan and the rest of the teams. Yeah, so with that, thank you for your attention.
Thank you, Professor Tianzhong, for the showing us great achievements happened in your lab. Since we switched the time, in fact, we cannot have a panelist, so I'll work as a panelist because I also kind of worked in this similar field, kind of cousin field. So I have a lot of common interest with Professor Zhong. So let me ask two quick questions that I was most curious about. So the picture you showed us, the most interesting one was that the one you are working right now, the silicon sandwiching the rare earth, the material, right? That one, I wonder how you ended up in that particular structure, because yeah, I actually probably missed the details of the fabrication process. That in my mind, it looks like if you can grow it on top of the silicon, right? You said that there is a lattice matching.
Yeah.
So easiest thing probably you can do is that you start with the SOI wafer and grow the material and then just etch and try to use that as the waveguide with the silicon covered with another material.
Right.
So I wonder why you are going all the way up to silicon, memory and silicon disenriched structures. That's first question. And the second question is, you mentioned in the beginning of the talk that we always have to think about this future perspective of entanglement distillation with the help of qubits nearby. So I want to hear some comments on what you think about, with your system, what you expect in the future for the entanglement distillation.
All right. Yeah, thanks for these two great questions. For the first question, I think, I don't know if it's possible to bring up that slides again. If not, that's fine. I can explain. So the reason we're thinking about this relatively complex structures where we have a silicon on oxide on silicon, and then of course there's another oxide below in the SOI, is that we can leverage this so-called dielectric discontinuities. Meaning if you polarize using the TM mode instead of TE mode, the electric field intensity actually spikes in the low index materials. So that gives rise to these further enhancements of the field inside the memory material. So actually that's the goal of that sandwich structure. So we actually intentionally want more field in the oxide and less field in the silicon. I think in terms of a fab, this is not crazily difficult, because if you start with SOI, we grow our thin films. Essentially, we can regrow another silicon on top and then etch through. So it's one additional step, but we think is manageable. Now, second question is regarding the entanglement distillation. Yeah, so this is obviously a kind of the holy grail of this field. And once we achieve the single qubits, and then the next stage is the 2 qubits and more qubits. So we think about two approaches to solve this problem. And the first one is thinking about using a cluster of rare earth ions that couple to the same cavities. And the interactions between this cluster of rare earth ions can be realized by their direct dipolar interactions. In the ground state, it was very strong. There's obviously this magnetic dipolar interactions. But even if you consider a very dilute sample, so the interdistance between these rare earth ions can be as large as hundreds of nanometers. In that case, the dipolar interactions decreases almost to nothing. But there's another degrees of freedom you can leverage is actually using these optical dipoles. So the physical picture is if you optically excite one rare earth ions, that excites a effective optical dipole. And that dipole can shift the resonance of the other rare earth ions. So essentially, this is optical dipole-dipole interactions. And it has been, the proof of principle experiment has been done on samples, and this has been shown to be working. So we think nevertheless, we think that's a viable approach. The second approach is, as I mentioned, we can leverage the, again, very similar to the MV center case, we can leverage the nuclear spin registers that nearby. Either nearby, or actually for many isotopes of rare earth ions, they already carry the nuclear spins by themselves. So we think that's another exciting avenue. For example, erbium, this isotope erbium-167 has electron spin 1/2 and nuclear spin 7/2. There's a hyperfine coupling is rather strong on the order of hundreds of megahertz. So that means you can first build the qubits, entangle qubits in the electron spin, and swap and store in the nuclear spin, and then do it again. It's essentially the demonstrations, very nice demonstrations done by Delft's groups last year. So I think with all these possibilities, we think this is a solvable problem.
Thank you for your answer. Yeah, I think I understood, and it sounds very promising. I'm excited too. about your field. And since we're a little bit late, so let's finish here. And let's thank again the speaker with an applause.
Thank you.
And let me give you an announcement. So we will keep our schedule. So we will resume our workshop, resuming from 2. And we'll have lunchtime until 2. So the location will be the building nearby. We'll go all together. There is a faculty club nearby, so we can go all together. And it's the same place if you went yesterday. So let's we will have a break until 2, and let's have lunch. Thank you. it. And then this one should work. Hello everyone, welcome back to the afternoon workshop. There's one announcement. Because we are missing one speaker, we decided to update the order of talks a little bit. So the first talk, right, originally supposed to be Professor Zhong, but he already did in the morning session. So what we decided to do is that the last order, originally the last order, PaiQuantum, Dr. Mihai Vidighin, he agreed to switch to the first talk of the afternoon. So, and then the rest of the two talks, ion traps and the diamond envy center, they are staying the same. So we're going to start with Dr. Mihai Vidighin. Let me introduce Dr. Mihai Vidighin. He's an R&D director at PaiQuantum, which is the leading photon computing company located in United States, Palo Alto. He received his PhD in 2016 from Imperial College London, and he continued to work as a postdoc in University of Oxford. From 2017, he joined the PaiQuantum and has been contributing to the development of the industrial scale photonic quantum computing technologies. Dr. Vidighin has a broad expertise in photonic quantum computing technologies, including quantum optical sciences, integrated photonics engineering, and also quantum information science. Let's welcome the speaker. Also, we have a panelist here, Dr. Zhong Lee from ITRC is here with us. Mihai, the stage is yours.
Thank you. Hello, everyone. I'd like to start by thanking the organizers for inviting me to give this talk. Like Young-Gig mentioned earlier, we used to be colleagues at PaiQuantum. Now, I can't directly show you the results of his work, but I can promise you that he had very good impact. So as you can see from the very existence of this seminar, quantum information processing is a widely spread field. You find it in electrical engineering departments, in applied physics, theoretical physics, foundations, computer science, maths, and outside of academia. So that's partly because the research on controlling individual quantum systems is diverse and exciting, and partly because of the promise of new technology. And we live in the age of the information revolution, and computation is certainly a technology that we know how to apply to things that we think are important. So Young-Gig suggested that I give high-level overview of the architecture that we're trying to build up PaiQuantum. And since we have a whole hour, and you can already find online some high-level overviews from my colleagues, I thought, let's take a challenge, and I'll try to do a little bit of a deeper dive in fault-tolerant quantum computation. So please don't be surprised if some of the slides are a little bit detailed and require your attention. My ambition is to guide you all the way from basic concepts to close to the state of the art, And the idea is that that will provide the context that you need to understand the work that we're doing at PaiQuantum and maybe how your work fits into what we're doing and all of that. So, there you go. PaiQuantum's mission is to build the world's first useful quantum computer using silicon photonics. So many of you may have some idea of exactly how ambitious that is. Maybe after this talk you'll think it's even more ambitious than you thought. And I think it's kind of a moon landing sort of level of ambition for various reasons, right? There's like the scale of the technological challenge is just huge, but also it's exciting to work on. It drives new discoveries and pushes technology beyond where other applications would push it. And it's a singular goal, right? So we don't need to build, we don't need to mass manufacture millions of quantum computers to have an impact. We just need to make one. Okay. So since it's that hard, it makes sense to start with asking, why do you think it's worth pursuing this ambitious project, and how a quantum computer might be useful? So I'll start with the basics. Quantum mechanics is most at home in particle accelerators. That's where we get glimpses of the full richness of the quantum world. And we can make predictions that are very accurate and precise about what happens in these incredible machines. Think 10 digits and more than that. But everything around us, that's just quantum electrodynamics. So there's two particles. It's electrons and photons. And of course, there's nuclei so that you can describe atoms. So quantum mechanics is very accurate. But calculating the predictions of the theory is a different issue, right? So the largest number of electrons in an atom that you can solve analytically is one, is hydrogen. And then we have approximations for modeling larger atoms and small molecules and small unit cells in crystals. And a molecule like this is caffeine. You can simulate accurately. You can model accurately using wave function-based methods, which are accurate and well-controlled approximations. But they do use a lot of computational resources, and indeed, large supercomputers, like the one in this image here, are often used for physics simulations. Now, the scaling of this simulation method is such that if I add an atom there, I'm going to multiply. I don't know why an atom didn't get added, but I'm going to multiply the resources required by some factor. Now, the factor of 2 there is just for illustration, but the point is that the computational resources scale exponentially with the number of orbitals you're simulating. And of course, this is just talking about wave function-based methods. You can use density functional theory and other methods from quantum chemistry to calculate for a molecule like this, for example, the exact shape and whether it's stable and estimate some properties. But if you add things like reaction energies, then those methods are not accurate enough. And this sort of molecule, which indeed has some possible applications in the biomedical field, you'll never be able to simulate this on however many supercomputers, right? Okay. Now, what I've just said, it means that, okay, quantum mechanics, it has a known set of rules. They're relatively simple. We know how to calculate what's going to happen. But it's hard to actually run the calculation, and there's no shortcuts to simulate the quantum system, okay? So then it's a reasonable question whether you can use that evolution, that complex evolution, to do computation. And often Richard Feynman is pictured as sort of the pioneer of that kind of thinking, right, of quantum computers, basically. And that's because he said, let me just read that out to you. So nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy, right? So he really had a way with words. And if you type in the first words of that quote, you will get that beautiful inspirational lake picture, right? So it's an inspirational quote. So you'd be forgiven for thinking it's something he said in an interview, and then it became an internet meme. But it turns out he did actually write some papers that are relevant for quantum computers. The one that this quote is from is the transcript of a talk from 1981. It was called Simulating Physics with Computers. And this is a talk that Feynman gave to the computation community. So he was addressing the new community of people working on computers. And the point of his talk was just to let them know that, by the way, quantum mechanics is very difficult, very hard to simulate on your computers. And you just wanted to see what they think of it. Maybe they make something of it, right? So I've already mentioned that, you know, wave function-based methods for simulating molecules are hard because, you know, they scale exponentially. But that's not the point Feynman was making here. So he's making a much more fundamental point, right? So representing any, well, what happened there? Sorry. Representing any state with uncertainty requires, you know, exponential space in the size of the system that you're representing, right? But the point is not to represent the wave function. The point is to, the question he was asking is whether you can use a classical computer to actually just model the behavior of the quantum system. Just like you can't represent the probability distribution of a large number of particles, but you can still run a simulation when you let the particles move around and then you measure something about that gas, right? So can you do the same thing for quantum mechanics? And the answer is no, because it's the same as asking whether there is a classical hidden variable model that makes the same predictions as quantum mechanics, right? And I knew that I could input here, you know, some reference to Rob Spekkens' talk from this morning, but I didn't actually expect that Feynman would feature in his talk too, which I think is quite hilarious, right? Can make a conference on things that Feynman got wrong. Yeah, so in this case, obviously Feynman did not make some, you know, correct and clear and watertight argument about what exactly makes quantum mechanics difficult to simulate on classical computers, but he was definitely on the right path, right? So they definitely did better than with the double slit experiment that Rob Spekkens talked about earlier. And in fact, I Googled some papers after Rob Spekkens' talk, and it turns out that people are still producing like interesting, like nice research on the exact connection between what I'm going to show now, which is the negativity of the Wigner function and contextuality and the hardness of simulating quantum computers on a classical computer, right? So I think the point that Feynman was making in this paper is instructive and it's worth showing. It's definitely missing some details and we're still working them out, okay? So he introduced this thing called the Wigner function. So like, this is similar to things that Rob Spekkens mentioned this morning. So the Wigner function, it is a complete description of a quantum state. And it's a lot like a probability distribution, right? So over there on top, I'm showing an example of a Wigner function for a single particle, right? So it's like a probability distribution over position and momentum. And it has nice properties. So if I integrate over momentum, I get the correct prediction of the measurement probability of the position of the particle. That's what I'm showing as P of x there. Sorry. If I integrate over position, then I get the correct prediction for the distribution of the momentum that I can measure of this particle, right? So that is like like probability theory. And this generalizes to more parameters and more particles and even dynamics. And yeah, Rob Spekkens' papers are very, very good reading for this kind of description of quantum states. Okay, so I'm showing this because it's like an easier to understand image. Feynman actually was using the Wigner function of a spin 1/2 particle, which is kind of a similar thing. He didn't put it in a matrix like I did there, but it doesn't matter. So you have these 4 numbers. He called them F++, plus minus, and so on. And they're kind of like probabilities. So they add up to 1. And if you add up pairs of them, you get things like, you add a pair and you get the probability of the spin being up. You add another one and you get the probability of spin being down. Some other pair gives you the probability of the spin being in a positive superposition, another one is negative superposition, so a lot like probabilities. So Feynman's saying this would be the natural object to use to run your simulation, your classical simulation of some quantum dynamics, right? And this is really nice setup because the reason you can't do that is quite neat, right? So the reason is that the Wigner function, while it is well behaved for some states, like the ground state of a harmonic oscillator. So if I make those XMP the amplitudes of a field, for example, of a mode of light. Some other states, like the single excitation state, which corresponds to the single photon Wigner function, are actually negative in some places, see? So they become negative. And in Feynman's example from his paper, so the state of a spin 1/2 particle can be represented on inside a ball like that. We call it the Bloch sphere. And that particular state, shown as an arrow, that has a Wigner function that has that entry -1, which is negative. So everything's fine as long as you're okay with negative probabilities. And if you're doing calculations, negative probabilities are fine, right? You just work them out, and at the end you get something that makes sense. But if you're actually trying to simulate this thing, you can't just make negative probabilities, right? They don't make sense. It's just not a thing. So that was one way of saying, look, you can't do quantum simulation on a classical computer. And then he went on to talk about entangled pairs of photons. And I didn't read super carefully, but I'm pretty sure he was talking about things that related to the Nobel Prize from 2022. So you can learn more about that in the lectures from the Nobel Prize. Okay. Now the second question Feynman addresses in this paper is whether a quantum computer can simulate a quantum system, right? So he's thinking something like you put these spins on a lattice, and then you can control exactly how they interact. And yes, he says that clearly there are analogies between spins on a lattice and quantum field theories. And the cold atoms community has done some amazing work to actually make this vision reality. And yes, you can simulate quantum mechanics with quantum mechanics. So I want to mention a second paper from Feynman is also relevant, and also not quite wrong. So this one is from 1986, and it's called Quantum Mechanical Computers. And this one was suggested by Charles Bennett. So Charles Bennett was worried, does quantum mechanics impose any sort of fundamental limitations to computation, right? So Charles Bennett is the guy that said that you must use a kT of energy when you erase a bit of information. And he was wondering, does the uncertainty principle also put some fundamental limit on what you can do? And Feynman's answer is no. You can very well do digital computation, so all the ands and nots that happen in a normal computer, as long as you sort of use Bennett's reversible computation model. I don't know why this keeps switching on its own. So in this computational model, you just have to make sure that all of your gates have an equal number of inputs and outputs, right? So if you think of an AND gate, you know how you have 2 bits come in and then only 1 comes out. So you can always keep one of the bits and kind of keep track of it. So that means you don't lose any information, right? And that's because quantum evolution is unitary. Okay. So as long as you do that, then yes, you can write any sort of digital computation using these kind of simple quantum gates that Feynman introduced. So you see those lines, you can look on the left of the figure. Those lines are like bits, but in this case he was saying, you can replace these with spin 1/2 particles. And then you can do a knot on a bit, so that flips its state. So if it was 0, it becomes a 1, and if it was 1, it becomes a 0, right? And then you need to add this controlled NOT gate, right? So I don't know if is there a laser on this thing? No. Anyway, so you see that gate between 2 wires there. So that's a gate, and when then the spin on top is pointing up, let's say, right? Then it flips the spin on the bottom. Let's call these things qubits from now on. Let's stop calling them spins. That's what people now call them, right? And if the, and then also let's call the state 0 and 1 instead of up and down. So if in the controlled NOT gate, if the top is 0, then the bottom stays the same. If the top is 1, the bottom is flipped, right? And you see some examples here where Feynman put together some of these states, including these gates, including a controlled control NOT, and he built like an addition, right? So that's pretty cool. This is not the first time universal quantum computation was mentioned. That was Paul Benioff 6 years earlier. But this paper is still cool because this is the first time you see this diagrammatic notation. And the controlled NOT gate is sometimes called the Feynman gate. So yeah, he introduced these things. So if you're thinking of using spins to do addition, and that's kind of an expensive way of doing a simple calculation, right? So moving on from what Feynman said in that paper, people later realized that if you add just a single extra type of operation, so if you let those spins or those qubits actually evolve and rotate in the Bloch sphere to arbitrary rotations, then that together with the controlled NOT gates form a universal set of gates for quantum computation. And what that means is that this thing, which looks less like a lattice of spins interacting and more like an actual digital computer, this thing, so these diagrams can be made to simulate any quantum evolution, right? So there's a reasonable number of gates that you can put together, and running the qubits through those gates is equivalent to like running, I don't know, spins on a lattice through some complicated interactional Hamiltonian, right? So you can digitize any quantum operation using these gates, right? So clearly this kind of computer, this quantum computer, can do something that classical computers can't do, which is simulate quantum mechanical systems, okay? So what in general this can do that efficiently, that a classical computer can't do efficiently, everything I'm talking about is efficiently, right? In principle, you can do anything. Is pretty hard question. Like, no, we don't really know. But I don't know, I put a snapshot here from Wikipedia. This is what we think. So we're pretty sure you can do things efficiently on quantum computers that you can't do on classical computers. And we're pretty sure that you can't do things that are problems that are in NP-complete. So NP-complete has problems like traveling salesmen and optimization problems. And I guess if we could solve those, we would be too powerful and the universe would explode or something. So people don't think we can do that with quantum computers. But there's stuff that you can do. And there are some really interesting algorithms, like examples of what you can do with quantum computers that you can't do with classical computers. Examples that are outside of simulating quantum mechanics. And the coolest one is, well, I don't know, I think is the coolest one, is Shor's algorithm. So shown here in the modern version of Feynman's diagrammatic notation, right? This is the Mathematica version. So there's an algorithm, right? You have a number of gates. This is a simple case with just 4 qubits. And there's that subroutine called the quantum Fourier transform. There's some other gates that actually depend on the input to your problem. And what you can do using this algorithm and some more calculation is take a large number and factorize it, find its factors efficiently. And it's believed that that's really hard to do on a classical computer efficiently, so much so that the security, the main encryption protocol used for securely signing and securely communicating messages across the internet is based on that. So if anyone could, in fact, factor that large number q times p, which is a public key, then they would get the private key, which is both q and p, right? So that's how strongly we believe that this is hard to do, and yet we know an algorithm for doing it on a quantum computer. So this is a nice example, but in terms of like applications that are useful, because I said we want to make a useful quantum computer, we're kind of back to where Feynman started, right? So we're back to just simulating physics. So you might cringe at this slide, right? It's like, maybe you think it's an investor slide, so are you going to solve climate with a quantum computer? So obviously I'm not saying we should solve climate change by building a quantum computer. What I'm saying is there are examples of physical simulation problems that we know we can solve on a relatively small quantum computer. They are actually useful for things that we at least at PaiQuantum, and I guess everyone agrees are important, right? So there's examples in drug discovery, in sort of, let's say, getting insights on high temperature superconductors, figuring out how chemistry of batteries works, figuring out how chemical reactions work that use up a significant part of the world's energy or generate a significant part of the world's carbon, things like that, right? So they are examples, they do have impact. And, what happened there? Okay. And there are some benchmarks, right? So these are the sort of the simplest, the smallest useful examples of what I just mentioned. And some of them I already mentioned. So down there on the left you have the Fermi-Hubbard model, which might give you insights on high temperature superconductors. You have nitrogen fixation there. That's an important part of making fertilizers, and it uses a lot of energy. You have encryption there just for fun. And on top, a paper that we have with Mercedes-Benz on simulating chemistry in batteries to improve lithium-ion batteries, right? So you can see, who worked on these things, so you can imagine that, there was a good effort into making these things as efficient as possible. And I think they are indeed useful applications. But then, an important thing to notice on this slide is that axis on the left, right? So to do these things, the smallest things, they are useful. You need billions of gates, right? So you need those gates that I was showing in a previous slide, you need to do billions of steps of these things. And we do billions of gates all the time in CPUs on laptops, right? And that's really impressive. And that just happens. That happens the same time every time you do it, right? There's no error. That's very impressive. And I guess transistors have some redundancy built in, but that redundancy certainly doesn't exist in individual, like isolated quantum systems, right? So spins, they feel some field, or maybe just spontaneously decay, right? So there's something that's going to happen on your quantum system if you try to use that in a bit instead of a transistor. And people have gotten really, really good at reducing the error rates, is called. So the probability that something happens to your qubits within one operation, right? And they've gotten down to like probabilities 10 to the minus 3, 10 to the minus 4. So what you can do hundreds of gates with that. But we just said that you need to do billions of gates. So getting from 10 to the minus 3 to 10 to the minus 9, that's not an incremental step, right? You need to do something else. And that something else is like you need to do active noise suppression. So you need to build some redundancy in the way you represent quantum information. So you're going to use multiple physical qubits to represent a single logical qubit, right? So you store your information in some redundant state. And that way, if something happens to some of your physical qubits, you have all the other ones to remember what the state actually was, okay? And obviously, the price you pay for this is, okay, there's one qubit there, and there's like 100 to 1,000 times more there. So it makes everything 100 to 1,000 times bigger, but that's the only way to do it, okay? So here comes I'm going to try to explain quantum error correction now, so please. Hopefully we follow through. Okay, so let's see. So I said that you don't do error correction on CPUs, but for communication we do sometimes do error correction because radio channels and things like that, they are noisy. So let's say that's your information, that's a bit string, like 100 something something. So the simple thing to do is you just repeat what you said. So you transmit 111, 000, so on and so on. So then if one of your bits gets flipped by you're supposed to measure 0 on your antenna, but it looks more like a 1. then that's okay, because you have the other two, and you can just see what the majority says, and that recovers your information, right? So it's pretty simple, the concept. See, notice how you couldn't do this with 2 bits. So if you had 2 and one got flipped, you couldn't tell which one got flipped. But if you have 3, then you have a majority. Ooh, what happened there? Oh, that's okay. That's okay, keeps me on my toes. Right, so that was classical error encoding, error correction codes. And now I'll show you the quantum mechanical version, okay? Okay, so a qubit, right? It lives in the Bloch sphere, right? So hopefully you've seen the Bloch sphere. It's analogous to the Poincare sphere for polarization. So you can think of this as up and down is like vertical and horizontal polarization. Then you have diagonal and anti-diagonal and circular and anti-circular, right? That's one way of thinking it. And you can label one of these. You can pick an axis and label the 2 states on that axis as your logical 0 and your logical 1, right? Okay. And then the state of the qubit will be a superposition of these, right? So you write that superposition as like a sum of kets. So you have an alpha 0 plus beta 1. Let's say that's your state that you want to protect. So basically you want to protect the alpha and the beta, right? That's what you want to keep from. Your errors should not ruin your alpha and beta. Just keep watching for that one. Okay. So to talk about qubits and states and measurements and things like that, it's useful to introduce the Pauli operators. So I think Rob Spekkens also introduced them earlier. I don't think you need to write down matrices to introduce them. So obviously, if you know Pauli operators, that's fine. Bear with me. But I think you can live without the matrices. So they're basically a way of labeling Cartesianal sort of directions in the Bloch sphere. So the Pauli Z kind of corresponds to the vertical axis here. So if you say I'm doing a measurement of a Pauli Z operator, that means I'm measuring how likely my qubit is. So basically the projection of my qubit on that vertical axis. So how likely it is to be a 0 or a 1. And when you do that, but when you do that measurement once, so you get the probability of 0 or 1 if you do multiple measurements, right? If you do it once, you get one of 2 outcomes. You can label them plus and minus 1, and your state becomes 0 or 1, right? So that's, you project when you do a measurement. On the other hand, if you apply, when I'm going to say we apply a Pauli Z, what that does, it's called a phase flip, and it changes the plus, so the positive superposition into the negative one, and vice versa. Okay. And then I'm also going to talk about the Pauli X operator. So it's the same thing. It kind of labels this sort of in-depth axis. So when I'm saying I'm going to measure a Pauli X, you're measuring the projection on that axis. Again, you get a plus minus 1 outcome, and your state becomes either plus or minus, right? So obviously, if I measure my qubit, my alpha and beta are gone, right? If I have many copies, that's fine. I can estimate them. But if I have one copy and I measure it, they're gone. Okay. So you can't just measure and make copies, that's for sure. If you apply a Pauli X, that flips the qubit. So it's called a bit flip. It changes a 0 to a 1, a 1 to a 0. Okay. So let's say that's my quantum information over there. That's alpha 0 plus 0, 1. And like I said, you can't just measure and copy, right? That's the no cloning theory, so you can't do that. But you can apply this simple gate that Feynman introduced, the control NOT gate, to do something, do pretty much the same as the redundant encoding in classical error correction. So you take 2 extra qubits, you start with them being 0 and 0, right? And then what happens is the alpha term over there from your information bit, so that 0 leaves the bottom qubits in the 0 state, and the other term with the 1, it flips them. So you get an alpha 0, 0, 0 plus a beta 1, 1, 1, right? So you get an entangled state of the 3 qubits. You can see that there's some redundancy because now I know these qubits should have the same state, but my alpha and beta are still there. So that's good, right? That's fine. I've done something good. So now if I measure any of these qubits, I'm going to get a 0 or a 1, and that's it. I've basically measured the initial qubit, and I've ruined it, right? So you don't want to do that. But you would like to do a measurement that tells you whether these whether, let's say, the first and second qubit are the same, right? Because whether they're 0, 0 or 1, 1, that's fine. Both of those options are fine. So if I can keep both terms and know that those are the same, then I know that my state is not being changed by some errors, right? So that measurement exists, and it's called the ZZ measurement, right? So that's not like you're measuring each qubit. I just said that's not a good idea. And we're not going to go into why. It's because products of Pauli operators have degenerate eigenvalues, right? But basically, every time you measure a product of Pauli operators, you still get either a plus or a minus one, and it always halves the space in which your state lives. And you can see that from the way you actually, this is how you would apply a measurement, and you can see what it does if you think of it a little bit, right? So you add an additional qubit, and now you do a control knot. So if the first one is a 1, that second one gets flipped, and then you do another control knot. So if the second one is also 1, then it gets flipped again. So you see it stays 0 if the first two qubits are the same. And if they're opposite, then it flips. So then if you measure that, it's like you're measuring the parity of the first two qubits. So you're measuring whether they're the same or not, right? So I hope that's clear. So if I do a ZZ measurement on the first two qubits, and I get a +1 outcome, that just tells me that the first two qubits are the same, and both terms agree with that. So I keep my whole state, I keep my alpha and beta, and I know that it's fine. It's like in the right states that encode my information, 0, 0, 0, and 1, 1, 1. Cool. So what if something bad happens and I get a bit flip on the second qubit? So now it's turned from a 0 to a 1, right? So now I get that state. That's bad. But now I do that measurement, and again, both terms have opposite signs for opposite states for the qubit. So it's 0, 1, and 1, 0. They both give me a -1 outcome. So if I get a -1 outcome, then again, I keep my state. See, alpha and beta are still there. And I know that something bad happened, right? Because I'm supposed to get a +1. And to know exactly what happened, I have to do another check, right? So I have to also check the parity on the second and third qubits. If I get -1 on both, I hope you can see that, right? If I get -1 on both, then it must be the case that the middle qubit was the one that got flipped, right? If I get a +1 and a -1, then it must be that the third one was flipped. And you can work it out. You can also tell if the first one was flipped. So this is pretty cool. And once you know which qubit you got flipped, right? You know, oh, there was a flip on qubit 2. Your first reaction is better go back to my 0, 0, 0, 1, 1, 1. But you don't have to do that, right? Your alpha and beta are still there. You just have to remember that now you expect to measure -1, -1. That's fine. So -1, -1, by the way, is called the error syndrome, right? So in an error correcting code, you measure an error syndrome. It doesn't change your state, but it tells you if an error occurred. And then you have to be able to interpret your error syndrome. And then you're doing successful error correction. Now, the other thing is, why am I suggesting that errors in quantum computers happen like this? Like every now and then you just randomly flip a bit. That's not what happens, right? Like basically what happens is you have these 3 qubits, and then there's like a little extra field on one of them, right? So it like rotates a little bit faster than the other one, or something like that. So what actually happens is when I apply the parity check measurement, one of two things happens. I get a +1 outcome, in which case I project back into the correct state. My code space is called, right? But sometimes if one of the qubits is like a little bit off, with some probability, my measurement gives me a bit flip error, right? Because that's why I measure. So the measurement transforms like tiny coherent things that happen in your quantum computer into most of the time nothing, and sometimes a Pauli operator on a qubit. So I hope that's clear. And these two measurement operators, I added an identity on the qubits where we don't do anything. These are called stabilizers, right? So stabilizers are measurement operators for a certain quantum error correction code. And you just keep measuring them. You can measure them however times you want, in whatever order. And they're supposed to give you +1 if nothing happens. And sometimes they'll give you a -1, right? And you'll know that an error occurred. But your alpha and betas are not changed by doing these measurements. Now, obviously, this is a very simple code. And it's not that good, to be honest, all right? So if you get 2 bit flips, then your error syndrome, so remember the result of these 2 parity checks I'm doing, they're like +1 and -1. So remember, that was an error syndrome of a single bit flip. So that's bad, right? I'm not distinguishing between 2 different errors, so that's a fail. And the other thing that can happen, it's a quantum system, so you can get a phase flip, right? You can get a Z operator acting on one of the qubits. And that turns my state from having alpha and beta coefficients to having alpha and minus beta. And this error correction code doesn't do anything about that. It just has no idea that that happens, okay? So it's not what's going to get you to 10 to the -9 logical error rates, right? To get to 10 to the -9 logical error rates, you have to use this, which is the surface code, right? And because this looks a bit more complicated, you're probably hoping that this is not another toy example. And the thing is, it's not. This is state of the art, right? So there are other quantum error correction codes, but pretty much everyone working on trying to build a quantum computer at the moment is basically trying to make this. So it's pretty cool. We're close to state of the art here. Okay, so why is the surface code why it's such a good code? Why do people want to make it? It's in the name, right? It's because it looks nice on a surface. So those points over there, those are actual qubits. So you can imagine there's like a chip. So let's say there's ions or something that our friend over there is trapping on a chip. And then, those qubits are there on the chip. And all of the stabilizers, so all of the parity checks that I have to do for error correction, they're local, right? So they're these operators that I'm showing there. I'm going to describe them in a second. And they get applied on qubits that are run right next to each other. So that's great if your qubits are on a chip. And you just need to do gates for things that are close to each other. Because I've shown you in a previous slide, you have to do some gates to do these measurements. They're not trivial measurements, right? So that makes it pretty nice for implementations, right? The surface code. And it's also pretty nice for error correction, and I'll try to explain why that is. So it has many, many stabilizers. So again, the dots are the qubits, and stabilizers are the measurements that you can do on this code. And if no error happened, you get a +1 result to all of your measurements. And if something happens, you get a -1, and you know what happened. But you're not ruining your alpha and beta. And the stabilizers for this code are such that all of on the border of all of the pink areas, you have these Z measurements, right? Like Pauli Z operators. And on the border of all of the blue areas, you have the X versions, right? So these are the measurements that I have to keep doing. So keep checking the parity of those 4 qubits bordering these areas in order to do quantum error correction using the surface code, okay? So I hope that's clear. Notice that I'm not even attempting to tell you how to prepare the states that these qubits are in, right, like I did previously. And that's because doing these measurements prepares the state. So that's how there's so many stabilizers, there are so many parity checks that if you measure all of them, each one of them halves the space that your state lives in. And then the other one halves it again and halves it again and so on. And there's so many of them that you're left with a 2-dimensional space. And that's where your logical information lives. So however big I make this area, however many qubits I put here, if I measure all the stabilizers, there's only 1 qubit going to be left. And that's your logical qubit that's encoded by this. And I'm going to tell you later how to access that qubit. But what you might be wondering now, I'm hoping you're wondering this, is I just said that you're going to prepare the states by doing all of these measurements, right? And you're going to be like, how am I preparing a known state if I have so many possible outcomes of doing so many stabilizer measurements, right? Like they can be plus, minus, 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 plus, and so on, right? And the thing is, traditionally, you say you don't have errors where everything measures a plus one. But plus one and minus ones, they're just labels. You can just do a measurement, relabel everything as plus one. And the important thing is that from there on, you know that when something changed, then there's an error, right? And again, the state of the logical qubit, we'll talk about that one later. Okay, so how do you detect errors with the surface code? You keep doing these parity checks, right? And it turns out, maybe you can work it out if you like this kind of stuff. If I have a Pauli Z doing a, let's start with an X. If I have a Pauli X doing a bit flip on one of the qubits, then I'm going to measure -1 on the parity checks next to it, like I'm showing over there on the right. If I have a Pauli Z, then I'm going to measure a -1 to the left and the right, right? So if I see these -1s, then I know an error happened there, and I just have to remember. From now on, I expect -1s there. And then my logical information is fine, right? So it's very much analogous to the much simpler code that I showed earlier. Okay. So I keep saying that you have to keep measuring these things, right? So the way to imagine it is, let's say you have some qubits, you have your surface code, you do some measurements. Let's say first time you get all +1s, you have no errors. And then in the next time step, you measure again, and some stuff changed, right? You get some 2 minuses there, 2 minuses there, and you're like, okay, some errors happened, it's fine, I know where they are. And then in the next time step, I do the measurements again, and some stuff, that you get an X and a Y on top of each other there. It's, sorry, an X and a Z. You get a Pauli Y, that's fun, right? So you keep getting these, you keep track of the errors, and that's all you need to do, just keep track. So at each step, it has to be clear what happens. You have to have a simple enough error syndrome that you can tell kind of what happened. And the really cool thing is, I want to explain this, but okay, so maybe something bad happened with your measurement, right? Maybe your qubits are fine, but your measurement has errors. So what happens there is you'll see in one time step, right, you'll get a -1, then you get a -1 again, but then you can stop getting +1s, and you're going to be like, well, that doesn't look right. So that's actually, you can imagine this thing in 3D, and in time, you're detecting errors on your measurement. So that's a bit more of a subtle thing, but I think it's kind of cool. Okay, so this thing is really good at detecting errors. And the way it works is that the bigger you make the code, so the more qubits you add to that state, to that area, the more tolerant you are to errors, as long as your probability of having errors in each step is below a certain threshold. So then that's called the quantum error correction threshold. That's kind of an important thing, okay? So you see there's a plot there of the logical error rate, so the probability that something happened that's actually really bad, versus the physical error rate, so the probability of something happening at each step on one of the qubits, right? And there's this step function. So, and you can see there in the different colors, the bigger I make the code, the sharper the step function. So if I'm on the left, below threshold, and I'm increasing the size of the code, my logical error goes down, and you can see where I put the arrow there, that's pretty much 0. So you can get 10 to the -9 like this. It actually works. And you might ask, how far below threshold do you have to be? How do you choose how big the code is, where your error rate has to be? And that's a nice question. It's really fun. The short answer is kind of where I put that arrow there, like a 60, 70% kind of thing. But the more fun answer is, I saw a colleague of mine made this plot once, and I think it's really fun because it's like very high level, but still says something. So let's say I have my error rate on some component, right? And there's a error correction threshold that I just described. And if the error rate is higher than that, then at each step there's going to be too many errors, and I'm not going to be able to tell what happened, and the code's going to fail, right? But if I'm to the left of the quantum error correction threshold, the lower the physical error, the smaller the size of the surface code I need in order to get my 10 to the minus 9 logical error, right? That makes sense, right? So your number of components goes down as you decrease the error rate. Okay. And then it's fun to think, okay, let's say I'm really good at making these components and I can actually make error rates that are below threshold, that's what you want to do. That's the most important thing. But then probably as I keep going below threshold, the cost of the component is going to go up. And it's kind of hard to talk about, actual money costs because it's R&D and production and so on. But you can make a nice argument about, for example, cooling power. Let's say my error rates go down if I reduce temperature. To reduce temperature, I need more cooling power. So the cooling power per component is basically this cost. It goes up if I want to reduce errors. And at some point, it blows up because there's other reasons I have errors than just my temperature. So it's kind of cool. If you imagine these are on a log plot, then if I multiply the number of components and the cost per component, which in a log plot is addition, then I get a total cost versus errors. So we've done like a very high-level optimization of a quantum computer architecture. There you go. So that's what we're doing at PaiQuantum. We're figuring out where that point is, where thing is the most efficient to make your quantum computer, because your total cost is the lowest. Okay, cool. So let's recap. Thank you for paying attention to this part. I think it's worth it. Okay, so we've seen that you can solve useful problems. Quantum simulation, hopefully some classical nonlinear dynamics. We're also working on that. So you can solve some useful things that can have actual impact using quantum computers, right? But you need very low error rates, 10 to the minus 9 or higher or lower. And to achieve that, you need quantum error correction. You do quantum error correction using the surface code. So you now know the state of the art on that. You know what a quantum error correction threshold is, right? It's like the most important property of your code. And to do fault-tolerant quantum computing, now we just need to figure out how to do logical operations while doing this error correction, right? so it's still a little bit more complicated. Okay. So how do I access my logical information? So it turns out there are two operators which are not, they do change my state if I measure them. So if I measure this Z that spans all the way from the left to the right of the code, notice that the colors are not symmetric, right? So there's blue on the top, red on the bottom, right? So that's why these are not symmetric. So I measure these Zs. That's actually how I measure in the Z basis, the qubit. I get a 0 or a 1, and I'm measuring my logical qubit. And then if I do these X's on the vertical that span all the way from the top to the bottom, that's how I measure the X basis for my logical qubit, right? And that's also how my error correction code fails. That's the only way it fails, is when I happen to get so many errors that there's a string that spans all the way from one boundary to another. And then it's indistinguishable from a logical operator, and it actually changes my state. So the code has failed. And that's why if you make it bigger, it's less likely that you'll get a string that spans the whole thing, because there's more to span. All right? So I hope we understood that. Okay, so that's how you measure and you access the quantum information in your surface code. And now let's take a circuit diagram. We've seen a couple of these in some previous slides, and see how the error correction code fits on that, right? So it gets getting a bit more complicated. So I have a bunch of qubits. Now each of them are logical qubits. For each of them, I have a surface code. And remember, we said that you stack these measurements. You keep doing the same measurement. So in this diagram, time flows from left to right. So what I'm showing in that prism is like a bunch of surface code measurements. You keep doing and you keep doing them. And that's just to do nothing. That's just to do the line, right? Okay. And you have all of these lines for the different qubits. They correspond to one of these surface code pipes. Okay. So how do you do the gates? So I'm not going to explain how you do the gates, but here's some nice pictures. And that's the paper that you can read to understand how we do gates. Right? So, but high level, you can imagine that if to do logical things to one qubit, I have to like change the way I do the measurements. It's kind of the same thing for gates, right? So let's say I have two neighboring qubits. I want to do some logical operations. Normally, I would do surface code parity checks on this, surface code parity checks on this, and now I'm going to switch to like doing some measurements between them. That's going to do a logical operation. So I'll leave it at that level. I would need to study a little bit to even explain what these things do. And then at PaiQuantum, right? Like we understand all of this stuff. And we can simulate it, and we can simulate applying a logical operator while doing error correction, and we make plots like that. And the thing is, these things are hard to describe, right? Of course, you can't analytically tell what your threshold is, especially when you're doing logical operations. So we do numerical simulations. We just sample these things a lot, and we can measure the thresholds, and we can tell how good our architecture is, right? But you just said that you can't simulate quantum computers. How come we're simulating something that complicated? Okay, so that's a good question, which hopefully you asked. And the truth is, all of this stuff with stabilizers is actually classically simulatable, because it's all like Feynman's addition. It's just a couple of gates, right? In order to do universal quantum computation, the hard stuff, the negative Wigner function stuff, you need to do one more thing. You need to do magic state distillation. So there's like, you still use these operations, but you use them in a special way. And again, it's in the paper if you want to figure out, but there's this extra complication, then you have to do magic state distillation on top of all of this. So all of this is to simulate a molecule or something. So all of this, these guys, when they figured out the resource estimate for doing this salt molecule to lithium ion reaction energy, right? They had to figure out how to represent a chemical reaction with like 3D orbitals onto these discretized quantum gates. They had to figure out how to compile them in the most efficient way, how to implement them while doing error correction, and they even like did optimize for low-level operations that are suitable for photonic quantum computers. So all of that to get this resource estimate. But on the other hand, to do the same thing, we know that the resource estimate is for the accurate wave function-based simulation method for this same reaction. And yeah, you need more bits than atoms in the universe, so it's impossible, right? At least with current algorithms. So yeah, that's why we keep doing these things. Okay. So I told you about qubits and like these measurements on many qubits, but it seems kind of hard to implement. How do you actually implement these things, right? How do you measure 4 qubits in ZZZ? So you can imagine, right? Like I told you that surface codes like could be actual qubits. So this is what the matter-based qubit community would prefer probably. So you have these qubits; they're always there. And then you can do nearest neighbor gates, and you can do measurements, and you implement your surface code that way, right? Or you could imagine that you had some natural way of building a very, very entangled, very big state that looks kind of like a 3D lattice, and if you keep measuring that, it's like measuring the surface code. So that's measurement-based quantum computation there, right? And at PaiQuantum, we think of everything in a third framework. I mean, these are all equivalent, right? But this is particularly useful for us because it's suitable for photonics. But it also has some general, very nice properties. So we call our framework fusion-based quantum computation. So in fusion-based quantum computation, your resources are these entangled states of small number of qubits, represented here as those hexagons. So they're linked to show that they're entangled, right? They're in some correlated state. And yeah, they're small and they're always the same. And you just have to make a lot of these. You have like some factory that makes resource states. And then you implement your error correction and your logic by doing 2 qubit measurements that we call fusions on these resource states, right? So it's pretty simple. And let's see what a surface code looks like in the fusion-based quantum computation picture. Okay, so it looks like that. I was kind of planning to pause this. I don't know how to pause it with this remote, so you have to just look really quickly. So, oh, there again. Okay, so keep that image in mind. There's like a single layer of qubits, right? So that's kind of like my surface code. That's the layer of qubits that encodes one logical qubit, okay? And then in the next step, I keep those, and I make a lot of resource states. Those are the little hexagons. The points are qubits, and the lines are showing that they're in an entangled state, right? So I've created many, many resource states. Okay. Now the third step, I do this fusion measurements. So the fusion measurements, once you've measured a qubit, is like done. It's out. You've measured it. You forget about it. So they do two things. One is they move the information that was stored in the bottom layer of qubits onto a new layer on the top. Technically, they do teleportation, but yeah, it's fine. So they replace the layer of qubits with another one. But in the process, you get all of these measurement outcomes from all the fusions. And those tell you what the parity checks on your surface code are. So that's how you do quantum error correction and the surface code with fusion-based quantum computation. So you've understood a lot of things by now, hopefully. Okay, so to describe an architecture in fusion-based quantum computation framework, you need a resource state. You need to put it in some shape that you can tile, because you know we need these surfaces and volumes and stuff. And you need some description of how you're going to measure 2 qubits from these resource states to fuse them. And again, once you measure, they're gone. And yeah, you saw how it works in the previous slide. And then you can define it like that, the architecture, and then you can do your simulations, and you can get your threshold. You can figure out what is the threshold for errors that this code can tolerate. So I hope you can see those axes there. One is showing the error probability, so the probability that when you do a measurement, like it's flipped compared to what you expected. The other one is actually showing something that I didn't mention yet, the probability of erasure. So actually, the surface code is so cool that sometimes if you just, you try to measure a parity, and you neither get a +1 or a -1, you just get nothing. You just see you lose your qubit. Because in particular, if it's implemented with photons, sometimes it just misses the detector. So let's say it's just missing. And that's still fine. You can still guess what it's supposed to be by looking at its neighbors, as long as the probability of that loss is like low enough. And you can see, so these are toy models from a paper that we published, right? So the 6 ring is like a toy model. But I mean, it's a good model, right? It's still good architecture. And you can see these are reasonable number probabilities, right? So you can have 10% probability over there in the corner of losing your qubit. That's a big number. That's reasonable. You have like 1% probability of an error there in the bottom right corner. So these are reasonable numbers. They're not like 10 to the -3, right? So that's pretty cool. And our codes are a bit more complicated than, you know, our optimal architecture is a little bit more complicated than this. And the cool thing about this is, you know, we can define pretty transparently an architecture in this framework. And it's a small sort of constant depth architecture. You saw the resource states. You create them, you measure them, that's it. They always live the same amount. The same thing happens to them. So it's very easy to see, to model everything. And you can actually go down to physical errors. And you can describe in the same framework, which is a simple definition. You get errors on qubits, you get measurement errors, loss. You can treat cases when your measurement just doesn't make sense. You're looking for a 0 and a 1 and you get a 2. And maybe your fusion measurement, like I'm going to show you in a second for photonics, maybe it's non-deterministic. It only works sometimes. That's fine. That's included in the framework. It's included in the fault tolerance analysis. Or maybe, you know, your resource states, they're generated probabilistically. That's fine. That's included in the framework. Maybe you need to decode your error syndrome, and like the algorithm for doing that in the best way possible is like pretty hard to implement, and you just have an FPGA. You can do a simpler algorithm that's included in the threshold calc simulation, right? So all of this stuff, and logical operations, we can just simulate it for architectures which are well defined. And we can get multi-dimensional versions of that graph where you don't need to put high-level things like qubit error. We can have propagation loss or detection efficiency, or like things that we actually know we have to build, right? So we know exactly how to measure whether we're close or not to building a quantum computer because we know what the specs are on all of the components. The only disadvantage of this framework, you can't really answer the question, you know, how many physical qubits do you have? Because we never really do physical qubits, right? It all kind of emerges. And maybe a good question would be, how expensive is a resource state generator? That's a reasonable question for us, right? So we can't really tell you how many physical qubits we need, but we can tell you exactly how good our components need to be, and we can measure how good they are now. So we can go down all the way from architecture to hardware level errors, like classical things that you can define. Okay. So hopefully I think is that the last slide I have? Yeah, okay, so that was the last slide, there's kind of high level. So now there are two reasons why fusion-based quantum computation is particularly appropriate for photonic quantum computing. One is the fusion that I was assuming in those examples previously is like really easy to do with photons. So it turns out, oops. So, I'm talking to the microphone, sorry. So the way you do a qubit with photons is you have two waveguides, right? So hopefully you know that an optical fiber is a waveguide. You can also draw waveguides on surfaces, on chips, and light will just propagate through them in a single mode. So when you have two waveguides and a single photon in one of them, then that's a qubit, right? If it's in the top mode, it's a 0, bottom mode is a 1. So that's your photonic qubit. And it's like really easy to do single qubit things. So you can bring the modes together and couple them and make little interferometers and phases and stuff and just basically make your alpha 0 plus beta 1. That's easy. The other easy thing to do is fusion. So if you just take two pairs of modes, so 2 qubits, and you do that simple beam splitter network and detect photons at the end, with probability 1/2, you get a successful fusion. I'm not going to explain what that stuff means there, but okay, I can explain it. So when you happen to get a photon in one of the 2 top modes and one in the 2 bottom modes, then you get a successful fusion. Sometimes you get a failure. You get like 2 in the top or 2 in the bottom, but you still get information, right? And sometimes you've lost a photon or you have 3 and you're supposed to have 2, and that's erasure, right? So we can work with this probabilistic fusion. So this fusion that works half of the time, this is fine. In the top slides that I was showing, you can imagine that each fusion is actually the result of some combination of fusions on redundantly encoded qubits, like I was showing in the repetition code. And that works. So we can build this into our architecture. Now, the second reason why this is particularly appropriate for photonics is that it's very modular, right? So you see, you had all of these resource states, they were all the same, and then you just had to make these measurements between them. So it's a very modular architecture. And you can imagine, if you want, that you can build a module that's a resource state generator, right? And then you have to link them. And that's true for any quantum computing architecture, right? Like I think it's possible, and it'd be really impressive to see, you know, on a chip, maybe superconducting qubits, you have enough to do a surface code. That's awesome, right? But then you still have to make thousands of these and connect them, right? So you need to be modular. And you need to be able to connect these modules and like kind of move qubits between them. And the best way to move information like in the world is optical fiber. So if your qubits are photons, you just put them in an optical fiber and everything's fine. The other thing this image is showing is kind of how these modules communicate to do, let's say, the error correction measurements. So that's like a very simple, repetitive thing they do very, very fast. And maybe there's some central processing unit kind of thing that changes things every now and then to like actually do the logical operations. And that happens at a lower clock rate, right? But it's like maybe a more complicated computation. So one fun takeaway from this image is, you know, sometimes maybe you read in a magazine that, oh, quantum computers are going to be bigger or faster than normal computers. I mean, the truth is that the classical computing power that you need to drive a couple of qubits quantum computer is way more powerful than that quantum computer if you were running the same algorithms, right? So it's like there's a lot of classical logic in here, but we've kind of figured out the error correction, the error syndrome decoding and all of that, and you can do it fast enough. Okay, so this is really cool. It turns out optical fiber, you can do more than connect resource state generators with it. So optical fiber is so low loss. I'll just move because I don't want you to be stolen by the image. So you can make a really long optical fiber and put many, many qubits in it, and you're basically storing, you're making a buffer of qubits, right? And then you can bring them in when you need them, and you can basically print your surface code. And in fact, in principle, you can print your entire quantum computation one by one. So I'll try to explain this, but there's a paper over there. So basically, when you're doing nearest neighbor fusion, you're just fusing two qubits where one of them was delayed by some short fiber, by one clock cycle, right? If you want to do a fusion across a line, then you have a longer fiber, however big your area that you're printing is. And if you want to join between two planes, then you have an even longer fiber, right? And you can 3D print your quantum computation, right? So that's kind of cool, because in principle, a resource state generator, you can do a whole quantum computer with it. But in practice, this is really slow, by the way, right? Obviously. It takes a while to print that. So in practice, a kilometer fiber is negligible loss, and we can fit like 1,000 qubits or something in a kilometer of fiber. And basically what we're thinking is a resource state generator is a logical qubit. That's kind of a good compromise, we think. And you can read more in this paper. Okay, so final question is, it seems like I put all of the difficult parts in that resource state generator. I just shoved them all in there. So what's inside there? So let's recap what you need for fusion. So you need a way to route these dual rail photonic qubits, right? You need to move them around in waveguides without loss. You need to be able to switch them fast and efficiently, like move them where you need them, interfere them for the fusion, for example, and detect them very efficiently at the end when you do the measurements, right? Those are the components you need. And to do resource state generation, you need the same components. It's just the same, more of the same stuff. And you need one extra component, which is a photon pair source, which you can use to make, to actually prepare your single photons to start with. And that's the part that I actually work on. And I'd love to tell you about the advances we're making there, maybe at some point. Okay, and the good news is all of these components, including the pairs, the photon pair source, the detector, we can make them in what's arguably the only way that you can make millions of interconnected things, which is semiconductor fabrication. And I'm going to skip this video. Let's play it. And it's just showing, I think the point of this is semiconductor fabrication is cool, and you have nice automation. Okay. So that doesn't mean we have to build our quantum computer out of silicon and oxide and metal, right? Like we just need to use the tools of the semiconductor fabrication industry. And I'll just give this example, which is how we make our single photon detectors in the semiconductor fabrication. So basically, there's a production fab somewhere in the world where they deposit superconducting films for us. And the critical temperature of the semiconductor films is like record high. We've optimized everything. And then we go ahead and we make these nanowires out of a superconductor. And their critical dimension, some tens of nanometers. We use advanced lithography to make that. And then these nanowires are so sensitive, their superconductivity is so sensitive that if they absorb a single photon, they'll always just like stop being superconducting. And the whole thing you'll see a big voltage spike that's very easy to measure. So they're like ideal single photon detectors. And this was a research technology, right, in academia, and like it's now basically production, right? So yeah, I don't know. It depends who you're talking with, but yeah, it's fair to say that we've made and measured orders of magnitude more of these devices than anyone ever outside of PaiQuantum, and we know how they yield, we know how the efficiency, and we just need to do that for more components. But this slide is from a few years ago, so obviously we'd made advances. So we're improving our designs on these things. We're improving our designs on everything. And apart from the component level design and manufacturing, we also need to work on packaging. So the I/O of these integrated chips that have the sources and the detectors and the waveguides on them. You need to. I was saying that you have optical fiber. Well, you need to connect that optical fiber to the chip. So again, this is an old picture. You can't do it vertically. It's too lossy. But again, it's like a very clear problem, well-defined engineering problem. We need very low loss between an optical fiber and a chip. And it's not a quantum problem, but it will make or break the quantum computer, our quantum computer, right? So we're just focusing on making that really well. And that's the kind of work that we know we have to do. And the cool thing is that, yeah, we're now iterating on these things, right? So we're not like figuring out if we can do them. We've like done them once, and now we're improving, right? So that's when in your company, you really enable your engineers to do their thing and like do expensive things. And so a day in the life at PaiQuantum, right? You're designing some components, you're figuring out how to put them in some circuit, or you're figuring out how to make those components exactly to spec with no defects. You're testing them automatically, and then you're analyzing. So for each of these cycles, you're going to analyze hundreds of thousands of components, and that's how you really make progress and improve your components through this iteration cycle. The other thing that we're working on, so I said that we're working on I should have flipped those slides, but I had to send them early. So I said that we're working on the semiconductor fabrication of components. We're working on packaging to make good I/O for the semiconductor chips. And the components, right, like they need to meet architecture spec, but they also impose specs on your infrastructure. So for example, those single photon detectors are awesome, but they have to work at 4 Kelvin. So we need liquid helium temperatures, right? And as the detectors get better, then you need less helium temperature. So a good question for us would be, hey, how much cooling power do you need for a resource state generator? And we're lucky that we only need 4 Kelvin, which is 4.1 is liquid helium temperature. So people can generate like pretty impressive amounts of cooling power at that temperature, right? Like you have hundreds of kilowatts in particle accelerators. That would not be the case if we needed hundreds of millikelvin. So you can see from this picture and that just the mention there of CERN. I wasn't kidding with the moon landing thing, right? So that's we need particle accelerator levels of cooling power to make the first thing, right? But hopefully, I've convinced you that by focusing on the moonshot, right, we've managed to break it down into reasonable, like manageable, well-defined problems. And none of them seem impossible, right? And that's the work that we're doing at PaiQuantum. We're working on solving these problems, and hopefully you have like a reasonable understanding now of what they are and maybe how your research fits into what we're doing, and maybe what we're doing now or in the future will contribute to this moonshot. So yeah, thank you.
Thank you, Mihai. That's a very impressive result. So we're beyond the schedule, so let's quickly have a Q&A session with the panelists.
Actually, I have many questions, but I will give you one or two questions. You talk about the error correction with the source code, but for the photon losses, you showed that about the 12% erasure probability. But when I saw your papers from PaiQuantum, in some papers, it shows that only several percent of the threshold for maybe for the fusion making fusion networks, and some for the fusion-based quantum computing. In that case, the threshold was higher. So when you mean the 12%, is it for the making fusion networks or for the computation?
Yes, thank you for the nice question. So what I was showing was kind of a toy architecture. And I was showing the total probability of erasure. So that includes unsuccessful fusions and loss and nonsense measurements like multiphotons. It includes all of that in that 10% that I was showing. But that's not the actual architecture we're using. So I don't actually know exactly what the different levels of error correction, like of error tolerance are in the newest architecture. I just know that the architecture team can simulate directly the components. So I know the specification on fiber to chip coupling, for example, directly. But I think they add up to something like, something like 10%, I think, in total, like if you put all the losses. But there's a lot of components that a photon has to go through. Yeah, something like that. If I can definitely check what the exact number is and let you know. And if I'm allowed to
one more question here.
Go for it.
One more question.
Yeah, and usually the chip, its size could be about 1 inch by 1 inch chip.
Yep.
And within the one chip, how many resource states can make?
So a resource state generator is many multiple chips. So I think you can make a Bell state, an unheralded Bell state on one chip. And then you need to multiplex your successful Bell states. And then you need, I forget, but some large number of those to make a resource state generator. So the resource state generator is already a pretty big machine. But the thing is, once we have that, you just put a long fiber on it and make a logical qubit.
Okay, thank you.
That's a good question.
Thank you, Mia. So let's move on to the next session. Let's thank speaker again. There's a remote up there. Oh yeah, that's a new one you can take. So let me introduce our next speaker. Professor Tim Tamniau is a group leader at Delft University and QTech in Netherlands. Many of you already know it, which is it's world-leading research institute in quantum information science and technology. He is an expert in the field of diamond color centers, including nitrogen vacancy centers. Especially recently, over the many years, he pioneered the controlling of nuclear spins near diamond color centers, which allows the 2-qubit gate operations deterministically. Also, he achieved a very long coherence time of keeping quantum information safe. His pioneering works has really extended the functionality of MV centers to a much more advanced level. So please welcome the speaker. And we have our panelist, Dr. Dong-Yeon Kang from the Korea Institute of Science Technology, who is here with us. Okay, Tim, the stage is yours.
Okay, great. Thanks. It's really a pleasure to be here, and this has been a very fun conference so far. Actually, it's also really special always for me to come to Daejeon. Actually, I have a long history with this city. So if you look at this map down there, Kais, that's where we're right now. I actually came to Daejeon for the first time about 20 years ago. And then I spent some time here at the expo, right next to where we are right now, playing competitive computer games. Here's kind of a semi-embarrassing photo of a young me at that time in Daejeon. Sometime later, I then also actually worked at an institute around the corner here. I did an internship there for about 6 months at the Hanguk-gi-ge Yongu 1. And I apologize for my terrible Korean by now. It's been about 20 years. But yeah, it's always a pleasure to be here. And as you can see, this neighborhood is almost, I'm almost a local to this. Okay, so on to the research. One of the main goals of QTech and Delft and also my research group is to realize quantum networks. So what we have are these kind of nodes that contain multiple qubits that can process and store quantum information. These qubits, these nodes, can then be linked together using optics, using photons. Now, in this particular talk, the qubits are going to be spins in diamonds, and in particular associated to a defect called a nitrogen vacancy defect. I'll show a bit more about that later. But it's important to realize that there are many systems that can fulfill this role. People are looking at other defects in diamonds, for example, the Silicon Vacancy Center, which our chairman did a lot of pioneering work on. Defects in silicon, silicon carbide, but of course also things like trapped ions, trapped atoms, etc. Okay, why do we want to build these kind of quantum networks? The motivation here is kind of threefold. So the first is that this is a way to build large quantum information systems. For example, one can think about doing distributed quantum computations and simulations. And you saw on the previous talk, a key idea there is that if you can have these optical interconnects between small modules, then this gives you a kind of modular architecture with some inherent scalability. Now second, because these connections are made using photons, they can go over long distances, we can use the same systems also for long-range quantum cryptography. And finally, another point that I think is important is that we have not yet really had control over large extended quantum systems, both in number of qubits, Hilbert space, as well as extended in space. And we can use this for fundamental tests of quantum mechanics. And perhaps at some point we might run into some surprises there. Okay, I want to say a little bit more about this distributed quantum computation, because that's also something that my group particularly focuses on. So, the idea there is to get some scalability through modularity. So by making a very good module containing a certain amount of qubits, and then making many copies of these and connecting them together to build a large system. And that is one way to sidestep the challenge of cramming ever more qubits on a single chip. There's some other reasons why this is appealing. Right? So if these systems are optically connected, you can think of them as rather independent. And you start to have a natural way to get rid of errors that are correlated between the qubits. This can be bad for error correction. But also things like crowding of wires and fan-out and heating kind of problems. And finally, one thing that's nice of this kind of network or distributed architecture is that you're not necessarily limited to simple topologies. Right? These optical connections are flexible. They can go in 3 dimensions. You can even reconfigure them on the fly. And that means that, for example, you're not limited to something like the service code. Right? So now if you see this, this picture over here, you might recognize this as a piece of a 2-dimensional service code, as we've seen in the last talk. But in principle, we can also build these systems in 3 dimensions, have long-range connections, and change them. And that means that you can think about implementing the whole zoo of types of error correction codes that are out there and that are still being discovered. And at least from an academic point of view, I think that's very, very interesting. Okay, so the question, can you really build a large-scale quantum computer in this way? We don't know yet. But we've started a large-scale collaboration with industry, with Fujitsu, a Japanese company, essentially to come to a blueprint of how you could do this in large scale. And as you can imagine, and you've also seen in the previous talk, these are serious engineering problems. Okay, how would you run error correction over such a distributed way? So now logical qubits are spread out over this network. For example, in this case, there will be one physical qubit that is holding the quantum states that we're doing the calculations on in each of these nodes. And then we have to perform these stabilizer measurements, but now distributed over the network. So you saw in the previous talk these kind of ZZZs and XXXX stabilizers. How do you now do this if the qubits are in different nodes? The trick there is to first generate resource states, entangled states. So you generate an entangled state spread out over 4 of these nodes, and then you consume this as a resource to perform the measurement. Very simply put, you can think of an entangled state, like a G at Z state, of 4 ancilla qubits, as they essentially act together as a single ancilla qubit. Yeah, so the trick here is to all the time distribute entangled states between spins over the network, and then use this as a resource to kind of drive the error correction in computation. That's the difference from this kind of more monolithic service code. Okay, you see there's also some extra qubits drawn in here. Essentially because these entangled states are resource states, we can try to make them in various ways. We're allowed to use tricks like error detection. If we don't like one because we think it's bad, we can throw it away. We can do things like distillation, and that's why there are extra qubits in here to perform distillation processes. Okay, in this talk I'll focus on how can we actually control many of these qubits in one such a module. But I also want to first show you a little bit about the optical connections and show you that this is something that we can do and that has been working and we've been demonstrating. So how do I connect 2 spins that are some distance away from each other using photons? Here you see a picture. It's the same process that also Tony Yassine showed us yesterday. We take these 2 spins. On both cases, we locally entangle them with a photon, so we generate spin-photon entanglement. For example, here, if the spin state is 0, a photon is generated early. If the spin state is 1, a photon is generated later in time. Some sort of time bin entanglement. We interfere these 2 photons on a beam splitter, after which we fundamentally not know anymore which photon came from which spin. And then a measurement that, for example, gives us 2 clicks, projects the 2 spins in an entangled state. Now, one thing to keep in mind here, that this is a probabilistic process. Photons tend to get lost, detectors are not perfect, but also the linear optics interference here on this beam splitter is fundamentally probabilistic. However, that's not much of an issue because the process is heralded. So when the detectors click, we know we have this resource state, and we know that we can now deterministically use it to drive our computation. Yeah? So you can kind of repeat this until success if you want with extra distillation kind of steps. So it's all the time running in the background, generating these states. You know when you have them, and then you can deterministically use them. Okay. A nice example of that is that the experiment shown here, where we generated an entanglement between one NV center in a diamond in the physics building of the Delft campus, all the way to the left, and one in a nuclear reactor about 1.3 kilometers away on the other side of the Delft campus. We then used this to perform a so-called loophole-free bell test. If you've seen yesterday also a motivation of why that is interesting. For this talk, I think the takeaway message here is that this shows we can make these optical connections with fairly high quality and even over long distances. If you then start thinking about how I build larger systems, there's kind of like 2 things that you want to do. You want to be able to connect more nodes together. That's what you see here, an experiment on the right. This is from the group of Ronald Hansson, a colleague of mine at QTech, where they then first make entanglement between 2 defect centers, 2 NV centers, between Alice and Bob. Then they swap this state to additional qubits. These are going to be nuclear spins. And then make another pair between Bob and Charlie, and then you can fuse this entanglement together. Another trick that is important is this entanglement distillation, so ways to kind of overcome imperfections. For example, by generating 2 entangled states and then fusing them together in a higher fidelity entangled state. And the kind of take home that I want to give here is that to build these kind of things, at least on the qubit kind of level, there's really two things that we need, right? We need to be able to distribute entanglement fast and efficiently. So there's a lot of research going into putting these systems in optical cavities, doing better integrated photonics, and also looking at defect centers that are better at these things than the NV center, and to be able to generate this entanglement really fast and well. And second, we want multiple qubits per node, and we need to have high fidelity control to be able to do things like error correction in the end, right? So one will end up with with thresholds that are in about a 0.5% range or so for this architecture. And that means that we need high fidelity control over multiple qubits to essentially build larger networks and play tricks like distillation and error correction to ultimately overcome errors and get to this very low logical error rates. Okay, in this talk, I'll focus a bit on the second one and show how can we control a bunch of qubits and what can we already use them for. Okay, so here's an outline. It's a little bit ambitious, so please stop me if time runs out. I'm not entirely sure when we started. First, I want to introduce the nitrogen vacancy center and the qubits associated to that. Then I want to show how we can use one of these NV centers and kind of turn it into a little 50-qubit quantum node processor simulator by controlling nuclear spins that surround the defect. And then finally, as a kind of like near-term application, I want to show that we can then use such systems as a quantum simulator to look at some many-body physics called a discrete time crystal. This is kind of like a new out-of-equilibrium phase of matter for interacting many-body systems. Okay, let's start with the defect. So we have the carbon lattice in diamond. We replace one atom by a nitrogen atom, and one atom next to it is removed, a vacancy. So we have a nitrogen vacancy. This captures some electron spins. They form a spin-1 system. Usually we just use 2 levels, so just think of it as a little qubit. This is then what it looks like in the lab. Unfortunately, it's actually a really old picture, but the idea is still the same. So you have a little diamond wired up on a chip. We typically work at 4 Kelvin. For the NV center, you have to be around 10 Kelvin or below for the work that we're doing. If you zoom in a little bit more, you see here the diamond, little few millimeter large chip. If you look closer with an electron microscope, you see this kind of pictures, where the gray stuff is the diamond, and then we kind of sculpture with a focused ion beam a half sphere out of the diamond. And that is really just to get the light, the photons, efficiently out of the diamond. Right? Diamond is a very high refractive index, so you can get a lot of total internal reflection, but if you make a sphere, you exit everywhere perpendicular, and you stop reflections. Okay. See then control lines like to send through microwaves that they control the spin, and also gates that can tune the wavelengths of the emission, so the optical, the photons. Down there you see your fluorescence image, so you scan a laser over the sample. You see this ring, that's the solid immersion lens, and in the middle you see one bright spot, so this is one of these NV centers fluorescing. Okay. So what's the most simple experiment you can do? Well, you can prepare the spin or qubit, for example, in spin up, apply a microwave pulse of varying lengths, and this coherently rotates it from up to down and back up again. Yeah, so that's kind of to show that you have a qubit. You can see that's pretty fast. You can flip it in about 10 nanoseconds or so, and with quite high quality. So what is nice about the system? What is one of the reasons that we really dug into this one and to try to figure out and use it for a lot of things? So one thing is that this system is amazingly well, it's a solid state system, right? It's in a diamond, but it's amazingly well isolated from its environment. So one way you can see that if you perform a so-called T1 or a relaxation measurement. So you just take the spin, put it in one of its eigenstates. In this case, there are 3 eigenstates. Let's say you put it in spin up. Now you go do something else, go have a coffee, and you come back and you check, is it still there, right? Is it still pointing in the same way? And you can see that we measure after 10 minutes some decay seems to be occurring, and the T1 relaxation time here is about order of an hour. Actually, we're pretty sure that these are our lasers and our setups drifting, not the spin relaxing, so it's likely even much longer. So what does it mean? It means that the physics is really isolated from the solid state matrix. Right? You can almost think of it as a diamond not being there. It's a very clean system, and that means that we can hope to control and understand it to a very high level of detail. Yeah? Things can get pretty complex if you have many spins, but the physics is just spin-spin interactions. Right? And that we can hope to control and also understand very precisely, and I hope I can show you some examples of that. Okay, one nice example there is if you look at the coherence of the electron spin qubit. So what is it limited by? Well, the diamond consists of carbon, and naturally 99% of carbon is carbon-12, it has no spin, but 1% is carbon-13, that has a spin, it's also a quantum bit. And those nuclear spins in the environment, yeah, they can take some random states, they're like little magnets, they create a fluctuating magnetic field on the NV center. And that dephases it, right? So changing magnetic field, change of energy levels due to Zeeman shift, pick up a different phase and lose the phase. So if you do a simple experiment, like a Ramsey experiment, where you bring the NV center in superposition, you let it evolve for some time, it will pick up a phase that depends on the state of that environment. If we do it a little bit later again, some of the spins in the environment might have flipped, we pick up a different phase. And if we integrate that over some period of time, you see that you lose the phase coherence. In this case, in just about 5 microseconds or so. Right? It's not terrible for a solid state system, but it's also not really long for what we want to do. So what can we do? We can play a trick, and yeah, maybe you saw the talk of Paula this morning. You can apply something called a spin echo or an echo. Right? So now we apply an additional pi pulse in the middle of this evolution time, and it inverts the spin. Just think of it as inverting the interaction with the environment, or in some sense inverting the environment. If we now have the same time before and after that pulse, and the environment is static, it cancels out, right? Independently of what it is. Now this only works if things are kind of static, but if they're slowly varying, what we can do is just apply many of these pulses closer to each other, and in this way average out the interaction. So we decouple the spin from its environment. Now this works, I think, amazingly well. Right? So here you see some data. It looks a bit complicated, but at the top of this graph, the coherence is protected. The bottom, your qubit is gone, it's lost. And if we apply more and more of these decoupling pulses, you can see we can extend the coherence longer and longer. So this is on some log scale. If we go to about 10,000 pulses, we extend the coherence to 1.5 seconds for the electron spin. Yeah? So with just flipping the electron spin around a bit, we extend this coherence by 6 orders of magnitude. So we can decouple the interactions with that environment very well. But how do we get more qubits? What I will show you now is that we can actually also selectively couple the electron spin to individual nuclear spins in the environment. So in a very cartoony way, we're going to flip the electron with some frequency, and we're going to control and detect that spin down there. Just think of this as a 2-qubit gate, CNOT gate. And if we do it with a different frequency, we target a different spin. Okay, first a classical picture of this process. This comes from like AC sensing. Earlier today, Paula gave a very good introduction on this. Essentially, the idea here is that if I have some sort of static field and I apply this train of inversion pulses, I will decouple it. I will average it. But if something in my environment actually oscillates with exactly that period, now I kind of rectify the signal. And that means, if I now think about a carbon-13 nuclear spin and it's in some superposition, it will process Zeeman in just Zeeman precession with some frequency. And that creates an oscillating magnetic field on the electron spin. And if I flip it in tune with that, I can selectively pick up that signal. Okay. So here's a similar experiment as you saw before, but now with much higher resolution. Before you kind of saw only the envelope of this. So here we apply 32 of these pulses, we sweep the time between the pulses, and we see what kind of signals we pick up. And you see there's a lot of stuff going on. I'm just going to zoom in on the first few microseconds here in the beginning. And you see there a signal with very sharp dips in the coherence. So this is the electron spin qubit getting entangled with individual nuclear spins in its environment. Right? And because it's getting entangled, it's losing its coherence. Now, if you just stare this at a bit, or you give this to a PhD student, it's really easy to see signals from about 7 or 8 of these individual nuclear spins. You might think there's many more, but note that the signal is always periodic, because if I can fit in half a wavelengths, 1.5 wavelengths, 2.5 wavelengths, I rectify the signal in each case. One nice side remark here is that we also threw this kind of data to a machine learning algorithm, together with Do-Hoon Kim at Seoul National University. And they took out of this kind of data then about 30 individual nuclear spins in the environment, and they're coupling to the electron spin. Now, of course, unfortunately with machine learning, we don't know if that's actually true. But I will show you later that we have different types of measurements to really get all that information. And it turns out that also from this simple data, the machine learning can actually detect a lot of individual spins in the environment. So the outcomes also match the more advanced experiments I'm going to show next. Okay, this was a classical picture where you're kind of sensing some classical signal, right? Some oscillating signal. That's of course not what's going on, right? It's a 2-qubit interaction. It goes both ways. So the key idea here is that actually the nuclear spin evolution depends on the electron spin state. I just want to explain it in a simple way. So if we have the electron spin in the MS0 state, it's like it's not there, right? It's non-magnetic. So now all the nuclear spins precess around the z-axis, which is the applied magnetic field. But if I flip the electron spin, I invert it, it becomes a little dipolar magnet. It creates a little magnetic field on that nuclear spin. It now changes its precession frequency a little bit, but it also tilts the precession axis a little bit. Okay, now maybe you can see if I have 2 precession axes that do not commute, and they're not parallel or anti-parallel, I can rotate anywhere in 3-dimensional space. So I have complete control over that nuclear spin. Because that tilt is small, this is it's kind of like a resonant process. To build up any significant rotation, I have to time the flips very precisely. And that means that it's selective. The other nuclear spins, they feel a different magnetic field, and they are not sensitive to this same control sequence. Okay, and finally, because these 2 axes do not commute, the order matters, so I can build 2-qubit gates or entangling gates in this way. It turns out if you just flip the electron spin periodically, what you're doing is you're creating a controlled rotation on the nuclear spins. Okay, just think of it as a C0 gate, your 2-qubit gate. And that's kind of the workhorse for us to use these, to detect and control these nuclear spins. Okay, I won't go into too much detail here, but kind of as a little bit state of the art of what we can then do. Here is an example of a recent paper from my group where we then use 7 of these spin qubits to show the fault-tolerant operation of a logical qubit. And so the last talk you saw a lot about error correction, fault tolerance, and etc. So the idea here is that we ask ourselves the question, what is the smallest number of qubits that we can use to build a logical qubit that is fault tolerant? And where fault tolerant in this context means that if any single component of the system fails, if any single component of the system fails, for example, a single qubit gate, 2-qubit gate, a measurement or initialization, or an error on any of the qubits, the logical qubit information is recovered. When we started that, we actually didn't know the answer to how many qubits we needed. We thought it was 10. Actually, quite interesting, in 2018, I think beautiful theory work came out from Chow and Reichert that show you can do that with just 7 qubits, using something called flag fault tolerance. I won't explain it here, but yeah, I think this is actually quite cool. Okay, I'm just an experimentalist, but for me it's quite amazing that in 2018 we still discover a very big surprise about very simple quantum error correction codes after 20, 30 years of intense research. So what could we show? We could show that we could encode a logical qubit over five spins. Those are 5 qubit codes, the smallest code that can detect any error on these data qubits. Then fault-tolerantly perform gates on them, operate on it, and also perform the stabilizer measurements needed to detect the error syndrome in a fault-tolerant way. Right? So that also, for example, on the ancilla qubit and so, there can be errors. Okay, so I think that's just an example of how we're trying to push towards where we're starting to operate on logical qubits on the long path of ultimately overcoming imperfections using fault tolerance. Now I want to talk about how can we actually then detect and control many of these nuclear spins. And I want to show you that we can do this now up to about 50 of these nuclear spins, 15 qubits. Okay, what's the idea? Before we were looking at the electron sensing the signals of the nuclear spins. This is actually quite a little bit difficult to interpret because you need to understand your electron spin very well. It has a complex wave function. Yeah, I drew it as a dipole. That's not entirely true. It's kind of delocalized a bit. So that information is difficult to interpret. So instead what we're going to do is we're going to look at the nuclear spin qubits interactions. Right? So the coupling between the nuclear spins. And we're going to measure those. And those really reveal the interconnection of all the qubits in the system. And we can transform this back into the three-dimensional structure, where they all are in space. And that gives us a really neat kind of shorthand notation of our entire Hamiltonian. Okay. The clicker stopped working. Maybe we're out of battery. Yeah, none of the buttons do anything at the moment. Yeah. Point in a certain direction? Or?
It was the video problem, so now it's recovered.
Oh, okay. Yeah. It was only the projector that didn't work. Let's see, where were we? Okay, this is a story backwards. I assume you didn't follow that. Right. So what we want to do with this is to characterize this quantum processor or network node, or we can also use it as a simulator. There's a bonus motivation here, and that is that we're also working towards doing kind of atomic or nanoscale magnetic resonance imaging in this way. Right? Now imagine we can take that defect center, the MV center, put it very close to the surface, put something interesting on top, and detect where all the atoms are in the same way. Right? And the dream there is kind of to think about maybe a biologically relevant a molecule or protein and ask the question, can we really image individual molecules magnetically? Right? NMR, MRI are very powerful techniques, but they are very much ensemble efforts. Okay, that's a very hard problem. There are beautiful theoretical proposals out there. What this talk will add to that is that we're showing some methods and testing them on spins in the diamond that might allow you to also do this at samples outside of the diamond. Okay, what are we going to do? First, the simplest experiment. We're going to take one of these nuclear spins, the one that's encircled there, bring it into a superposition and let it evolve. So you can ignore the kind of pulse schemes. The first part is just to prepare some state, then we let it evolve, and then we detect its state using the NV electron spin. If we do that in the time domain, you see some complex evolution. You can make a Fourier transform, a complex spectrum. We stared at this for a long time. Master student tried to figure out, like, okay, what's going on there? It turns out it's too complicated. We see that qubit coupling to all the other qubits in the system, right? There's order 50 or so that it interacts with, so that's like 2 to the power 50 kind of couplings. There's millions of spectral lines in there. We can just not resolve anything here. We just do not have the spectral resolution to see all the qubit-qubit couplings in such a picture. So how do we enhance resolution? We have to enhance the coherence. Right? If we can let the system evolve longer, it becomes a more precise probe of the interactions with its environment. So what we do is, we apply again a train of pi pulses. We decouple now this nuclear spin qubit from its environment and extend its coherence time in the order of tens of seconds, which you have shown up to various minutes in other work. And that makes it a very sensitive probe to its environment, except that in this case we actually have decoupled it from everything. So we get no signal. So what we do is we apply another pulse sequence on one of the other qubits and we flip them both together. Right? So now we decouple them both from the rest of the system, but keep the interaction between them. So now this oscillation you see here is a two qubit interaction. It's like a C-phase a gate, a very slow one in this case. It takes about a second or so to do one C-phase gate. Not useful for quantum computation, but interesting for the physics and characterization of the system. If you look at the Fourier transform, so you see now two peaks, right? So one is the frequency of qubit A if qubit B is up, and the other one is the frequency of qubit A if qubit B is down. Now we took a bit of an extreme case here. These spins are far from each other. They couple with only half a hertz, but you can see we can really detect and control that interaction with very high spectral resolution. So about 80 millihertz here, and we have microhertz kind of precision in these measurements. So we can map out all the interactions between the qubits in the system very accurately. Okay. What do? We just sweep all the parameters to find all the frequencies at which the qubits live and how they interact with all the other qubits. Okay. Gives us a large three-dimensional data set. It's highly overdetermined because there's 3m, where m is the number of qubits, coordinates, right? X, Y, Z for every qubit. But the couplings go quadratically. So we have a very highly overdetermined system. We can invert this, so you can write a computer program to find the spatial distribution of the spins that matches that data. That's what you see here. So on the left you see the spatial image. So it's pretty small, right? It's just 3 by 3 by 3 nanometers or so where all these qubits live. In this case, there are 27 of these nuclear spin qubits. We can get some idea of the uncertainties on these spatial coordinates. So in the other graph you see a fit uncertainty on the 77 spatial coordinates of the system. And you can see this is all well below the diamond bond length and often even deep sub-angstrom. So we think that we know with very high precisions where each of the atoms are. Okay, here you see a three-dimensional picture of this same system. If the operators could press play, we'll see that's a video. So what you see here is the white balls are carbon-12, right? They're boring, they're just the diamonds that hold the system together. The yellow balls are these carbon-13 atoms that we can detect and control. And we do all that through that electron spin, which is trapped there at the middle at the Neisner vacancy center. Okay, this is not a computer model, but a model that the students went and built with these nice stick and ball things. I believe this took them about a full day, including having to write a computer program to help them. So these are about the 3,000 atoms for this quantum processor that at that time we knew the isotope of. I promised you would go larger, so how can we extend this further? Let's say to 50 of these spins, 50 qubits. And for that I want to change the picture a little bit and think of the network of coupled spins also as a kind of network, like you see there in the bottom. So what we've been doing is apply the pulse sequences to detect the connection between two spins. So the nodes of the network here are the frequencies, and then we measure the couplings. Right? And in principle, what we want to do is map out all these couplings. Now, if each frequency, each node contains only one spin, then I just have to get all the pairwise interactions, and then I characterize the entire system. However, due to the physical nature of the system, once we go larger and larger, farther away from the NV center, the qubits become more similar in frequency, and we get spectral crowding. Essentially, multiple spins share almost the same frequency. And that means that if we measure a coupling here between A1 and A2 and A3 and A2, we do not know a priori if these are two spins coupling to the same spin or to two different ones. Right? So the problem becomes ambiguous, and this is very annoying if it becomes very large and ambiguous. So can we do experiments that remove that ambiguity? And maybe you can see it in this picture. The key idea is to measure spin change through the network, to correlate many couplings together. Why? Because then we can see if we have the left picture, where the system connects, or the right picture, where it doesn't connect through that node. Yeah? So that's the trick here. I'll go a little bit quick. So what we can do is concatenate these kind of pulse sequences and build complicated experiments where we essentially measure change through this network of spins, where we use every time the next spin again to explore its connections to the network, find a new connection, and use that spin again for, to probe its connections, etc. So this does two things. One, it allows us to move away farther from the NV center by creating a chain of spins. And two, it resolves this ambiguity problem because now one of these spins is not just defined by its frequency, but it's defined by how it connects to this kind of change. Right? And for example, this chain is very likely to be unique, even if there's some probability for multiple spins to have the same frequency. Okay, a little bit of technical story, but then finally what we can do is you measure this kind of change. Let's say this is an example. And now we can identify that pieces of these chains have overlaps, and we can then hypothesize that that means that we need to fuse them together in our solution. And in that way you can map out the network and get the connectivity of the system. Okay, so we do that, right? We measure this long change, we merge them together, and then in the end we use this positioning algorithm both to fill in all the pieces that we don't have, that we didn't measure, but also to validate the solution. Right? Essentially because the system is so highly overdetermined, either it will spit out, I can't find the solution, you made an error in how you fused everything together, or it will tell you, okay, this must be it. And here you see then for 50 of these nuclear spins surrounding an NV center, a visualization of their network. So how all the spins connect together. And essentially what we know now is then, this is a full reconstruction of all the 1225 2-qubit gates in the system. Yeah, so that gives us a very high level of knowledge about what's going on there. In principle, we could add another 2,000 atoms to this module. We didn't do that because it's hard work. But we know now for the closest 5,000 atoms which ones are the locations of the 50 qubits. Okay, why is this exciting? So one is that we can use these systems as quantum processors or nodes for quantum networks. Now, I don't want to give you the idea that we're going to control all those 50 spins with the kind of really high fidelities, threshold fidelities, let's say 99.9% gate fidelities that are needed for error correction. When thinking of this system for quantum error correction, quantum computation, think of it like this. Take the closest 5 to 10 spins that couple strongest with the electron spin. Those are the ones we can control best. The other 45 are actually what is causing our noise. And now, because we can both control and characterize that noise environment to a very high degree of precision, we hope that we can use that to get the gate fidelities from the current, let's say 99 something percent to the 99.9 and higher level. Yeah, so it's for quantum computation, think more about as a very precise characterization to develop precise gates. If you think about quantum simulations, you don't need this super high level of control. And there this then really does give you a controlled platform with 50 qubits that you can use for simulating many body physics, and perhaps also problems from graph theory or network theory. Right? You saw that we solved this by actually using some tricks from network theory. This is also something that we might be able to do quantum simulations of. And finally, there's this last motivation of that this is a nice method for atomic scale magnetic resonance imaging. It can be image complex unknown spin structures. Okay, I think there should be about 10 minutes left or so. Okay, so yeah. So we'll try to get through the last part. So this is now a little bit change of gears, but let's think about, can we already do some interesting quantum simulations with such a system? And in particular, something called a discrete time crystal. So what is the idea here? We're now going to use this coupled system of spins as a programmable quantum simulator. Right? What is nice here, we have individual control over these spins, and in principle we have a universal gate set, universal control. In principle you can make whatever you want. Obviously some things are going to be easier and some things are going to be harder and some things are going to be near impossible. So we'll pick first the problems that map naturally well on this kind of simulator. But in principle, by using echo pulses, you can select groups of spins, turn on and off interactions, and control the system. Okay, and then the first problem we thought was interesting to crack with this is to look at time crystals or discrete time crystals. So what is going on there? Think about a normal spatial crystal, right? So what happens there is that space itself has a continuous translation symmetry, right? There's no periodicity in space inherently. But if I take a bunch of atoms that interact together and I put them together, they form this crystal, like a diamond, like a spatial periodic pattern. And this is really like a phase of matter, right? It's stable to small perturbations of the parameters. And so we say that spontaneously breaks the underlying symmetry of space. We spontaneously get this periodic pattern even though translation is continuous in space. Now a discrete time crystal is something similar. So now we have a system that spontaneously breaks time translation symmetry. So think, for example, of a system that is periodically driven with some period, right? So its Hamiltonian underlying symmetry is periodic with some period, but now it reacts or responds with a different period. And we're not looking to some sort of fine-tuned solution there, but you want to see that then forms a stable phase, right? So that it oscillates with that period stably and is robust to small changes of parameters. And colloquially put, if you have such a system, it would be, and if it's perfectly isolated from its environment, then it would, and it's infinitely large, then it would form a new kind of phase of matter. It would spontaneously oscillate with that period forever without absorbing any energy from the environment. Okay, now maybe you caught the isolated system and maybe you think, well, wait a minute, isn't that trivial? If an isolated system, it will oscillate forever. So it's a little bit more subtle like that. So let's think about a perfect pendulum that cannot lose any energy to the environment. You might think if it oscillates, it will just keep going forever. That's in principle true if it's truly like a single mode system, right? However, if you think about a real pendulum, at least in theory, it's a many-body system. It consists of many atoms. So what will happen is, even though it's isolated from its environment, the energy will spread out over the system. And for example, for the pendulum, it will ultimately come to rest with all the other vibrational modes and all the other modes of all these atoms being populated. I shouldn't say it comes to rest, it comes to almost to rest. It will still oscillate a little bit. Yeah, so it's this problem that we're considering here. So a many-body system, a complex many-body system, that in principle you would expect to thermalize, right? But now we're looking for a discrete time crystal, which is then a phase of that system where it will just spontaneously break this symmetry and oscillate stably, in theory, forever. Okay. So what we have is a quantum many-body system that is strongly interacting. We periodically drive it so that we create what we call Floquet Hamiltonian, so something with period t. Then the discrete time crystal breaks that discrete time translation symmetry. So it responds, for example, with a period of 2 times t. We want this to be a phase of matter, right? If we change the parameters a bit, it should stay stable. And that's really the challenge, because how do you stop the system from just absorbing energy from this periodic driving and heating up to some infinite temperature, right? Essentially going to an entirely mixed state. Now, the only real answer we know to that is something called many-body localization. So this is, if we consider the situation of a quantum system with disordered interactions in low-dimensional systems, the hypothesis is that something called many-body localization can occur, where the interactions stop the system from thermalizing. Right? So these interactions, they break the ergodicity. It is, I think, if I understand correctly, still an open theoretical question if that really exists in some sort of asymptotic long time limit for large systems. And also if it exists, for what dimensionalities and kind of interactions it exists or doesn't exist. That theoretical discussion seems to be playing on timescales that are, it looks like, beyond what is experimentally accessible. Perhaps forever, maybe there will be breakthroughs in the future. So that's just to say that we are not really sure if this many-body localization exists, if it would be compatible with our system, but I will show you in the end that we see signatures that, that match these ideas, at least in small systems on limited timescales. Okay, so what we do is we make a one-dimensional spin chain, because that's where many-body localization might happen. So we take 9 of these spins, we flip them together to decouple them from their environment, but keep the interactions between them. And what we did here is we just wrote a computer program to, within our subset of 50 spins, find 9 of them that happen to couple together with a certain matrix that actually makes them approximately like they're on a one-dimensional line. But then with disorder in the interactions. Okay. So here you see how the 9 spins interact. And these are the kind of systems that you would theoretically expect to see, at least, signatures of many-body localization. Okay, so how do we then program this discrete time crystal? Here's the sequence. We initialize the system in some way, and in the end we read out all the 9 spins in some way. In between, we apply this flow case sequence. And it consists of 2 elements. In the middle, you see inversion pulses, where we invert all the spins. Now, we don't do this perfectly. If we would do this perfectly, you get a trivial solution, right? If I invert all the spins periodically perfectly, they would, after 2 periods, would come back to their initial state perfectly, and they would keep doing that forever. Right? So that's a kind of fine-tuned solution to this problem. That's not what we care about. Instead, we make these rotations not exactly pi, right? So we don't flip the spins perfectly. And of course, also in practice, there is a lot of noise on that, and there are errors, so we couldn't do it perfect anyways. So that's one parameter, right? Like how far from perfect do you rotate the spins? And that's what we want to see, that we're stable against perturbations. And then the other parameter is how long do we let the spins interact, right? If we let them interact longer, the interactions are effectively stronger. If we don't let them interact, there are no interactions. So that's what we kind of can use to map out the phase diagrams. So what you see here is we start with some imperfect pulses. If we have no interaction, and we prepare all the spins up, we look at the total magnetization, it just decays quickly, right? That's because everything just kind of randomizes rapidly. If we now let the spins interact a bit more, we increase the strength of the interactions, you see it starts to become a little bit more stable. And if we go through this phase transition into the discrete time crystal, now they start periodically oscillating for a long time. Yeah? So the interactions between the spins here make them all synchronize and oscillate together. Okay, if we want to know that this is really compatible with this idea of many-body localization, one thing that we have to see is that this eigenstate order kind of goes through the entire spectrum, and that means that all possible initial states, or at least, should show this behavior. There are other tricks you can play, and then for certain states it works, but then it doesn't work for all the other ones. So we want to prepare different states. So here you see all the spins up, and now you see how the spin states change over these kind of Floquet cycles. You see they all synchronize together and start flipping together. But also if you prepare them, for example, in this up-down kind of state, then you see the same pattern holding. Right? So we see this order both in time and in space. This we call some spatial temporal order, and it's a signature for this many-body localized discrete time crystal phase. Okay, so we did this then for another 11 random states that we selected. And you can see that if we plot the signal strengths, it does decay over time. The 1/e value is about 400 periods. And because the system is not perfectly isolated, right? In experiment, there will be some leaking. Maybe let me quickly say that there was at about the same time also beautiful work from Google looking into this, and then a bit later also people using the IBM quantum processor doing this kind of simulations of these time crystals. Superconducting qubits are a bit faster, so they can map out larger space. They can also use a little bit more qubits. Our advantage here is that the qubits are much more stable, live longer, so we could get about an order of magnitude more periods. Okay, why do we care about that? As a final graph, I want to show, let's compare to what we theoretically expect for this system. So what you see here on the right is the discrete time crystal signal simulating our spin chain, where we use 7, 8, or 9 of the spins. And what you can see is that it lasts for a very long time, million periods, and you also see it exponentially increasing as you add spins. Right? So that's the signature here of this many-body localization. Again, we don't really know if this continues. There are, I think, many hypotheses that somewhere at 10 to the power 50 or so this breaks down, but we don't really know how to get there. If we don't have this order, or we don't have any interactions, then we get this kind of red curve. Right? So the system collapses very quickly. Our experiment ends up somewhere here. So what does it tell us? Well, one, we can certainly distinguish this from cases where this many-body localization is certainly not happening. Right? And that's previous experiments did not get out that far. We can also see it's not anywhere near the theoretical prediction for the chain, and that's because we are limited by decoherence due to the environment. Okay, so that gives you some idea that we're showing the signatures of a many-body localized discrete time crystal phase of matter. But there are, of course, also open questions about if these things can really exist on asymptotic timescales. Okay, as an outlook, what do we want to do next? Roughly speaking, we want to bring these two things together. So this control over many qubits within one module and make the optical connections to start building larger networks for quantum communication, computation, and simulation. I'll leave you with a photo of the group. Here we're doing a very Dutch thing, sitting on a boat in a canal next to a windmill. Thank you.
Thank you, Tim, for the very nice talk. I really enjoyed watching your time crystal picture because it really shows the feature of the crystal, especially that alternating spins. So we're a little bit beyond the schedule, so let's have a Q&A session with the panelist, Dr. Kang.
Thank you for your nice talk and nice and inspiring talk. I am Dong-Young from KIST and Asian Lab of Korea, and recently joined to MB Information Quantum Information Sensor, Information System. As a panelist, I have a lot of technical and scientific questions to you, but as a panelist, I'd like to ask you one or two main questions. One is about scalability of your system. It's very amazing to characterize 50 nuclear spins. Then can you use those 50 qubits as computation via ambient center electron spin in a practical sense?
In what sense?
Like in practice, can you use that?
Yeah. So what about scalability, right? So fundamentally, the scalability here comes from this modular network idea, right? That's where you can think about going to really large amounts, but just making many copies. I say just, but it's a tremendous engineering problem, right?
Yeah, yes. But if long nuclear spin may have weak coupling, so.
Yeah. So the optical connections, that's where the scalability comes from. Within one defect and controlling more and more of these nuclear spins, I think in principle there are hardly any limits there because there are no decoherence processes that are really fundamental, like spontaneous emission or phonon interactions or so. We don't really see any of those. But in practice it gets harder and harder because the farther out you go, the more all the spins have a very similar frequency.
Yes, yes.
Right? Because their frequency is determined by how they couple to the electronic spin. That's the only thing that distinguishes them.
Yeah, that's right.
So it gets more spectrally crowded, and you can see that at least from a theoretical point of view, right? This is a no-go theorem for scaling, because the more qubits you want to control, the slower your gates have to get to stay selective. And this means that your error rates grow with the number of qubits. So you can't build a quantum computer out of one NV center. This is at least not in the way we are doing it. And that's also not what we're planning to do. We're planning to make modules containing order 10 nuclear spins per NV center, maybe couple various of them together, get to 50 qubits or so, maybe 100, and then say, now it gets too hard, just make many copies of that system and connect them optically.
Yes, thanks. And a related question, so for linking the separate NV center through photons, so you said in your talk, but it is desired to implement NV center to optical cavity, but as far as I know, it's not easy to implement NV center to optical cavity compared to other defect center. So can I get your comments about this using NV center?
Yeah, so you're right, right. So to scale to larger networks, the optical links have to be faster, also for practical reasons ultimately. And with the NV center, this means that you need a better spin photon interaction, and for the NV center, this means you need to put it in the cavity. This is difficult, right, as you say, because the NV center is very sensitive to electric fields. Doesn't like to be near surfaces, near nanofabricated structures. It might work with like large cavities, Farabi Pro kind of cavities. My approach, and also the approach that we're taking together in this collaboration with Fujitsu at QTech, is to look at different defect centers. The tin vacancy in diamond, which is insensitive to those electric field noise. And also the V2 defect in silicon carbide is something that my group works on, which has a couple of large advantages, one of them being also much less sensitive to that problem and easier to integrate into cavities.
Are you already working? Are you already working with the tin vacancy or another defect?
So yes, at QTech we work with the tin vacancy and the V2 defect in silicon carbide. The tin vacancy center is Ronald Hansson, my colleague, not me.
Thank you for your answer.
Yeah, we have a question from the audience.
That was an awesome talk. So when you do the pi pulses to either isolate or couple a spin to something else, what would be the difference if you just like continuously rotated it instead at some frequency?
Yeah, so I think the question is about how do you compare doing like a periodic pi pulses versus just continuously driving it. It's very similar, right? Maybe you can see that in some limit it's the same. It's kind of called pulsed dynamical decoupling or continuous wave dynamical decoupling. I think it is also possible to do such things. What we have seen in practice is that it's always harder, and people claim it's better, but in practice I've never seen it work with very high fidelity.
Thank you.
I think it's difficult because now your dephasing, decoherence, comes from amplitude fluctuations of your driving. Right? You're making a kind of dress qubit, and now your Rabi frequency and that's actually quite difficult to stabilize. Whereas for the pulsed cases, you can play all sorts of tricks where you use kind of error cancellations. So we're applying these pi pulses with phases so that pulse errors to first or second or third order get cancelled. And this is a bit more tricky for this continuous driving, I believe.
Okay, so let's move on to the next session. Let's thank the speaker again. Okay, our last speaker is Professor Robert Niffenegger. He's an assistant professor of electrical and computer engineering of University of Massachusetts Amherst. He, actually, I think among everyone I've seen, has one of the most interesting career paths. After he gets his PhD in quantum simulations with the Bose-Einstein condensate, he worked as a 7-nanometer integration and yield engineer at Intel and invented new metal gate processes. Afterwards, he came back to the quantum field and he completed his postdoc work at MIT. And during his work there, pioneered the application of integrated photonics to ion chips. Let's welcome Professor Robert Niffenegger.
Thank you. So it's very...
One second. Yeah.
Oh, sure.
Yeah, let me also introduce briefly our panelists. Professor Kim, are you there on Zoom?
Yeah, I'm...
Yes, Professor Kim, can
I'm
you...
here.
Yeah. Professor Kim is leading the effort of trapped ions in Korea. Professor Kim, can you briefly introduce yourself?
Oh, by myself. Okay. Hi, I'm Tae-young Kim at Seoul National University. As introduced, I'm working on the ion trap, and then what we are also doing is the fabrication of the ion trap. Yeah, so yeah, I think our interest also overlaps a lot with what Robert is doing. Yeah, so I'm quite interested to see him here.
Okay, thank you, Professor Kim. So now let's move on to the presentation. Bob, you can start your talk.
Thank you. So it's great to have the panelists online. We met at the North American Trapped Ion Conference just a month ago. So his work is featured in this talk. So all right. So hello, my name is Bob. I'm going to be talking about quantum computing with trapped ions today. I'm going to give an overview of where the state of the field of quantum computing is, where I think trapped ions are, and how photonics are hopefully going to help trapped ions move to that next echelon of scaling, which is very important. And then just a little bit about what I'm doing at UMass now that I've just started my own lab. So, just to motivate, remind us, Moore's Law is dead. I did have a chance to work at Intel. It's a very exciting place, and they're doing very exciting things, but it's just gotten very, very hard. And really, it's not that they can't do it, it's just very expensive, right? We're not willing to pay for the chips that they can make anymore. The economics don't work out. And unfortunately for everybody, computational demand has accelerated just at this moment, if you believe these AI extrapolations. So the world needs more compute. So what are we going to do? Just to give a sense of the problem we're dealing with Intel is dealing with. These are FinFETs. You can see they haven't changed a lot, but they keep getting smaller, and eventually we really will run out of silicon atoms, but it gets worse. If you look very carefully here, you'll see that the interface at the high K gate, that is already a few atoms, right? That is, the inversion layer is only a few atoms. It's already there, and then actually that's not the real problem. The real problem are the vias, getting that metal layer interconnects, and we should all appreciate here how difficult interconnection is for quantum computing, while it's also the issue for computational. So just some background, motivating why we have to do a little better. What's very interesting is Intel is actually pursuing spin quantum dots there. Jim Clark and Hubert George are doing great work there. And the idea is, if this is already a scalable platform, can we just use it to make qubits? And it's very, very challenging. There's tunability issues, control issues, but they're really making great progress. And one important thing they're pushing is being able to test things at not millikelvin, but 1 Kelvin, and do full wafer qubit characterization, which is very exciting. But it is very challenging. And if you look at the broader field of qubit candidates out there, I'd like to tell you ions are great. They start off with a lot of advantages that really it's the inverse problem, where an ion has atomic levels that are basically identical, pure, and everything, but there's no scalable platform for them, and everything else usually starts with the opposite problem, right? They're trying to fix the qubit. And so hopefully photonics is a bridge to meet those together. I won't, everybody's talk has really done a nice job introducing all these things, so I'll just keep going here. One way to compare quantum computers might be to ask how many qubits each system has, what the error rates are for them. I had to update this just last night because IBM had a very exciting announcement for 433 qubits and the new Osprey processor, which is very exciting. I don't know what the error rate is, so don't quote me on that. That's a guess. But they really are pushing forward. But you can see there's a noticeable gap as it goes to the number of qubits increasing and the fidelity increasing, right? So that's really where the field needs to go. And IBM themselves actually came up with a metric that tries to capture these things together as kind of a worst case scenario for an algorithm that might need a lot of computational resources and a lot of gate depth, and that's quantum volume. So it's not just the number of qubits, it's how many gates you can execute with them as well. And if you characterize this now, if you plot this data where you're using quantum volume as the metric, where depth and the breadth of the circuit matter, it starts to become a little more clear that ions have had a nice headwind to make some progress here. And the question is, how do we keep it going, and if it's possible? And for the moment, ions have enjoyed high connectivity, right? You can shuttle them around, or even within the same chain at IonQ, they don't need to move at all. But there's limits to this, and eventually we're going to run out. Whereas transmons and other modalities, they have they have to play a game of telephone often that has a cost on their overhead. Okay. All right, but a little more details. Why are ions so far ahead here? They have a lot of advantages. They're high fidelity, right? The high fidelity of the operations is extreme. 1 qubit gates are basically free. A very high fidelity readouts, state preparation and measurement. They have very long coherence times depending on the qubit that you're using. In fact, the ratio to the gate times is actually very favorable. They are identical, and this is actually very critical. You don't have to tune to them. They're always there. And you can move them around. And so again, connectivity is an important problem for quantum computers, and the fact that you can move them around without perturbing the qubit state directly, maybe indirectly, but directly, is very advantageous. And in principle, with laser light, there's very low crosstalk. So that's very nice. So this is what qubits look like, ion qubits. And in fact, this makes them already, these qualities make them the world's best clocks, which is very exciting. So we always have sensors. But they have many challenges, and not the least of which is that they are not in the solid state. You must catch them, they can escape, and they require many laser beams. And I'm going to go through all the operations that an ion needs to have to survive and have operations, and you'll see how many lasers they need, and each one needs to be addressed individually to an ion. Not a trivial task. And they're slow. So full disclosure, they actually have a pretty slow clock rate if you're going to just ask how long it would take to do some calculation with them. It's not nanoseconds, it's microseconds at best. All right, so what does an ion trap operation look like? Well, first you need to take some neutral atoms. You need to photoionize them. Usually this is a two-step process now. You can use laser ablation just to rip off that electron as you ablate it from a sample. Then you need to trap it in an RF trap and begin laser cooling it. So ion traps are just electric field traps that are oscillating like this saddle trap here. In 3 dimensions, you'd imagine these rods, but if you unfold these rods, you can actually make a surface electrode trap. And this was actually invented by John Ciavarini, who was the PI at Lincoln Laboratories while I was there. Very exciting. And the ion just likes to sit in the null of this electric field here. And then you can cap the ends of that trap with a DC field and just move them around and shuttle them, which is pretty easy. So this is what their traps at Lincoln Laboratories look like. There's RF rails in the center there, DC rails to tilt that slightly, and then DC electrodes that can move it left and right. If you look very carefully, you can look ahead. There's a fiber block attached to the end, which I'll get to soon. So there's been a multitude of these traps that have been fabricated, and they've done very exciting things. And they all show that there is a possibility to scale this architecture, right? It's just metal on the surface of a substrate. You can play a lot of tricks to move the ions around, and you can actually get very good densities. The problem has been that the lasers haven't come along for the ride. So you can have an electrode chip with a density where this isn't close to scale. You could have thousands, if not more, ions on the same chip, move them around with pretty good control with the digital analog converters, in-chip, et cetera. But without photonics, things get difficult. So that's what we'll get to soon. But back to ion trap operation. So once you've ionized the neutral atom, you have to trap it in that ion trap, RF Paul trap, laser cool it. So now we're doing a cycling transition on an S2P. You need some repump lasers to bring it back into that cycling transition. And once you have it there, you can begin your experiment where you do some initialization of the state, more state preparation of the ground state of the harmonic oscillator trap, then your qubit operations and detection, where you just take a picture. So qubit state operation, you're trapping it in a harmonic oscillator well. You need to do some laser cooling it. You're just going to take energy from it with a photon, where the photon of light from the laser just is detuned such that when it's counter-propagating with the motion of the ion, it's tuned into resonance, more likely to absorb. And this is kind of like stopping a bowling ball with ping pong balls. Eventually it works, but there's some tuning to it. And it's a very powerful technique used for Bose-Einstein condensates, neutral atoms, et cetera. And it works very well. But you can't quite get to the bottom of that trap. You still need sideband cooling to do that. So one example of a qubit, and there's lots of ways to slice an atom to make a qubit. One example that's actually better as a clock and makes it a difficult qubit is to use a metastable state. So here, this D state, if you do an excitation to it, the ion will actually persist there for 350 milliseconds, which in ion, or milliseconds, yeah, in ion time is long enough to do some things, and it very slowly decays. This also gives it a very narrow line width, and it's what makes it a good optical clock. But you can then do qubit operations on this, where here I'm just showing a spectrum of the carrier transition, where there's an electronic excitation but no motional ones, and it has motional sidebands, again, bring it up and down. And this is how you can do sideband cooling to get it all the way down to the ground state. Detection then, you just shine this resonant light you're using for laser cooling, and if it's in that shelved D state and it's sitting up there, it won't have any fluorescence, and so you can wait some time while you're taking a picture, and if you get no photons or very few, that means it's dark, it's in that shelved state, but if you get many, or at least more than the other bimodal distribution here, it's in the excited state. And so this is an actual picture of the ion. And then qubit gates are actually executed with laser pulses. So we take an RF pulse. So if you're kind of decompiling the circuit that's on the left, some Hadamard gates, controlled knots, those become RF pulses that then go into an acoustic optical modulator. It's a little quartz telluride oxide cell with a piezoelectric, and you just have a pulse of RF power that goes in there, makes a laser pulse that comes out with a shifted frequency precisely at that RF drive, and a sequence of these can execute qubit gate and qubit operations. Okay. So that's a breakdown, and I guess the important thing for you to grasp is that it's a lot of colors of light, and it's a lot of laser pulses, and each ion actually needs one. So this kind of gets pretty complicated pretty quickly. So we're going to need to figure out how to do this. Some more details about how 2-qubit gate works, just for fun. So if you have two ions in the same harmonic well and you want them to interact, they're going to interact pretty strongly due to their Coulomb repulsion within that well. And if you want to use an intermediate state to mitigate that interaction, you'll actually excite a breathing mode or some other motional mode where the first photon from the laser pulse that is absorbed excites a global mode for both, but it's only electronically excited one of the ions. Now the second photon that comes in kind of allows this to take both paths at once in a superposition where it's going back down to the state where neither were excited, they're both in that S state, or up where both are electronically excited. Either way it goes, it's back down to its motional ground state. And so that's kind of important for not introducing heat to the system, but this is effectively the Bell state pair that you're looking for, a superposition of the state where they were both in the original electronic state and they're both excited electronic states. What's very nice about this Molnar-Sorensen gate is that I've shown it only in one direction, but it doesn't actually have to be in the ground state. It can be in some excited motional state, and it still comes back to where it started. But it is susceptible to heating, so if there is a phonon that's introduced into the system while this gate is operating, it'll destroy the coherence. So kind of as an example, again, I mentioned that this metastable state is a very good clock. It's very sensitive, maybe not a good qubit. This is an example of a 2-qubit gate running on that transition. And you can see that a few things. So first, there's kind of this envelope that's going on there that's reducing the fidelity. That's actually from vibrations, right? So anything on the order of a wavelength of light of vibration will change the phase of the pulse and remove your coherence, which is very, very bad. And also on top of that, you can, if you look carefully at the fit from Q-tip inside there, this actually was 100 hertz off of resonance, and so it even had a little worse error. But it just to give you a flavor for what's going on. And with this, you can create a universal gate set. Ions have much better gates, and for example, actually a very recent paper showed that with microwaves, you could have errors that are consistent with 0. So they did 10,000 shots, and were able to have a data set where there was actually no error in that 10,000 shot set, which is very exciting. I think I think they were just kind of running out of time to publish, but I think they're working on getting this not to be equivalent to a 0 error, but it's very exciting. And in fact, other Raman gates have shown very low errors as well. So, all right, so we have ions with low errors. That's exciting, but what are the ways that we're trying to scale this up to larger systems? IonQ is working on a single chain of ions where each ion can actually talk directly to each ion in this chain, which is very favorable to scaling up to a certain extent until you get spectral crowding, which happens around 50, 60 qubits. Also, Honeywell or Quantinium is working on a QCCD architecture where, again, you have the ability to move these ions around and, in fact, split them, join them together, swap them, rotate them around, and kind of play a little game of shuffle until you get the ions or the qubits you want to have interact in the same well, do your laser pulses to have them have an interaction, split them apart again. And they've been very successful. This has been kind of a holy grail achievement for the field for a long time, and they're really executing this pretty successfully. Just for comparison, just to show that both architectures are doing well at the moment, this is kind of old data, I think, that was publicly available at the time, but they're pushing out their quantum volume really nice. So that being said, this is a long road, and so I think everybody's thinking about how to push this into further and further territory where, one estimate is that if you want to break a 2,000 bit RSA integer, you're going to need 20 million noisy qubits at the current error rates. And you can imagine, even with perfect ones, you need at least some multiple of the size of that bit integer you're trying to factor. Maybe there's some middle ground, but it's a long gap. And so this is a joke that a student at MIT made that I'll just steal. Jules Stewart said that he quoted the TV show Devs, which if you haven't watched it's about quantum, but it's also whatever. It's a show about, so this guy gets hired, he shows up at the quantum computing company, and he asks, how many qubits does it have? And the owner of the quantum computing said, a number that seems pointless to express as a number. And the joke is it's 2, right? So, because that's what we're kind of dealing with. So we need to get to that pointless number. So how do we do that? Yeah, and again, ions are pushing this down, so it's exciting. Well, it really comes down to, in a lot of ways, scalable optical addressing, right? We're talking about focusing laser beams to the surface of a trap, and Honeywell had a recent patent come out about their newest racetrack architecture, where you've got, in principle, they're going to have 2 parallel zones, and this should be okay to some extent for crosstalk. But the question is, what happens next, right? It's like at some point there has to be some 2D scaling, or maybe 3D, but there's going to be a lot of laser beams flying around. So how do we get around that? And not to mention really that optical laboratory is, a Rube Goldberg experiment of optical elements. We really need stable, integrated ways to lithographically define photonical wave paths. So I think that means integrated photonics. So while I was at Lincoln Laboratories, I got a chance to work on this project, again led by John Ciavarini there. And so this is a picture I took when I was doing some cryogenic testing of a fiber block attachment. If you look carefully, you can see these little antennae. Those are actually laser beams coming out of the surface of the trap. Well, I noticed this was happening when I was pouring liquid nitrogen directly on this poor chip to break it. And so, there's a little cloud of water vapor going over the top, so you can see the laser beams coming out the top. And the top view here, again, this is a Lincoln trap they actually designed for clocks. You can see there's multiple rays, multiple zones here with splitters, and et cetera, but passive photonics. So, what are these? Really, we're talking about taking optical fibers, putting them into a vacuum chamber, coupling them in to the edge of a chip in a fiber block. The edge of the chip will have tapered waveguides, inverse tapers, to try to match the mode with the fiber. Then the waveguides can route a single mode through into the chip. You can have splitters if you want, et cetera. And then you have a diffraction grating, which can not only diffract the light out of the chip, but also focus it in 2 dimensions by changing the period and changing the curvature. And so the goal really here is to have laser beams that are coming out at a very precise location for the ion. So again, at Lincoln, they fabricated all these. They have a very nice lithography tool capable of fabricating these very small critical dimensions, and doing it quite well. And here, this is a picture of the surface of the trap. You'll notice that now this beautiful trap has windows in it, and those windows are not very nice to the ion. They're oxide that can charge up. And one thing that they figured out to mitigate that charging was to put indium tin oxide over the windows. So here, 2 windows had deliberately omitted that indium tin oxide, and in the scanning electron microscope, you can see that those windows charge up quite readily. And in fact, that charging is a leading source of error on any gates that are trying to be executed on a chip like this, where there's large oxide areas exposed. So one thing I'm hoping to work on is studying how to improve this surface quality. So here's a zoom in of what that fiber block attachment is. This had to survive to cool down to 4 Kelvin. So again, you've got input tapers on the edge of the chip. You can see the fibers in the fiber block array held by a vacuum chuck. They go in, it's aligned via a loop back, so one continuous route of laser light goes in and out of the chip all the way around. And here we just epoxied it. It was kind of dirty, but it worked. We've since improved and made this a little bit more robust, but it did work. And this is what the laser beams look like if you take a series of images at different focal planes above the chip. You can see they all cross at a point. Unfortunately, it wasn't exactly at the RF null of the chip, but it was close. And so this is a reconstructed animation of each beam path superimposed together, where again, we're just translating the microscope to new focal planes. And then if you do a 3D reconstruction with MATLAB, I think using every function that exists, this is what it looks like. And you can tell that this is not a simulation, this is real data, because there's some higher order diffractions coming out of the side. So this is very exciting. This allowed us to demonstrate operation of all of the different wavelengths necessary for different operations, laser cooling, ionization, etc. It was a little high, but we were able to make it work. So yeah, photoionization, which we were a little worried that the 405 nanometer would charge quite readily, was not too bad. Doppler cooling, sideband cooling, qubit operations, and of course the repumping as well. So yeah, and the trapped ion is right at the surface. So you can see there's a lot of room, right? It's very promising. One exciting thing that they were very excited about, because again, this qubit transition was designed for optical clocks, was that there was a lot of, there's vibration resilience by the integrated beam path. Okay, so here what I did is deliberately defeated the cryogenic cooling vibration isolation, which usually there's a gas exchange space, so there's no mechanical coupling between the chamber and the cryogenic compressor. Defeated that, and now the ion is going and doing huge loops. And so this is kind of a long exposure picture of a loop that an ion is doing. And during that loop, the integrated laser beam is moving right along with it, right? And so because that, there's very precise stability, interferometric stability, and it's passive. You know, we're not doing any fiber noise cancellation on this at all, which is pretty exciting. And it actually survived. I think it would, if we would just have to have broken the coupling to break it. So yeah, that was very exciting. And then also we were able to show you know, illumination and detection with this integrated beam path. So light coming directly from behind the ion, we were still able to detect the ion state and not be blinded by the light coming out of the chip. So next, I think a natural thing is to do more, right? And Lincoln's certainly working on this. It's very exciting. Multiple zones of operation. You can imagine shuttling readily between these zones and doing QCCD type of stuff, which is very exciting that, you know, as this technology is kind of seeming to come online, this QCCD is also seeming more and more tractable. And, you know, I think the other thing is that, you know, at Lincoln Lab, Ciavarini has had a vision for integrating things in this chip for a while. There's a lot more that can be put in there. One other thing they did was put digital analog converters within the chip itself. So now a standard foundry actually fabricated silicon circuits beneath the chip. They put the electrodes on top. Now serial connections can just make all of the control of the digital, the electrodes. Detection has also been integrated. NIST and Schlichter and Susanna Todoro have done some work with nanowires, photonics obviously, and also microwave gates can be integrated into the surface. And there's even a question if you could do pixel traps for non-Schmidt-Kähler mines. And you know, there's really already been a lot of review even of what could all be in an atom chip. And it's been hard, packaging is hard. Cryogenic packaging is hard, but you can imagine many, many more things that could go in, which would be exciting. Okay, so that's, you know, I'm happy to answer questions about all of that. It's very exciting. I'm starting a new lab at UMass, Amherst. Where is that? It's kind of by Boston, but not. Yeah, it's very pretty this time of year. You should come visit next week. This is the building that I'm in, the physical sciences building. It's a picture of our laboratory, some renovations still ongoing, but we have at least one optical table, so that's great. And we've been fabricating surface electrode traps. So this is a sapphire substrate. We're kind of looking through it here. Single layer of niobium, 1 micron, just getting started with first things first. Nice for cryogenics once we get there. And yeah, this is just a single niobium layer, reactive ion etch, and we're dicing it at UMass. This is a scanning electron microscope image of our logo. Dicing sapphire is kind of a pain. Make sure your streets are nice and wide. This is a picture of our packaging. So we've used an interposer here. It's all vacuum compatible. And you can see the source kind of hiding on the right, left. And yeah, so we're starting with just a compact room temperature system. Pretty standard, enabled by a few things like small vacuum pumps, et cetera now. But we're working on getting ions in it. One thing that I'm hoping to do is test a lot of chips. The cryogenic systems have a nice turnaround time, but hopefully We're going to have a room temperature system that can test a lot of chips too. To do that, we've used a consumer grade oven from a store. Like you needed, it's just an oven. And it's a fun story. The postdoc Dave Reens at Lincoln that suggested to do this, he paid for the oven that we got out of his pocket because Lincoln's like, we can't pay some guy on Craigslist $50 for an oven. And he's like, well, I'll do it then. So, but he did it, it worked, so I'm also going to be attempting this. And so far, it's been really easy. You just cut a hole, which is not easy, but you cut a hole, you've got your vacuum pump on the outside, and just a few days, you got a vacuum. So it's great. Yep, we also didn't have to modify it. We were a little worried. It is a binary heating element, but it works fine. So, and that's about it. We are still working on getting ions. As you may know, it takes a lot of time. So one thing I'll just also tease is that I'm working on I've laid out a new photonic trap that Lincoln Laboratories is going to help fabricate for me. This has 4 different zones designed to test a few different things with a new type of qubit, Zeeman ground state qubit, lower power, hopefully a little better fidelity. And one zone is going to have gratings designed to focus to 5 ions within the same chain. And the other zone is to test some polarization stuff with the Gaussian generated beam with a singularity in the diffraction grating. So with that, I am happy to take questions. Thank you.
Thank you, Bob, for the nice talk. Your video is really addictive. I keep watching. Yeah. So Professor Kim, yeah, you can start the panel discussion.
Yeah, actually, there are many questions I also want to ask, but yeah, probably. Well, maybe simple things first. How high temperature can you go with that customer grade oven? Yeah, it was impressive.
Yeah, we were worried we'd have to do high temp bake, and we didn't. Yeah, we were just at 250. It was fine. So.
Oh yes, it still can go to 250.
Fahrenheit.
And then
sorry, Fahrenheit. Yeah, it's just 100.
Oh, Fahrenheit. Okay,
yeah,
okay.
Sorry.
Okay.
Yeah, no, we were a little nervous because the hydrogen kept going up, but it was actually the vacuum station that had bad pressure. So.
Okay. And then a little bit longer term. Yeah, some more. So yeah, compared to the typical ion trap as a surface trap, integration of photonics requires completely different resolution.
Yeah.
And then yeah, sometimes I feel like the order, I mean, for the typical electrode structure requires order of micrometer resolution, while the or 10 order of 10 micrometer, while the integrated photonics requires sub micrometer.
Yep.
And then I also agree that it probably is not easy to separate them and then bond two separate individually fabricated chip together. But
no, these
my
are
question is
this trap was monolithically fabricated. All right, so
yeah, but yeah, sometimes requirement for the photonics part and then the requirement for the more general planar trap might have some conflict requirements, and then you generally don't feel like there won't be any problem.
I think one question is, this is a single layer electrode trap, but you want a multi-layer stack, some topography maybe to shield the oxides, right? And then also you want to create extinction ratios from photonics that are nearby from each other to avoid crosstalk. So there's a lot of metal layer complications that could come into play, especially if you don't have a good crossing and routing in your photonic structures. So tapering up so you can have photonic crossings that are low loss, or just having multiple layers of photonics with escalators. I don't think it's going to be trivial, but I think it's very tractable because all of the losses effectively are, the power budget is not that bad for the, it's not a direct hit on fidelity, right? It's maybe a time that you need for the amplitude, but I think the conflicts are pretty minimal considering the advantages, yeah.
And somehow you probably implied that, but yeah, can you can I assume that the main reason you are using strontium rather than other ytterbium or other thing is because of the wavelength?
Yeah, that's one big reason.
System?
Yeah, right. So strontium requires 422 for most of its transitions, not below 400, so not UV. And that is exactly right. So I mean, we're hoping to push materials down and continue to lower and lower loss of the UV, so you can do higher and higher power for pulsed gates for ytterbium, et cetera. But yeah, that's exactly right.
Okay. And then yeah, probably yeah, just one more question. And then you are also using the sapphire substrate rather than silicon substrate or other material. Is there a specific reason for that choice?
Yeah, I think at cryogenic temperatures, at 4 Kelvin, you still have a lot of cooling power, but it is not a trivial task to get that cooling power out onto the chip, maybe through packaging, et cetera. So the better you can do it, reducing the heating from the RF itself, which we know happens with silicon chips, and get that heat out, just the better. I don't have any data to suggest it's better, though, necessarily.
Okay, then in terms of the fabrication technology, I mean, yeah, most of the technologies are based on the silicon technology, and then how much it will be different from fabrication for the sapphire substrate compared to the other silicon substrate?
Yeah, that's a really great question, and I'm not certain, frankly. I mean, obviously we're going to want an oxide layer, then a silicon nitride layer, or alumina or something else on there, and adhesion could be a problem, or bowing and things like this. But I think the main reason you would want silicon is that you could maybe put detectors in, avalanche photodiodes, which Lincoln has done, and as well the digital analog converters and all of the other electronics. So a full monolithic stack would require silicon, obviously. I'm not sure that's necessary, but yeah, that's why you would want to do it.
Thanks. Yeah.
Yes, I have a related question because it makes me curious. So you mentioned that this chip fabrication, right, is done in a Lincoln lab, and you design and they can produce, right? So it sounds a little bit like multi-project wafer process. And I wonder if this process, right, how, I think you're the best person to answer this question, that is it like CMOS compatible, or do you think is it continuously being CMOS compatible in the future? I'm curious about that.
Yeah, so their charter there is to really see how far down the road they can see. And so by sticking to full silicon CMOS compatibility, they're making sure they're seeing all the way down. And it's fully CMOS compatible. Yeah, the main question, which Professor Kim alluded to, is the lithography, right? You're talking about diffracting a 400 nanometer photon. So kind of in principle, you need a quarter of the wavelength to do that, and that's the bottleneck. So if your grading has that critical dimension, that's very difficult. So E-beam lithography is possible, albeit slow, maybe. So I have some collaborators at UMass that are very good at metal lens fabrication, and I'm working to hopefully collaborate with them soon to try some special techniques for creating stamps, et cetera. But that's the only alternative.
Is there any other question from the audience?
Yeah, yep. Yeah, photonics can get away with some things that CMOS can't, as far as defect densities and things.
Maybe I can ask one more question. So how many components were actually integrated in single chips. Yeah, so you were, I know that, Lincoln Lab has been testing with the integration of the APDs and also the that waveguide and also all other types of electronics. And then, yeah, you probably, yeah, my impression was maybe many of them were individually, or only a few of them were combined. Yeah. So how many types were the biggest one?
I think John Ciavarini and Robert McConnell have some exciting results. They'll show it the world soon, but I don't know exactly the status of those projects.
Okay.
Sorry.
Yeah.
Okay, I think we can finish Bob's talk here. Let's thank the speaker again. And we're done with all of our schedule today. And I want to thank all of our invited speakers for coming from the very far distance. And then we're all here all together and sharing the exciting results, the recent results from their labs. And I also want to thank the audience for coming and participating in our workshop. So yeah, with that, let's finish our workshop. Thank you all for coming.